So good morning to everyone. Today's the first talk. It is my great pleasure to introduce our Honorable Vice Chancellor, Professor Utpal Joshi. He is an eminent physicist, accomplished academic leader, and also the Vice Chancellor of Saurashtra University, Rajkot, with over 22 years of excellence in teaching and research. He has made significant contribution to physics through high quality publications, research projects, and the mentorship of doctoral scholars. He has received prestigious honors, including Young Foreign Science Award, Japan, Boykas Fellowship, DST, India, DAE Young Scientist Award, and SCRC Young Scientist Award. So, I invite Professor Utpal Joshi for his talk.
Okay, so good morning to all of you on this second day of this conference. I am a local boy and you should see here all the time. So basically, as Nikesh Bhai has said, I spend a lot of time in material science, and we were quite active group at Gujarat University. Prior to joining this university, I was, in fact, I am associated with Gujarat University Department of Physics. My background again is physics. But most of the work that I will present is somewhere between physics and chemistry, because those who do material science, particularly even this physics department of Saurashtra University, the thrust area is material science. You have to begin with chemistry. So unless you are very good in chemistry, it is very tough actually, because it is the materials that you grow and you make. If the quality of this material is ensured, of good quality, there will be subsequently the characterization where the physics comes into play would be quite difficult. So I shall be very briefly, I think I have half an hour time. So I would just try to talk about the brief review of these advanced materials in particularly, this is the domain in which we have been spending time. So, first of all, there is a disclaimer that whatever the material that I am going to, because in half an hour time it's not possible to cover up everything, but I'll try to touch upon some of the areas where we had some kind of, you can say, expertise and did some work. Basically, the functional oxide materials, which is the inorganic chemistry. Many of you must be doing that. In that, I shall be talking about the resistive random access memory. Some, this part perhaps I may miss. Some of my students have worked on this multiferroic compounds, and lately one of the students very good work in supercapacitors, and that is basically electrochemistry. So these are the domain areas in which we spent some time, and there was one novel strategy of nanorod growth of zinc oxide, and we tried to decorate that with this reduced graphene oxide, and the application area is the photodetector, UV photodetector, and this is this piece of work that I am going to spend about. What is encouraging is the organic electronics these days. Many of the things have been commercialized in organic electronics as well. So you know that your foldable screen like Samsung Z Fold, okay, so that is a foldable screen. Also you have organic LED TV of very big screen. Earlier it used to be very small, you know, 1 inch or 2 inch by 2 inch, something like that. But now the coverage area is very high. What is good about this point is there are many organic compounds which are, you know, essentially what you need is in electronics is the semiconducting behavior. That's a P and N type of material. Good point about some of the molecules is they are, you know, good either P type or N type or even ambipolar at times. So this is something I will touch upon. I go back to memory line where the first report was given by none other than the Nobel laureate George Bednorz. You know, Bednorz and Muller got the Nobel Prize in 1987 for the discovery of high temperature superconductors. And this is the era from where this, you know, the oxide electronics has started coming into play after 87. In one of his talk I was present at this particular point in workshop on oxide electronics, that was 11th, that was happened in Hakone, where he gave the title of his talk as Another Opportunity for Oxides. You see, high TC superconductivity, it's all oxide materials, and essentially it was like, you know, dream come true in a sense that oxides are known for, they are ceramics essentially, so they are known for insulating behavior, they are very good insulators. You don't expect even the conductivity, leave aside the superconductivity, but in this lanthanum compounds they found you know, superconductivity at very high temperature, elevated temperature, you can care about 40 Kelvin or so. That was the first report for which they were awarded Nobel Prize. And later on you see in superconductivity after that. By the way, my PhD is in high TC superconductivity, so this is very close to my heart because of that. And this gentleman perhaps is one of the inspiring figure in oxide materials. So what he said is, after this discovery of high TC superconductors in oxide materials, RAM, resistive random access memory, which I am going to spend a lot of time about, is another opportunity for oxides, because it can be, you know, all the conventional memories, flash memory or hard disk or everything, can be replaced by resistive random access memory, which in the present times is known as memory stars, as memory plus resistors. So that was the philosophy of his presentation. So let us talk about the brief on this transition metal oxide based resistive RAM, electric pulse induced resistive switching, EPIR, very popularly known as. So this was the talk, and here is the report of Bednorz group, IBM Zurich. In some compound like this, you know, when the chromium is doped into SZO, they have found that compared to normal ohmic kind of IV characteristics, what they found is, instead of, you know, retracing the path, it actually jumps to some other level altogether, and then it comes from this path. So it is the reduction after forming process, and then when you increase the bias, you know, very small bias, you look at this bias here on the x-axis, which is less than 0.5 volt. So in that, what they found, there is a jump in the current. Now when there is a jump in the current, obviously you put R equal to V by I. So when the I is changing rapidly, your R changes. So this we call it as the resistive switching. Now this was the actually second report. But the first report in the same year, which was in Applied Physics Letter, it was by Ignatieff, scientist is in UT Houston. They have given this particular, you know, characteristics of memory. In that, what they do is, you know, having this, we call it as the hysteresis, because when there is a irreversibility, then there is a hysteresis. And those materials which are having hysteresis in their any of the behavior, whether it is a PE behavior, so it's a polarization versus electric field, you have Fe RAM, ferroelectric RAM, right? In magnetic, very well known, you have BH curve or MH curve, wherein you have hysteresis. So that also is something what we call it as a, whenever there is a irreversibility, that candidate is known for its the memory effect, some kind of a memory effect in that. Now in this conventional IV characteristic, since you get the this kind of loop here, so IV characteristics is not reversible, there is an element of memory in that. And to characterize that, there are two ways in which the memory, the necessary part is the hysteresis in the IV curve. That is necessary but not sufficient. What you need basically is, when you give the pulse of the voltages, suppose if I generate with my, function generator, normal function generator that we use in MSc lab, okay, if I give a pulse of the voltage corresponding to where there is a jump, what I will be able to see is, I should have the modulation in the resistance, right, by applying the train of pulses, positive pulses and negative pulses, and which was first reported in this paper. This is the first paper here which reports the IV characteristics and the memory effect. This was the first report actually. Subsequently, in the same next volume, this is 76 APL 77. Bednor's group of IBM Zurich have taken up this problem seriously, and they have found these things. So both of these materials, here I have written PCMO, which is a praseodymium calcium manganite oxide materials, and this SZO, this is also perovskite oxide. The key word of this Bednor's lab was perovskite oxide, not superconductivity, by the way, for those who work on perovskite compounds. And this is the simple schematic diagram wherein you expect some kind of a insulating material. These are very high resistive materials. It is sandwiched between the two metallic electrodes. So essentially you call it as a metal insulator metal, MIM structure. And if you provide appropriate bias, DC bias, then you are likely to get such kind of property. At the time when this lecture I heard, I already started working on nickel oxide, that compound, as my postdoc in Tokyo Tech. And he visited the lab, Professor Bednor's, and he was quite thrilled to see me at working on nickel oxide, because he told me that this is one of the very potential material for RAM. And he said, why don't you give a try? Because my aim at that time was to work on P-type oxide semiconductors. You see, P-type oxide semiconductors are very few, very few. You have to go for de la Fossite structures. And de la Fossite structures in our lab conditions are very tough to make, single phase. So, like chromium aluminate or copper aluminate or all kind of materials. So he said nickel oxide is the one which is very potential, which has very high potential of working as RAM materials. If we look at very briefly, touch upon the mechanisms, people have started talking about why you get this hysteresis and what is the mechanism of getting the irreversible IV characteristics as well as the pulse induced resistive switching. Two models were very popular. One was the filamentary model. It is like fuse that we use in our domestic light, right? So when you have a fuse connected, okay, then the current passes from the device and you get the electricity. When the fuse is burnt, so it's you can call it as a rupture, right? At that time, the material goes into the higher resistance state. So under the bias condition between the two, because the thickness here is quite small, of the order of, let's say, 100 nanometer, and even if I give 1 volt, so you can calculate the electric field into the material. Very simple. It is, E is equal to, you have V by D. So V is the voltage and D is the thickness. So D is of the order of nanometers. So already you have 10 to the power minus 9, that order in the denominator. And voltage, even if it is 1 volt, you can find out that the electric field in the material which is produced is extremely high. So oxide materials can withstand that much of electric field, and that's a good point of that. So you should have a very right balance of the charge carrier free radicals as well as the higher insulating path in that. So that is one of the very well known model was about the filamentary. The other one is, since it is rich in oxygen, both this all the oxides, remember it is very tough to make stoichiometric or ternary this oxide materials. Why? Because you know this, they take the radical oxygen material from the oxygen from atmosphere as well during the heat treatment and the cooling cycles. So what you get basically is when we write O3 here, it is never 3. It is always kind of 2.9 or 3.1 or something, right? So if you have that is a stoichiometric one, in that case there is a what is called the oxygen electromigration. So if in this case it is a planar model, here it is a sandwich structure. So in sandwich structure, this is quite well understood that because of the trapping of the oxygens near the interface or the electrode could lead to this resistive switching. Then people started talking much about after evaluating so many oxide compounds, binary oxides as well as the ternary oxide, it was broadly classified into two categories. One is the unipolar, the other one is the bipolar. Two kind of resistive switching is proposed. So in the unipolar, what you need is the single polarity voltage, so either positive or negative, to switch the material from its high resistance state to its low resistance state. And in case of the bipolar, this happens with the opposite polarity. Now, when you say opposite polarity, at that time not necessarily the magnitude of voltage is same. So that is why it is written here as symmetrical. Symmetrical का मतलब है you have the same voltage at which the switching happens in the same polarity with the positive or negative, or you may take the material into the opposite polarity. So you have a fourth quadrant here, a third quadrant coming into play, where with the opposite polarity you can switch the material from its one resistance state to other. So broadly, whatever the reports available so far, thousands of papers, tens of thousands of papers I would say, are published in this particular domain, wherein people have reported either the unipolar switching or the bipolar switching. It all depends upon the material, right? So and this in this one, the top electrode here metal, this is also the blue color, here is also metal, and about 100 nanometer is the thickness of transition metal oxide. The top electrode may be silver, gold, aluminum, platinum, lanthanum nicolate or YbCO, which are room temperature milliohm resistance material. And the this is the layer here, this is red color. So that is the TiO2, hafnium dioxide, STO, strontium titanate, or you have this PCMO, that is praseodymium calcium manganese. And the bottom electrode here again is the same like metallic ones. Okay, so I try to dig the literature in that with all different papers that is projected here. You see, these are quite complex materials to prepare in the lab. Okay, like SZO, lanthanum cobaltate or PCMO. But if you have a very simple binary oxide like nickel oxide, any transition metal oxide, it will be quite easy to form. And what is important is this X. So if you can somehow tune this X, so NiO 1 minus X or 1 plus or minus X, in that case it is very interesting. By the way, this material nickel oxide was grown on platinized silica, one of the very well known, well established substrate which is commercially available in the market. So one can deposit this nickel oxide by any means. Ideal way is to grow by pulse laser deposition, or even if you don't have that facility, with this chemical solution method also. Nothing can happen in 5 minutes. Yeah, I will just try to pull on. Yeah. And this report of 2004, let me tell you, this is from Samsung Electronics, from Korea. Okay, and this report prior to that in 2002, 2003 itself, they have tried to do all kinds of, making the memory arrays in that. And they came into, commercial application in this year itself. Okay, commercial I'm talking about, not at the research level. Now what is promising about that is that it is a non-volatile, small cell size, fast read write and low voltage. In each of the cases, if you see here, the voltage, magnitude of voltage, sweeping voltage is very low. This means power dissipation is very less. And that is something and this transition from one state to another state is very rapid. So it is fast read and write. Now what is common in all this is the dirty film has a better switching performance. So that is something very interesting, that if you try to make, with molecular beam epitaxy or any other kinds of method like a PLD, you are likely to get epitaxial quality film. But if you do epitaxial quality film in all these materials are classic materials. Lot of people have done huge work prior to these numbers which you mentioned here. But the thing is that whenever they got the polycrystalline, all these reports are indicating that they are not epitaxial quality, they are polycrystalline. So if you have a polycrystalline sample, then the likely to get better switching property, that is what established. Okay. Mechanism is again very skeptical. From material to material, people write different stories altogether of switching performance. And binary transition metals such as nickel oxide are more favorable because of this compatibility with the CMOS. It's a complementary metal oxide semiconductor wherein most of your components in a chip are fabricated of. So if you do any complex material, although academically it is good, but then if you really want to go for application side and put it along with our conventional electronics, in that case the binary transition metal oxides are important. So not only oxides, but if you go back into literature, some of the Nature papers in 2003 where they found this read-only kind of memory which is based on polymers. Now this is also very interesting. This memory line, this Potember's report of 1979 in copper TCNQ, which also is the first report, I would say, in polymer based random access memory. So that is very encouraging in that case. And later on people have started with some of the C60 derivatives such as P.PSS, which is very popular material these days in organic field effect transistors. And so that is what the report also is. This is quite a modern report, 2010 it was published. And so these are the very scalable kind of several molecules have been tried and tested, whether with the p-type or n-type conductivity. Some of them are ambipolar. So that is also one of the report. I will skip this because this is talking about the mechanisms, which is not for this audience here at present, but one can refer this Sava's paper and Vassar's paper, wherein all the mechanisms, possible mechanisms have been undertaken. We published a lot of work in, these are all our group RRAM papers, about 16 papers we published in RRAM on different compounds with planar structure as well as the sandwich structure. One of two papers which is quite close to my heart, I will just try to brush it up. One was this PCMO into these things, and remember this is a planar structure. Now PCMO has been studied very extensively prior to our work, which I am going to present here. What we did in this case was, with all available substrates, we try to grow them. Okay. Now you see, when you grow any thin film, basic idea is when you get a better quality or good quality epitaxial quality film is if there is a lattice matching between the substrate and your active material. What we did was, We tried with the extremely good lattice match substrates such as strontium titanate or lanthanum aluminate, which are also perovskites, and then taking it on the glass, so which is amorphous. So if you try to systematically see that how much is the lattice mismatch between the active layer and that of the substrate, you can get variety of hysteresis. You can see here, over here, and the most encouraging one was this, and surprisingly it is on quartz. So that is highly lattice mismatch or amorphous. Quartz is glass, basically silica. So this actually proves the hypothesis or what we have mentioned here that this the polycrystalline quality gives you better film. So this is something was quite encouraging, and we did all the analysis of that and tried to see that how the resistance switching ratio actually changing with the compressive and tensile stress. So when you have a more stress, then at that time the switching property is better. In fact, it goes beyond 100%, which is quite astonishing. Not only that, we tried to see with the other compound here. This is also homemade, strontium ruthenate. Strontium ruthenate is very highly conducting oxide materials, and because we wanted to put oxide onto oxide with good lattice matching, and this is what we tried to see the cross-sectional FEACM and try to see the lattice matching in that. With this compound, this is the result that we have got. Other paper which was in Journal of Physics D, and that is on the BFO. Let me tell you, BFO is a very hot cake these days because of not only for this RAM, but it is very good multiferroic compound. It's a single phase compound, bismuth ferrite, BiFeO3, on again perovskite conducting bottom electrode, that is lanthanum nickelate, and we tried to do the study on such kind of material with all interface and the XRDs, and this is something what we have found in this, and this was very appreciated. In fact, we had two. Okay, so now we in fact we analyzed this and had some even industry collaboration into this compound. So I will just, in the interest of the time, don't write anything, and what we did was the later on checking the endurance and the retention, which are the two very important characterization of the memory. As I said, only hysteresis in the IV is not sufficient. What you should have is the endurance analysis as well as the retention, that how long this so of the order of up to for 450 seconds the HRS and LRS state remains. Okay, so this is another part. We try to do what by putting one of the buffer layer of this cobalt ferrite and try to see whether even there is a magnetic tunability of the resistive switching can happen or not. So this is one try that we give. And as I said, if you have a good quality film, one of the ways to control defect creation is the irradiation experiments. So we did some, I was associated with this institute for quite a long time, and we did several measurements of SHI induced, swift heavy ion irradiation induced, which can create the defects in that. So yeah, this is something very interesting. This is with the magnetic field, you see. So you know not only the bias, but the magnetic field, applied magnetic field, is also quite important and interesting in this. This is the old results that we had, which is a atomically flat single phase with the solid phase epitaxy. We have prepared the epitaxial quality film. This is a read data, and we tried to do all kind of measurement. One of the students has done it in the copper phthalocyanine. Yeah, okay. So this is with the copper phthalocyanine with the 100 keV argon, and try to do. And this is a new Journal of Chemistry, one of the papers of carbon-based RGO compound. So this the story was, so this we grow in the lab. You can see the very good hexagonal structure of zinc oxide, and we try to find out the density of that by optimizing the growth part. And what the strategy was basically to make this is a seed layer, and these are the ZNO nanorods, and we try to decorate with the RGO and try to see, these are all the results under the UV illumination, and we try to find out the responsivity, transient photo response characteristics, and it was proved to be good. And this work was again with the SEC ISRO, we tried to make the tunable antenna, and which was space qualified actually later on, of making about 27% of the platinized electrode. So so many things people can do with these advanced materials, and that is with the after Ellen Higger's and Shirakawa report on conducting these things. So you have all kinds of applications available, and this is the area in which it is quite open up. Many can do work on that. Basically what you need is the pi conjugated polymers, and we did some work on pentacin FET, field effect transistors, which is ambipolar, and try to demonstrate the field effect transistor characteristics in that. So these are the typical device structures of OFET which we worked on. So this is something what we had. So that is something what we have. So I am completely running short of time, so I am not able to touch upon the mechanisms and other things. But as I said, these are the very small domain of the oxide electron or the electronic applications to advanced materials. But there can be possibilities of many more other things, which I may wish to talk about it sometime later. Thank you.
Thank you so much, sir. It sure was a fresh start to our day too. Now I request the dignitaries to kindly felicitate Professor Utpal Joshi, sir. Thank you so much, sir, for sparing us your valuable time. Now, next on the queue, we'll be listening to J. Paul Atfield, who will be joining us online from Edinburgh, United Kingdoms. Can we have him, please?
Hello. I hope you can hear me.
Hello.
Yeah, shall I share my slides?
Yes, please.
Okay, so if I share screen and
Professor, we are able to hear you, please.
good. And are you seeing my slides?
Yes, we are able to see your slides. Please,
Yes, sir.
Yes. Right, okay, well, I'll start now then. So, firstly, thank you very much for the invitation to speak and for the award from the CRS. It's a great honour and I appreciate very much. For the next sort of 20-25 minutes, I'm going to talk about research that we've done over the recent years on making new materials from high pressure. Our group is based in the University of Edinburgh in Scotland. We have this centre, with this nice photo taken in the winter, and our centre called CSEC, Centre for Science at Extreme Conditions, specialises in the use of high pressure for different types of science. This slide gives an overview of why we might want to use high pressure, in particular for materials research. A reminder of basic thermodynamics for everybody, the Gibbs free energy. And what we're really playing with here is the PV, the pressure times volume term, that as we increase pressure, volume has to decrease to lower the free energy. And so as a result, we can use high pressure in synthesis to make structures that are more dense, more highly connected with broader bands. It's also quite good for some practical things like suppressing the loss of volatile elements. I'll mention that in the context of nitrides later on. We can also find new and unusual structures, new unusual phases of elements or simple compounds, usually at very high pressures using diamond anvil cells. And then there's a lot of sort of new physics or exotic physics that can be explored using high pressure measurements, where we measure, for example, conductivity or magnetization of samples under pressure. Probably the most famous of these is superconductivity in metal hydrates over the last 10 years, but there are many other kind of quantum phenomena and metal insulated transitions and the like. The work that we do in Edinburgh, we make use of this apparatus, a high pressure press, and we take a very small amount of sample. The scale here is about 5 millimeters high for the sample, so it's very small. It's heated by a graphite heater. It has various ceramic parts around it, and then that whole little sample assembly sits between these very hard tungsten carbide cubes, and these are pressurized using the high press. So we can get to pressures like this, and again, if you're not familiar with the units, then 10 GPa is the same as 100,000 times ambient pressure, so it's 100 kilobars. So we're working at between 100 and 200 kilobars, and these are typically the high pressures that we need to change the chemistry of solids, and while we also heat. And of course the downside of this work is the samples you make are very small, so this is really aimed at fundamental research, trying to explore the properties of new materials. The type of materials we're interested in are transition metal oxides. I've just put some typical examples here. So these are well-known materials for lots of practical uses, for example, lithium cobalt oxide battery materials, or the yttrium barium copper oxide superconductor. They're characterized by being based on quite simple solids, such as a simple one is perovskite, which I'll talk about a lot. Perovskite has different forms. It can have tilted octahedra, it can have cation ordering, what's called a double perovskite, as indicated by the colours here. And there are variants on it, layered perovskites as well, sometimes called Ruddleston Popper phases. There can be exotic orders, for example, of orbital and magnetic states, as shown in this is the lanthanum manganese oxide here. But in general, these perovskite phases are usually quite dense materials, and of course, this is what makes them favourable for high pressure. So I'm going to try and just give a very quick overview of three kind of case studies we've worked on in recent years. And the first of these was a very simple idea. It's, again, here's a perovskite structure, and perovskites are often stabilised using these typical 2+ metal cations, calcium, strontium, or barium. Now, they're good, of course, at stabilising the structure. There are also different uses of perovskites, but they themselves don't have any functional properties. And we wondered if we could use high pressure to replace calcium, which this is the radius. It might be a bit small, but calcium has an ionic radius of 100 picometers, whether we could replace it by manganese 2+, which actually isn't too much smaller. It has a radius of 83 picometers. And of course, manganese 2+ is very interesting because it's from the transition metal block. It's got 5 unpaired electrons, so it's got a very large magnetic spin, and so it can add further magnetic functionality to materials. And we were particularly interested in trying to make analogues of this material. It's a double perovskite with iron and molybdenum arranged on what are called the B sites, the octahedral sites. It's quite famous for having a property of very high magnetoresistance. That's to say, it's magnetically ordered, and the electrical current that's passed through it comes from conduction of spin polarized electrons. This is a theory paper from D.D. Sharma and others in India some years ago now. But anyway, the theory of this essentially relies on having as large as possible a magnetic moment in the system. And strontium is non-magnetic, but if we can use this trick to replace strontium by manganese, then we can increase the magnetization in the system. And indeed, this is what happens. I'll just put the results up. We made this material. We use rhenium instead of molybdenum. We have ordering of these two on the B sites, but then we also put manganese 2+ onto the A sites of the perovskite. I won't dwell too much on all the physics data that are shown here, but just to show it does have very interesting properties. It's magnetically ordered with a Curie temperature of around 500 Kelvin, so it's a real magnet. It's magnetically ordered at room temperature. And the magnetoresistance is how the resistance changes to a magnetic field, and it actually changes from being negative. In other words, the resistance gets smaller if you apply a magnetic field at, say, 100 Kelvin, but then at low temperatures it becomes positive. The resistance actually becomes bigger, and such transitions are not unknown, but they're quite unusual. To understand what's happening here, a very important tool we use a lot is neutron diffraction. So this is like X-ray diffraction, but using a neutron beam. And neutrons are sensitive, as well as the positions of atoms, to also the magnetic moments and which way they're pointing. And so we can do magnetic crystallography with that. And in this case, we were able to show from these peaks that emerge as we cool the material down below 100 Kelvin, which is where this resistive transition comes in, that there's actually a tilting of moments. There's actually a frustration between the B site, rhenium and iron, and the A site, manganese. And so we have a frustration switching of the magnetoresistance in these materials, which hadn't been seen before. As we went further with our high pressure research, we had a kind of lucky accidental discovery. We found that if we replaced half of the manganese by calcium, we could make a new structure type. We call it a double-double perovskite because we now have ordering of 2 cations on the A sites, these columnar sites. So calcium organizes here and manganese there, in addition to the ordering of iron and rhenium shown by the 2 colors on the B sites. And this restores the kind of the expected magnetoresistance properties. We just get a very large negative magnetoresistance, which is what's normal in this effect. We turn off the frustration that we had. And this slide summarizes everything we've done since then. It's around 10 years of work. It turns out that you can make a lot of these different double-double perovskite materials. There's a lot of chemical substitution games you can play. You can put rare earths in as well as calcium. You can have different charge combinations, as shown by these examples here, and they have lots of different magnetic properties. I'm not going to attempt to discuss them. But the important thing is it's really a very large family of new materials, and it's entirely made possible by using high pressure. All of the materials in this table have been made in our group using high pressure, and so far nobody has yet made one of these phases at ambient pressure. It'd be wonderful if it could be done, but at the moment this is purely a high pressure family of materials. I'm moving now to my second topic, which is actually something quite simple: new iron oxides. Iron oxides are very prevalent in nature and also in technology. The ferrites, which are based on doping magnetite, Fe3O4, are very prevalent. There's a diagram here taken from a paper that shows the different uses of magnetic oxides. It's either particles or nanoparticles in different applications. And magnetite itself is very, very interesting. It has a very complex electronic order. We worked on this about, over 10 years ago now, and again, I'm not going to dwell on the details, but has a very complex low temperature electronic order below around 120 Kelvin. We get ordering of different charge states, iron 2 plus and iron 3 plus, represented by the colours here. There's an ordering of the orbital states of iron 2 plus, and then also these unusual units that we called trimerons, where this is essentially an iron 2 plus. The electron is actually spread over its neighbours a little bit. We see we make weak, essentially metal metal bonds between the iron and its two neighbours either side. They get pulled in a little bit. And so these units we've shaded in green, these trimerons are what are ordered through the long range state of magnetite. And this was for a long time a mysterious state. Discovered first by Verwey back in the 1930s. So, in addition to sort of elucidating magnetite, around the same time, other groups, and I do stress this is not our own work. A lot of this has been done by the Dubrovinskys and others. Discovered that a whole family, very many new binary iron oxides can be made at pressure. This diagram taken from the paper shows some examples here, new exotic compositions like Fe709, Fe405 and so on. And the exciting thing, I think, certainly from my point of view as a chemist, is that each of these is then the starting point for a family of ferrites, in the same way that magnetite, which occurs naturally, is the starting point for the ferrite spinels that we all use as magnetic materials. So a PhD student of mine, Jackie Hong, his project was to look at chemical substitutions in one of these materials, the Fe405. And here we can take this, there's a trigonal prismatic site, which is in the binary material is occupied by iron, but we can replace it with other cations. And they all seem to have a lot of interesting properties. Again, I'm just going to actually talk about one of them, the calcium material. When we cool that material down, we observe it has a magnetic transition around room temperature, which is nice. But then when we cool it down through that transition, we see all the diffraction peaks splitting into two, which tells us there are actually two different phases, two different forms, polymorphs, if you like, of the same material. And it turns out, and again, I'll jump through the detail on this slide, that what we're seeing is that one of the two forms, the one that's charge ordered, CO, has these trimeron groups, the same thing that we discovered in magnetite. They're represented by the green lines here. We have three parallel spins and a single d electron delocalized between them. The other form, which we call charge averaged, is also magnetically ordered, but in a different way. It actually doesn't have trimerons. So it's a rather remarkable example of what's called electronic phase separation. It's well known in manganite perovskites, but this is the first time it's been observed in iron-based materials derived from magnetite. The last topic I'm going to come on to is a different area of chemistry, and I'm switching here from oxides to nitrides. It's well known that we can make lots of different oxides, and furthermore that oxides and also fluorides can stabilize very high oxidation states of transition metals. So these are some famous literature examples. We can stabilize an iron 6 plus oxide or a copper 4 plus fluoride. But we generally can't do this with nitride, and that's because in general it's difficult to make metal nitrides. We're always fighting against the stability of the NN triple bond, so that if you heat a nitride up, it tends to lose nitrogen gas and reduce to a lower oxidation state or to the metal. Now, it's already known that we can use high pressure to stabilize nitrides in diamond anvil cells. There are some exotic examples, for instance, these dinitrides or even iron 2 plus N4. But they're still not really very oxidizing. And the work that I'm going to show here, that the credit really belongs to Simon Close. He was a postdoc in my group a few years ago, and he's now a research fellow at LMU, University in Munich. I'm actually visiting his group as a visitor in Munich at the moment. And his great idea when he was a postdoc was to say, well, let's try doing the high pressure chemistry in the press that I showed earlier, but using a reactive nitrogen source. And what we use is sodium azide. Azides, one has to be very careful with them. They are toxic and they're also explosive. Organic azides are actually the chemicals in an airbag of a car, so they release a lot of nitrogen gas very quickly if they're subjected to a shock. But it's turned out this is a very nice trick for making nitrides. The first example I'm going to show comes from the world of perovskite. So again, here's that ABX3 structure of perovskites. I talked about some oxide perovskites. These are simple ones. We can also make halide perovskites, very famous for their optoelectronic properties, such as methylammonium lead iodide. If we replace oxide by nitride, there are a small number of examples of oxynitrides that are known, where we have a mixture of oxygen and nitrogen. But if we want to make a simple AbN3 perovskite, there was actually only one previous example in the literature, and the reason this is difficult is because we have to stabilize very high oxidation states of metals. To balance the charge of 3 nitride anions, we need this, which is a very relatively unusual combination. This looked much more attractive because we can use rare earths, the lanthanide elements, as the A cation on the A side here. If we can stabilize a high oxidation state +6 of a transition metal. And this is what worked very nicely. Yes, hello? That's fine, I'm nearly finished. And that worked very nicely. We were able to stabilize this perovskite LAN3. It's the first time that this has been, that this combination of charges has been stabilized. And then moving on, we're also able to make the very first examples of layered perovskites, sometimes called K2NIF4 type materials. Again, I won't play on the details, but one of these is ferromagnetic, the other is anti-ferromagnetic. They're metallic as well. And although this structure type is again very important for superconductivity in copper oxides and many other functional materials, it's actually the first time that simple A2BN4 nitrides have been made, thanks to using this high pressure synthesis method. So that brings me to the end. What I hope I've shown in this quick talk is that the high pressure synthesis gives us access to many, not only new materials, but even new classes of materials. And the stress is very much on the word recoverable, that we can actually do the chemistry at high pressure and temperature, but then afterwards these materials are stable at ambient conditions. They're stable over very long periods, so we can study their properties. We can observe things like these usual coordination environments, putting manganese on the A sites of perovskites, these new ferrites, and lots. I didn't talk about all of these, but really a whole number of new nitrides are made possible by that route. So I'll just finish by thanking different members of my research group, a couple of photos covering the last 10 years or so, and also different collaborators here and the research councils. And thank you again very much for the invitation to speak today. Thank you. I'm happy to take any questions if there are any.
Thank you, Professor. Indeed, it's a fantastic lecture. We all of us truly enjoyed. Now, on behalf of CRS, we honor you with our honor. It's a medal. So we are going to present before you in virtual mode. Kindly accept it.
Right, of course, I accept with pleasure.
Yeah.
This is your gold medal, will be posted to you. This plaque and medal will be posted to you, your address shortly. Thank you very much indeed for accepting our honor. Thank you very much. Thank you. Bye-bye.
It's a great pleasure. Thank you very much. I'll shake your hand online. Thank you very much, everybody. I'm greatly honoured. Thank you.
Welcome, Professor Sampath. Namaste. Good morning.
Hello, namaste, good morning.
Good morning, Marina. We are eagerly waiting for your talk. Please proceed.
Sure.
Please.
Thank you. It's just a minute. Is this screen visible to you? Hello?
Yes, Professor, it is indeed visible. We can
Okay.
clearly see and we can hear you very well. Please proceed.
Okay. Thank you very much. Good morning to all of you. My apologies for not being there in person. I'm very sorry about it. Indeed, it's an honor to receive the CRS award. Let me thank CRS for this invitation to present the work and also for the award. What I would do in the next 20 plus minutes or so is to give you an idea of something different from what was talked about in the high pressure, but then this will also have some pressure that will come up at some stage. So this is related to electrochemical interfaces. I'll just start with a little preamble on how the interfaces are quite complex. Even a metal solution interface that we think we have understood quite well is not so as yet. So quite complex. So I'll just give one or two slides on the recent findings as to how complex the interfaces are. I shall just then go on to three different aspects. The first one is related to reactions under surface pressure. The pressure that I'm talking about is much smaller than the pressure that was talked about in the previous talk, but then this will have some pressure exerted on molecules. Then I shall go on to using certain organic materials for batteries, and particularly talking about how strain in the system helps in having good electrochemical characteristics. Then if time permits, I'll just go on to very briefly on looking at molecular assemblies, how assembling a molecule on a surface can change the thermodynamics and also the kinetics of electrochemical reactions. Just come to the first part of just the preamble. I just mentioned that the interfaces are quite complex. As you see on the screen, interfaces are there everywhere. It could be a solid-solid, solid-liquid, or a liquid-like liquid type of interfaces. If you take something like photovoltaics, you have a semiconductor-semiconductor interface. So wherever we have two dissimilar sort of conducting phases coming in contact with each other, we essentially have an electric field in between and the interface is electrified. And this is seen all over, not just in electrochemistry, but in other places as well. So some of the examples are given on the screen. It could be battery, it could be plating, corrosion, sensors, and whatnot. This is what was known earlier, quite some time ago. This was initiated in the 19th century by Helmholtz, as you see there, 1853, and there's been plenty of contributions from all over, including from India. We do have lots of information available on the interfaces. So this actually makes us feel that yes, we probably have understood quite a bit about the interfaces, but it's not really so. I'm just giving you one example which has recently come up. I'm sorry about the resolution of this particular slide. It's been downloaded from the website. So this is a recent paper in a journal called PNAS on the AA structure of platinum aqueous electrolyte interface. If you just notice what's given on the red, the underlined one, the interface does not follow the classic behavior, which is known already. But there is something more to it because of the polarizability of the surface and also the solvent, which needs to sort of put into when we are talking about the interface, which means you need to have another electrical element, another capacitor that comes in as well. So this changes many different things as far as the double layer is concerned. I'll just go on to one another example to say how complex the interfaces are. What you see here is actually a cartoon where there is an electrode surface in water. The electrode surface has the little hydrophobic molecule attached to it. Very often the surfaces that we use are not completely hydrophilic, it's not purely homogeneous. And if we have a surface like this in presence of water, pretty close to those surfaces, water doesn't behave like water. So it behaves like water vapor, it behaves like water with a low density. This is something which has serious consequences. It could be in biology, for example, protein solubility, protein stability, and many other things as well. And how does one understand this is what is given here. This is an atomic force microscopy study, electrochemical atomic force microscopy study. What you see on the screen, just on the top, is the water molecules, and then this is the surface. Pretty close to water molecules, and between the surface and water molecules, you see a gap there. And then that is the place where the water behaves slightly aprotic. What do I mean by saying that? Just below that, if you look at the dielectric constant as a function of distance, and from this particular point, if we go inside, the dielectric constant changes, and it reaches a value of 78, which is known for water, after about 2 nanometers. So from the electrode surface for about 2 nanometers, the dielectric constant of water is pretty low, and it behaves like an aprotic medium. This is an observation which was looked at by statistical mechanists in some sense quite some time ago. What you see as Chandler's paper, it's actually a calculation wherein a hydrophobic pocket is in water, and the water molecules can go around retaining the hydrogen bond. But then if it is extended, the water molecules cannot have that. So there is an entropic cost as well as an enthalpy cost. So with that as a little preamble to talk about the complexity of the interface, I'll just go on to 3 different aspects. The first one is electrochemical reaction under surface pressure. Essentially, when I have surface pressure on the molecules, it brings them closer. They're all in close proximity to each other. And in addition to that, you have nicely oriented molecules, and they're all confined. These 3 qualities actually give a lot of advantage in terms of the reaction kinetics as well as the thermodynamics, as I would just show based on one example. Just to motivate the talk, these are some of the papers that have come up in the last few or several decades on looking at proximity and confinement. It could be insulator to metal transition, morphological transitions, and also lateral electron transfer rate. All these things can be tuned by having what we call as a surface pressure to the molecules. What do I mean by saying surface pressure? It's nothing but a Langmuir trough that we have, and in a Teflon trough wherein you have an aqueous medium, just water. And if I'm just going to have a surfactant on the water surface, the way it gets organized is like this. So you have a hydrophilic group which is facing water, and the hydrophobic tail is above water. So it's at the interface. But if I'm just going to compress this mechanically at the interface, these molecules start to get organized and they start to interact, and they form a nicely organized structure. So when they are nicely organized, you do have a huge pressure on these molecules, which is what's given here, few dozens of megapascals as you see here. And in addition to that, you have all the orientation order and then reduced entropy, which actually leads to advantage in terms of certain reactions. So typically we have this kind of an ordered structure. And then when we have an ordered structure, it's possible to have an electrode just at the interface, not by dipping the electrode in the solution, but it's just on top of water. So the electrode is actually going to feel the potential difference as in an electrochemical cell. In addition to that, the molecules that are going to react at the electrode surface will feel the pressure as well. And that's what is going to be done here. So what you see on the right is actually the way the molecule is actually brought to the interface. It's not a molecule in this case, it's an ion. I'm going to describe a polymerization of aniline, which is an age-old problem. People have been actually looking at polyaniline for a long time, which also received the Nobel Prize several years ago. So typically, we have aniline which is brought to the interface. Anilinium chloride is a salt which goes into the solution. And when we have a graphene oxide monolayer at the interface, graphene oxide can be stabilized as a monolayer at the water interface because of the charges associated with the edges, and depending on the size and the buoyancy is all right, it will all form a nice organized monolayer. So this negative charge will actually attract the anilinium positive ions, and that will come to the interface, and after that the electrode is seeing the anilinium and the polymerization is carried out the way it is usually done. Now what is important here and why is it that this is being studied? And if you polymerize aniline, there are various ways of looking at it, and then this is how it goes about. We will not look at everything except the third and fourth row. We have a bipolaron and the polaron. And the structure of this, if you look at it, this is a benzenoid ring and this is a quininoid ring. And these are all benzenoid rings. And this polaronic structure is preferable, but very often when you carry out polymerization of aniline, could be electrochemical or photochemical or thermochemical and whatnot chemical, you always end up with a mixture of two. This is like making carbon nanotube. You always end up a semiconductor in the metal nanotubes. So essentially, one needs to have only the polaronic structure, and that will only see the light of the day in terms of commercial applications, simply because the conductivity is much higher than what you will have for the bipolaron. People have been trying to look at it quite some time, and what I'm just going to show you is that when I polymerize it under surface pressure, it's going to be a polaronic structure. So what is done is bringing the aniline close to the interface, and it's polymerized like the way normally it's done. Once it is polymerized, it's characterized, and what is characterized is what is given here. What is characterized is what's given here. So on the left, what you're seeing is the automogram of the polymer, which is polymerized Xe2. When I say Xe2, this is actually the polymer without under surface pressure. And on the right, what you see is actually the polymer with surface pressure. You see that there are 3 redox peaks on the left, whereas only there are 2 redox peaks on the right. Why is it that there are only 2 redox peaks? We do have, Why is it that there are only 2 redox peaks? You do have the quinone that is available for the bipolaron is not seen on the polymer when it is actually polymerized under pressure. There are several other characterizations which I will not go into details on, and what you see on the right bottom is actually the atomic force microscopy of where the polyaniline actually gets formed on the graphene oxide monolayer surface. We know that, okay, the redox properties show that one is a polaronic structure and the other one is a bipolaronic structure included. It's essential for us to understand this using spectroscopy. So we do a lot of in situ Raman spectroscopy and also ex situ Raman spectroscopy to find out if it's a polaronic or the bipolaronic structure. What you see on the top is actually the Raman spectrum of the polymer formed under pressure, while the lower one is actually the one without pressure, open barrier conditions. By looking at the stretches associated with the CH bending of the benzenoid of the quininoid ring, which is given on the right in the table, one can easily make out that the polymer that's formed under pressure is a polaronic structure, while the other one has both. But what is the consequence of this? I'm just going to show you right now. Okay, let me just explain what that is. This is an electrochemical cell where the electrode is coated with the polymer polymerized under surface pressure. That is on one side of it. When I'm just using that as an electrode in an electrochemical cell and apply a potential, you see the actuator action. Essentially, the electrical energy, electrochemical energy is converted to the mechanical energy, and you see a nice actuator action. This actuator is possible only with the polaronic structure, whereas you have a bipolaronic structure, you do not have the actuation happen. So you will not see the movement when I make the polymer on the surface without pressure. you do not see the movement at all. And just to give you some snapshots, what you see on the top is actually the surface with a polymer carried out under pressure, whereas the lower one where you do not have pressure and you see the nice actuator action as such. What is the reason for this actuator action? We try to understand using impedance spectroscopy, and we try to understand and analyze the interface using a lot of equivalent circuit. Essentially what we understand is this is related to the intercalation of molecules, and there is a directed electric field at the interface which leads to this particular process. What are the applications of something like that? These are all in artificial muscles, soft robotics, micropumps, sensors, etc. I'll just switch gears and then go on to a slightly different aspect right now. I'm going to talk about an organic material and use that organic material, which is a polymer, as an electrode for battery. And I'm just going to try to convince you that the polymer has some strain, and that's the reason why it acts as a good electrode material. There has been a lot of interest in strain and inorganic systems. What you see on the screen is actually a strained inorganic material. This is a ternary chalcogenides containing selenium and tellurium with molybdenum. You have a nice crystal that's there on the surface. This is grown using chemical vapor transport, and this has strain because some selenium is actually replaced by tellurium. So you have a change in the atomic mass, and there is a change in the bond length and also the bond angle, and that leads to strain in the lattice, which is understood based on the Raman spectroscopy that's shown below. But what I'm just going to talk about is an organic system. Why is it that I just want an organic system? I'm going to use a polymer for an organic system-based, magnesium-based battery. And plenty of work on lithium batteries, and then there have been interest in looking at beyond lithium. And magnesium and aluminum are obviously the choices. But magnesium and aluminum have other issues in terms of little oxide formation on the surface, and hence the reversibility is not really very good as you see in terms of lithium. People have been actually looking at inorganic systems for quite a while, but the reversibility is not really much, and that's the reason why organic systems are actually brought in. Inorganic systems go through the kind of mechanisms that are shown on the screen right now. So you do have what we call as insertion, alloying, and conversion, which leads to changes in the structure of the inorganic material. But when we come to organic electrodes, we essentially have only the ion coordination process with a functional group, and that doesn't lead to any of those ruptures in the inorganic structures that we see. But there are issues associated with organic systems, which are essentially the solubility in battery solvents and stability. To do that, one goes into polymerizing the material and then try to use that as an electrode. So this is totally out of serendipity. What is done here is actually a polymer based on a quinone and pyrrole. What you see on the screen right left top, two beakers containing quinone and then pyrrole. And these two beakers, if they are just kept as such in open condition and then close it with another bigger beaker and leave it at room temperature overnight, you essentially will see the pyrrole going into the quinone and start to get polymerized. Of course, the conditions that's given is all optimized in some sense to have a particular property. So you have with very simple component, you end up having a random copolymer which is amorphous in nature. But the advantage of this particular polymer is that it's not soluble in battery solvents, and it has the functional groups that can pick up the metal ions for batteries or metal ion storage. So we use this as an electrode material and then try to look at the magnesium ion storage. But before looking at the magnesium ion storage, we try to understand the polymerization process, and this is how the polymer actually happens. And essentially it's a nucleophilic addition followed by the Diels-Alder reaction, which is what leading to all this. So we try to understand the different components of the monomer. Even though it's amorphous, one can actually lead to this kind of a monomer and understand the polymerization process. After making this polymer, we do characterize them. These are all the characterization. I will not go into details of all this. And all these characterization tell us that it is indeed a polymer, and it is indeed having the functional groups that we expect for an ion storage. We try looking at this as an electrode for the magnesium ion battery. What you see on the screen is on the left is the cyclic voltammogram with this electrode, and you'll see that the magnesium ion reacting with the quinone. It's actually the quinone redox couples is what you're seeing, Q1, Q2, R1, R2. When we use this in an electrode on the right as a battery, see that for about 1,000 cycles, you have fairly stable capacity with a nice Coulombic efficiency. On the bottom, what you see is actually the charge-discharge curve, and this is different from what you normally see for an inorganic system. In an inorganic system, you see a nice plateau, but then you see a slopy discharge curve. This is simply because the process, the mechanism is actually ion coordination. It doesn't follow the kind of Faraday reaction that we normally see in inorganic systems. One try to understand this and use it in an alloy, because magnesium is not very easy to deal with, malleability, but we look at an alloy and then the alloy actually works as well for a fairly large number of cycles with almost the same Coulombic efficiency as that of the pure metal. And anytime we just have a battery, we need to look at what we call as the rate of discharge and charge. This is required simply because any battery needs to be used in a toy as well as in an automobile. So it's important for us to look at the charge discharge characteristics at high rates, and this is at about 3 amp per gram, and you do have a fairly stable capacity that you see, and what you see below is all related to the stability of the electrode material for several thousands of cycles. Now, why is it that it's happening? We try to understand what it is. I did mention that there's something called strain that we have. And strain and contortion, as in inorganic systems, people have started looking at organic systems as well to see if there is a non-planarity that actually gets built in, and if the non-planarity gives rise to certain advantages. And what you see on the screen is some of the general things about the strain or contortion in organic systems. And right now what you see on the screen is in the middle, you have a peroline diamide based system, which does have some contortion or a non-planarity which is introduced. This is based on modeling, of course, 23 degrees. And on either side, you have systems which are planar. Very similar functional groups for ion uptake. So you just see the numbers that are given down, 700 farad versus 100 farad. So this is about 7 times higher than what you have for the planar system. And it's simply because the surface for ion association is quite accessible, the ion diffusion is pretty fast, and there's a reduced pi-pi stacking, which leads to some changes in the polymer molecular mass. So the polymer that I just talked to you about, this is again based on the molecular modeling. So we have about 15-degree contortion. We are in the process of actually finding out what the angle is at this stage. There are possibilities to do it using various spectroscopic techniques, but then we need to keep in mind that this is an amorphous polymer.
Professor, sorry to interrupt. Just 3 minutes left.
Yes. I'm almost done. Yeah, sure.
Thank you.
Yeah, sure. Yeah, I'm almost done. So this polymer does work not just for magnesium, but also works for other metal-ion batteries, and that's what's given here, lithium as well as zinc-ion battery. So now I just go to the last part of it, which will have just 2-3 slides, and I just close it. This is related to molecular assemblies on surfaces. Very often when we make catalysts, electrocatalysts, a molecular electrocatalyst, the catalyst is made and then we make it as an ink and put it on a surface, for example, and try looking at the electrocatalytic properties. But what we are going to say is that depending on how the molecule orients on the surface, the catalytic reaction, both thermodynamics and the kinetics can change. I'll show you one example of it. In this particular case, I'm just taking this cobalt phthalocyanine, and this cobalt phthalocyanine is known to be a very good catalyst for oxygen reduction. And what we are doing is to organize this phthalocyanine on the surface in 2 different ways. You see that it's on silver and gold. On gold, it is quite perpendicular, and on silver, it's more parallel. How is that possible to organize? I mean, there are ways to do it, and there's a spontaneous self-organization with certain diluent that we have, depending on the concentration of the solution that we use to adsorb, it's possible to do something like this. So we do have different orientations which are characterized both quantitatively and otherwise. So on silver, we have a lower concentration, surface concentration, as opposed to gold, what you see on the left. And then the Raman spectroscopy gives information on what kind of angle at which it's actually tilted. And what is the consequence of it? This is a very important thing. A and B see that you have a molecule which is perpendicular and parallel. It's the same molecule. On A, which is perpendicular, the oxygen reduction is actually catalyzed when the potential changes from -0.4 to -0.2. It's only a change in the potential. But you see on the right, it's not just the change in potential, but there is also another peak that comes up. Essentially, oxygen gets reduced to peroxide on gold when it is perpendicular, but it goes from peroxide to water on silver, which means a 2-electron process can go to a 4-electron process just by modifying the organization on the surface. So there's a possibility of controlling the kinetics and also the product distribution by orienting the molecules appropriately on the surface. This is related to the electronic overlap of energy levels, and that can be understood based on a lot of in situ spectroscopy. I think I'll just stop it at this stage and thank you very much for your attention. And if you have any questions, I'll be happy to answer. Thank you very much.
Thank you, Professor Sampath, for indeed wonderful talk. And it's now our duty to honor with gold medal. Honorable Vice Chancellor will be honoring you with prestigious gold medal of the CRS. Kindly accept on our behalf.
Thank you very much. I do accept. Yes, thank you very much. Indeed, an honor.
Honorable Vice Chancellor is honoring you with gold medal. This will reach to your office shortly.
Thank you very much. Thank you very much, sir. It's indeed a pleasure and honor.
This is a medal.
Yeah. Thank you very much. Thank you very much.
This is a shawl for you, and they will all send to your office. We will
Thank-
personally come and honor you. Thank you.
Thank you very much. I'm sorry I could not make it in person. I'm very sorry about it. Thank you very much. Thank you very much. Thank you very much.
So moving ahead, we will now listen to Dr. Shri Thara, MB, from IISc Bangalore. I request CV sir to kindly come and Shashidhar. Okay. Sorry. Yeah. Dr. Shashidhar from NIST. Yeah.
Dr. Sridhar MB is an accomplished material scientist. Sorry, Sridhar. Introduction, the text is something else. I would rather request speaker himself to introduce and then start. Sorry.
Check.
Sincere apologies.
I know, sir. No problem, sir. Slow or pointer is on, but the slides are not. 1 minute. 1 minute. Maybe distance is the problem, huh? Okay. So good morning to one and all. So first let me thank the Chirantan Sanstha for bestowing me the prestigious silver medal. I thank the President, Secretary, all the jury members. It's a great honor and privilege to be here, sir. I also thank the Saurashtra University for all the support and also inviting us to make the presentation on some of the ongoing research activities at our lab. So let me talk on something on small molecule based therapeutics, which is our interest in the last 10 years. So we are basically organic synthesis laboratory or a group, and our major activities fall at the chemistry biology interface. And you can see that some of the activities we precisely work on catalysis, which is mainly the metal catalyst free activation of small molecules. And we also work on process chemistry. We have a major mission projects in the in the process chemistry, enabling the indigenous process intensification or industrial facilitation for the active pharmaceutical ingredients, agrochemicals, as well as specialty chemicals, low volume, high value chemicals. And this right side you can see we work on the that is our major focus fundamental area, wherein we work on the medicinal chemistry from both natural product sources as well as the chemical sources. So this slide is connective to the drug discovery process. We are all aware of that large number of different kinds of molecules have been utilized for the discovery of drugs. It starts from small molecules to nucleic acid to the peptides, enzymes, antibodies, and microbiome stem cells. So if you see that, I mean the molecular complexity or the molecular mass is tremendously impacted on the drug discovery process. Why we are most interested in the small molecules is, see we wanted to catch up on the cell permeability, one of the important parameter in the drug discovery process. As the degree of complexity increases, the molecular mass increases, so the cell permeability decreases. If you want to work on, if you want to balance the cell permeability, so you want to choose a small molecule. That is of our interest. So there are again the pros and cons. I am not going into the other part of the molecules, but our interest is in the small molecules. So by definition, small molecules are low molecular weight compounds capable of modulating the biological systems by interacting with specific targets. And approximately till date, around 60 to 70% of the approved drugs contains a core of a small molecules, and the other properties such as bioavailability, ease of synthesis, and potential for chemical optimization, and then the cost effectiveness of these small molecules make them go-to molecules. Of course, there are the disadvantages also. I am not going to talk about disadvantages. So the legacy of small molecule contains, it starts from a very small molecule like aspirin, and then you have a salvarsan, and then you have a penicillin, you have a tamoxifen, salbutamol, and then the list continues. But in the last 2 decades, people have more or less moved on to the large molecules or the complex molecules due to several reasons. So apart from the small molecules, I just wanted to introduce another terminology called as a multi-targeted directed ligands. So our interest is to choose or design a small molecules and then club another property kind of a multi-targeted directed ligands. Why multi-targeted directed ligands? Unlike the small molecules which have the single target, if you add upon a design strategy wherein different pharmacophores can be added and stitched together, so these multi-targeted directed ligands are capable of modulating a different targets simultaneously at a time. So which is a unhidden kind of a properties, but it is not easy. So by definition again, single molecules designed to act on 2 or more biological targets simultaneously aim to address multifaceted pathophysiological complexes. The major advantages are enhanced efficacy, reduced side effects, lower risk, and cost effectiveness. And why these multi-targeted directed ligands are not focused or not being studied well? The reason is, in every therapeutics we don't need a multi-targeted directed ligands. Mostly we required in a kind of a Alzheimer's or cancer or inflammation where you have a multi-targeted pathways. Fine. So we have a design and we wanted to have a kind of a molecules which have the multi-targeted directed properties. How to make it? One aspect is polypharmacology principle, and you can also try the ligand based designs or structure based designs, and then through the hybridization approach. In this case I have taken 2 examples. One is in the dementia. The other one is in the inflammation. I mean, rather than not expanding to the more than 15 minutes, I'll just finish in 2 examples. So in the dementia, we all know that it is a declines in the cognitive process. Till date, I think it is the 5th leading cause of mortality, and more than 10 million new causes diagnosed every year, and at present 57 million people suffering from globally, and no different case for the India also. India is also having a large number of Alzheimer's patients. So again I mentioned, so in all the diseases are therapeutic targets, we don't need a multi-targeted directed ligands. But whereas in the Alzheimer's, we need this kind of ligands. Why? Because it is a multifaceted problem. It can target through different mechanisms like cholinergic hypothesis, mitochondrial hypothesis, upside uterus, inflammatory hypothesis, and then MAO-B, and etc. So we came up with a design based on the ligand-based approach. The initial starting point is actually taking into the preclinical candidates or the candidates which have failed in the final stage or in the some stage of a process, and then we come up with the design anticipating that it will possess the apoptosis and then have a neuroinflammatory properties along with the ROS or A-beta aggregation properties. So this is the strategy we designed, and I am not going to the design process or synthesis. It is a huge synthesis, and close to some 500 molecules we synthesized, a library of molecules, and then we initiated with the toxicity studies. Once we have a set of molecules in the toxicity studies, we fixed the dose, and with that we started initiating the anti-neuroinflammatory activity along with the TNF-alpha inhibition with the time-dependent efficacy studies as well as with the concentration-dependent manner. So once we have a particular dose, we have identified a hit molecule. From that again we started reinitiating the design process wherein we have a clinical active candidate. From 500 we reach down to the close to 75 molecules, and then I am just showing a one candidate which has the excellent property on par with the or unequal with the standard drugs, which showed like most of the efficacies, and it has also showed the COX-2 efficacy and then NF-kappa B expression in PSC stimulated in both the cells, neuroinflammatory cells as well as in the BV2 cell lines. And we have also extended this, as I mentioned, we have not stopped there, we have from the hit molecule to lead and then from lead to optimized lead. Once we have a lead optimized candidate, we have done all the assays, and then we have also studied its time dependent A-beta aggregation assays and then immunofluorescence assays. I am not going to the details, I am just showing these details. So therefore we could identify a novel triazole derivative which can incline to target a multiple pathological associated with the AD and including the reinformation, A-beta aggregation, etc. So with this we have a preclinical candidate, or I can say a candidate, lead optimized candidate, which has a different efficacy as a multi-targeted efficacy. What we did is we initially filed a patent on this, and then we wanted to see that how it shows the efficacy in the different animal studies, and we did a phase 1 acute toxicity studies, and we also done a phase 2 BBP permeability studies along with the other memory power extension and all. We could see that it has a greater extension of restoration of a memory and a different models of animals, and this has been studied in a more than 1 year experiments and different kinds of animals, and at a different concentrations we can see that it has a strong neuroprotection ratio as well as a improved cell pharmacology, and we have studied its biopharmacological properties by isolating the hippocampus of the brain of these animals. So in conclusion to this particular activity, we have a preclinical candidate or a potential candidate which is non-toxic up to 500 mg per kg, and we has excellent blood-brain barrier permeability, memory restoration, retains the biochemical parameters. So here our future program is actually, we wanted to collaborate with the ICMR labs or go with the BIRAC so that we can do start the phase 1 clinical trials. The second example I want to take in the inflammation. So inflammation is again a prolonged inflammation leads to the genesis of various inflammatory diseases such as Alzheimer's, cancer, and other related issues. We have a present drugs, steroidal and non-steroidal inflammatory drugs. But if you see the history of natural products or history of the drugs, close to 60% of the medicines are basically from the natural product genesis. However, in the last few decades again, we are going towards the AML or bioinformatics and all. We have forgotten our traditional medicine. We have a mission at CSIR NIST where we are actually rebooting kind of things from the traditional medicine. So one such plant molecule or plant material which is our interest. I specifically put this slide because I wanted to show that how traditional knowledge can be synergized with the modern science and technology so that we can bring this knowledge or translate this knowledge into a kind of a product. This particular molecule or a plant may be well aware of. It is called as a mango ginger. In Malayalam it is called as a manga inji, and northeast and then southern part of India is well aware of it. It is used in many culinaries. However, there are some herbal drugs or nutraceuticals, but there is not much science behind this. But why this is actually used or what is the chemistry behind this? So what we did is we have screened almost close to 40 molecules from this mango ginger, and we have isolated all the molecules and we have subjected for different kinds of assays. I am not going into the details. For example, I am just showing one aspect like NF-kappa B signaling pathway, which is very important in the anti-inflammatory pathways, by studying a nitric oxide synthase, cytokines like TNF-alpha, interleukins, COX-2 inhibition, inos, etc. When we studied this, one of the molecule from that particular ginger got our interest. So that molecule is a dialdehyde. This is the particular molecule. In the drug discovery principles, when you have a molecule with a moderate activity, if it has a more than 2 to 3% of in a particular 1 kilo or 2 to 3%, which can be qualified for the drug discovery process, or it can be considered as a clinical candidate. So what we did is we utilized this molecule. You can see the numbers. So initially this is a parent molecule which is isolated from the curcuma ginger as such. It has a 2 to 3% in a total 1 kilo. So it shows a nitric oxide inhibition, which is a parameter to evaluate the anti-inflammatory properties, and these are the two interleukins are the TNF-alpha, which shows a 30% to 23%. See, what we did is, I am not going to the deep details. We designed a molecule and then we come up with a synthesis, library of molecules have been synthesized, and finally we had a transformed that natural product into a kind of a lead candidate which shows improved activity from 16 micromolar activity to 3 micromolar activity, and then your interleukins and then TNF-alpha also improved more than 2 folds. So we did not stop there. We wanted to bring it to the nanomolar range, and what we did is, I'll finish. Done. So then we again modified that, and then again we did a kind of a swapping the molecules and then introducing a clinical candidates into that, and we have finally a candidate which has a nitric oxide inhibition of 1.46 and then interleukins and then TNF-alpha reduction almost 3 folds increased from the parent molecule. So this we are considering now as a preclinical candidate, and we are moving ahead with the animal studies. So this is actually how we did it. This is how the slides goes on. I'm not presenting the data. I'll just go to the last slide. Yeah. So similar way, I just told 2 stories. So we have several stories. So we have different molecules or different targeted therapies with a different multi-targeted associated molecules. We have built a different kind of a molecular library which shows with a simple indoles we can have a large number of preclinical candidates. We have more than 7 patents in this area, and we have taken up for the preclinical candidates. Many molecules we have taken for with industrial support. These are some of the products. Apart from our fundamental science, we also do a lot of technology driven research. I am showing here. We have an indigenous process for technology for specialty chemicals. We have transferred it to the press bureau, and then as well as the for the anti-counterfeiting technologies, we also have the industrially viable processes for several dyes. We have a one-pot process for the nitazoxanide drug, which is antiviral SARS-CoV-2. We have a multiple grants in the recent times, and we have a process technology for the very active fraction of a plant molecule. I am not disclosing. We have a which has a property of rheumatoid arthritis, and we have a several products, and we have transferred these to several industries. So I'll stop here. I thank once again my team, my students, and all the funding agencies, my director, my collaborators, and finally CRS as well as Saurashtra for giving this opportunity. Thank you.
Thank you so much. And now we'll have a short tea break and we'll regather after 10 to 15 minutes.
Thanks to Dr. Shashidhara who spoke, before me, for giving me a very good segue into this topic, drug discovery and development. So what I will do is that before I venture into what my company is doing, I just would like to take you through in 2 minutes what drug discovery and development all about. So I understand this is a very diverse audience. So just for everyone's benefit, I think it is not. Oh yeah. So essentially, if you look at the drug discovery and discovery to commercial or market continuum, it starts with the discovery, which is early, which comprises early discovery and late discovery. Early discovery is all about the disease biology, the target identification, and how the disease is forming. Essentially, most of the time it is an overexpression or an overproduction of an enzyme or a protein, and there the focus is more on understanding the protein and how we can bind that protein with a chemical molecule or a therapeutic agent, investigational therapeutic agent. That is the focus there. And then when we come to the late discovery, it's all identifying a lead and a lead optimization, and then comes to the preclinical phase where it's all about understanding the toxicity of the molecule. Essentially, as we speak, the current standard is animal testing, and it's also called a phase 0 or an IND enabling studies. And then the next phase is the phase 1, one of the most important phases in the journey of a drug molecule. So prior to phase 1, there is a filing called IND, investigative new drug application. So once that is approved, the phase 1 or the first in human trials can be conducted. Up until 2023, one of the mandate or the mandatory requirements was that no molecule can enter into a human for the first time without an animal testing through 2 different species: small animals, rat, rabbits, gerbils, hamsters, and the large animals, mostly non-human primates and dogs. So in 2023, the regulators have changed that rule, and I'll tell you why they have changed and where we found an opportunity. So after the phase 1 is a dose ranging or dose escalation study and on healthy volunteers, and phase 2 is an extended phase 1 study, and phase 3 is where the molecule first time sees a patient, unless it's a cancer medicine. I mean, in oncology, the phase 1 and phase 2, all of them are done on actual patients. Otherwise, phase 1 and phase 2 are typically on healthy volunteers, and phase 3 is where the actual patients are participating in the clinical trial. And most of the time, it will be tested against a placebo or with the current standard of treatment. And then phase 4, there is an NDA filing, new drug application filing. And once the NDA filing is approved, you have a commercial drug which gets into phase 4, which is a post-marketing surveillance testing. So this is in a nutshell, what I just mentioned in the last 3 or 4 minutes happens over 12 to 15 years, and the cost associated with is about 2 to 3 billion, and with 0.1% success from here to here. This is the biggest challenge in the drug discovery and development. So $2 billion in rupee terms, it's about 20,000 crore rupees, and any molecule which fails in later part of the continuum is a bigger loss, right? So what we are focusing now is that we found that the animal testing, which is considered as the gold standard even today, is not very human relevant. 90% of the molecule which pass through the animal testing later fail in one of those clinical phases. So the reason is that we assume that animal biology is a good proxy for human biology, but it is not. It has only 10% relevance. And also, if you look at the new, the current direction of drug discovery and development, I think Professor Shashidhara mentioned that 60 to 70% of the molecules are in the therapies are in the small molecule, but that's changing very fast. If you look at 20 years ago, the product portfolio of any large pharmaceutical companies, mostly it would have been completely small molecules, but today some of them have 50-50. That's why you see, the from 100% it has come down to 60% or so. It's fast, moving. The reason is that the druggable targets in our human body is fast depleting, or we are not able to identify new druggable proteins in human body. That is a challenge. So scientists are looking into alternatives. The novel modalities are biologics, immunotherapy, cell and gene therapy essentially, oligonucleotides, antibody drug conjugates, and therapies like that. Now, if you look at any of these therapies, more so biologics or an immunogen, if you inject to an animal, animals are going to, most of them will die, because it is specific to human, right? So now if you use animal testing as a mandatory requirement in the value chain, you can see that lot of novel therapies would have been faced early attrition in this space. That is where regulators are aware. They have changed the mandatory requirement. So we found that opportunity there, and how can we bring in a more human relevant methodology here? And unlike other artificial intelligence based companies, we wanted to start from here, because this is where the maximum value attrition happens. Because think of a situation, someone put a lot of money and time, that is about 4 to 6 years, and come to a preclinical stage and the molecule fails because we are using a non-relevant methodology. So essentially, yeah, this is the problem I was referring to. So the discovery AI has improved. The discovery process has improved through AI/ML means, but the translation has not. So we are coming from in the reverse order. So coming from the translational aspects, preclinical to phase 1, and coming in the reverse order. So essentially, yeah. So as I mentioned, we are developing an artificial intelligence and machine learning based alternatives to animal testing. Our mission is to remove the animal testing entirely from the drug discovery value chain. So how do we do that? We have developed algorithm which are essentially biological plausibility constrained generative algorithm, and the mechanistic explainability is the true feature of this algorithm. So later I will show you where are we today. So if you look at the current large language models, they are not deterministic. So we are moving away from that. We have actually a prototype where it's based on large language models, open source large language models, and trained on regulatory aligned data sets. With that model, it can actually predict hepatotoxicity, which is our anger use case. Today, if you give a known molecule, I'll show you some of the examples later. It will tell what mechanism it will trigger in the human body, and whether it is toxic or not, and what structural changes you need to make so that the toxicity can come down. All those things today it can do, but the moment we give a novel molecule, it will hallucinate, it will fail. So what we are trying to do is that is because of multiple reasons. One is large language models are not good for this kind of deterministic tools, and they need millions of data points. You can imagine that in one's lifetime, we cannot generate millions of laboratory data points by one company or one person or a group of people. So what we are doing is that we are doing two things differently. One is we are moving away from large language models, and we are using algorithms which require fewer data sets, which can study human biology much better than large language model. That is one thing. Second thing is that we are also doing our own experiments on organoids, the organ on a chip, and even that data is not sufficient. 500,000 data we generate in a 6 months or 7 months is not sufficient for an algorithm to learn. So we augment that data through our own algorithm. So essentially we are using our proprietary algorithm and proprietary data sets. When that training happens, we'll get a lot more reliable engine. So essentially we are developing building a defensible deep tech. We have already filed 7 patents. These patents are all around novel architecture for toxicology prediction, systems biology, therapeutic strategy, and these are the areas where we have, and a few more are still in the pipeline. So as I mentioned, what we have built is that a working hepatotoxicity predictor demonstrated on known hepatotoxins. And due to paucity of time, I am not going to the, otherwise there is a video which actually demonstrate what it can do. So the mechanistic pathway attribution is extremely important for regulatory alignments. Regulators are not going to accept just because we have developed a new tool which is more human relevant, all those things they are not going to accept. So they will look into what mechanistic pathway attribution or why a molecule is toxic. So if you look at the today's most of the prediction tools, those are all black box prediction tools. So it looks at the structure. Yes, if a structure is toxic, a similar structure is also toxic. That's how it's being done. But we are not stopping there. What we do is that we try to understand if a structure is toxic, what mechanism it is triggering. Is it immunogenic? Is it mitochondrial dysfunction, or is it metabolite pathway? And that information is given to algorithm. So essentially, in a nutshell, if you ask me, what we are doing is that we are teaching human liver biology to algorithm. That's what we are doing. So that when a new molecule is given to the algorithm, it will say that it triggers this mechanism. So hence it will fail. So if you look at, this is our the current functional prototype. If you just put the diclofenac into our model, what it says is that it says there is a long-term or a chronic hepatotoxicity associated with this molecule, right? And it also says that, I'm not sure whether you are able to see this, but what it says is that the mechanistic insights, what mechanism it kicks in. So it says reactive metabolite, immune activation, and mitochondrial dysfunction. These are the dominant mechanism through which this molecule, can fail liver. But what is important for a medicinal chemist is this. If you look at here, the halogen is replaced by a fluoro. You can get about, this is actually 15% toxicity reduction. This is another derivative which is about 20% risk reduction. So this is where we are moving into. So this is again, So this is again on known molecules and based on open source architecture and data sets. So our effort is to, or what we are developing now is our own proprietary algorithm, proprietary data sets which can predict the toxicity, liver toxicity associated with novel molecules, and give a structural alert for medicinal chemists to come up with a new variant, all through algorithm. Essentially we are planning to replace animal biology with algorithm. I think that's it.
He is from a pharmaceutical company, drug discovery. His contributions are phenomenal. If you go to his website, artificial intelligence is associating with the drug discovery. He has done a phenomenal job. In one of the conferences, we identified his company and his worthiness. So therefore, we proposed, CRS approached him, why don't we honor with this kind of award? He accepted. Now we are honoring him with a very prestigious partnership award to Professor Thampi. Dr. Thampi, sorry. Yeah.
Now, any AI related, you can consult him. Actually, my mail ID is there. If any more information or get in touch, please do so. There are so many people who are looking at dress. You can have. Thank you so much.
All right, we are moving to the next speaker. It's my great pleasure to invite now Professor Sanjeev K. Patra. He is a distinguished chemist and professor in the Department of Chemistry, IIT Kharagpur, and renowned for his pioneering contribution in the organometallic chemistry, inorganic chemistry, sustainable catalyst, polymer chemistry, and functional material. His innovative research has advanced the design and organometallic system and functional polymer for catalytical and material applications. Following his doctoral studies at IIT Kanpur, he got prestigious postdoctoral research at the University of Bristol, Royal Society, and he is also awarded the Mercury Fellowship. He has established international recognized research program with over 65 high impact research publications. He has made significant contribution to the interdisciplinary and chemical science, and we feel extremely proud to present him on this dais. Sir, welcome, and now stage is yours. Thank you.
Thank you. Firstly, thank you, the CRS, for honoring me with a silver medal, and the organizer for giving a nice hospitality, and it's a fantastic university campus. It's so big. It's really nice. So I'll talk today about our recent development of ruthenium iron-based bimetallic catalysts for achieving the redox-assisted polymerations. Just to inform, just to share. Okay. Huh? Oh, okay, this. On है तो. वो तो चालू है लेकिन नहीं हो रहा है ना. नहीं वो मुश्किल होगा, थोड़ा एनिमेशन है अगर. मुझे ही करना पड़ेगा. हो रहा है वो? चालू है. वो भी तो नहीं हो रहा है ना, मैनुअली हो रहा है. हाँ देखो एक बार. हाँ ये हो रहा है, अभी हो रहा है, अभी हो रहा है. Okay. Note this 2 minutes. Okay, so just to share that our institute is celebrating the 75 years of excellency, and through the different ways you see. In our lab, at IIT Kharagpur, you would mostly work on functional organometallic compounds. You see the wire-like metal organometallic conjugates, side chain metallopolymers, different type of self-assembled materials, and also the designing catalyst which will be sustainable. So today I'll work on this one, and then I'll try to amalgam with these applications. I just emphasize about what are the polymerization, mostly the control polymerization. As you know that this is the steps of free radical polymerization where the controlling of the chain length is very difficult due to the several unwanted reactions like chain transfer, chain terminations. So how to make the ERP to CRP? So as you see, this is a very well known, as many of you know probably, that we like this one, okay, not this one or this one, okay, because you can control your chain length and other well-defined, make the well-defined polymers. So how to make the FRP to CRP? FRP means free radical polymerization, CRP means control radical polymerization, with the concept of the persistent radical effect and the strategy to make a dormant species. Dormant species is basically to make the highly reactive radicals species to a little bit moderately reactive species. So this is the dormant species, this is the persistent radical, this is with a high lifetime radical, and this is the transient radicals. So there are several methods to make the free radical to a control radical polymerization, and these are the like NMP, ATRP, and the RAFT you probably know. And one thing is very common. The common is that through a dormant species everywhere. Okay, in our group we are interested on ATRP, where you use a redox couple, okay, metal containing redox couple to make the dormant species. We emphasized, we tried to make a yard stable and sustainable catalyst. Before that, I want to mention that if you use this ruthenium based catalyst, you also need a reducing agent, and mostly the ferrocin is used. But whatever the reported methods you see by Swamoto, mostly so by Swamoto, you see that you need a very excess reducing agents, and we don't want any unwanted reactive species in the reaction chamber. So what we thought, let's try a challenge, take a ruthenium center which is easy to prepare, and also take with triphenyl moieties, and also take a ferrocin which is conjugated, and make this catalysis truly a catalytic, not stoichiometric. So with this one, okay, we designed one, and you see that ruthenium tarpedine is not a good catalyst. Ferrocin is not a good catalyst. However, this is used as to induce the chirality. Okay, that is the different, but it does not participate in the reaction. But with this challenge, let's try to, when you conjugate, bind to bad people, how it will become a good people. This is very kind of a reverse philosophy. Okay, so let's see. So we know that good is always good. Good, bad, maybe good or maybe bad. But what the two bad things? Let's see. Okay, how it happens. So we try synthesize the ligands. I am not discussing in detail. And use this. This is the phosphonium. Okay, this is our prime starting materials. And if you can make very nicely by two methods, through route A or route B. The route B is much better. So basically you see the phosphonium and then elide salt, and then you couple with the ferrocinaldehyde, and you will get a nice product of this one, which is our catalyst. So all we are characterized by all various methods, including single crystal XRD and others. And you see the redox properties of these two complex. You see this is corresponding to ruthenium, and this is corresponding to iron. And we need this difference. Why? Because if the ruthenium 3 couple must be reduced by the ferrocin, so that the ruthenium 3 becomes ruthenium 2 again in the catalysis. So that with that philosophy, we started the polymerization, and we saw it's really nice in the ATRP protocol. You will see that nice polymerization. We started with a simple monomer, okay, methylchloride, and you will see that nice polymerations in the normal conditions. And many of the monomers are nicely polymerizing with a fantastic PDI, polydispersity index, ranging from 1.1 to 1.2. We characterized by NMR, by GPC. I am not going to discuss in detail, but yeah, people will ask question whether your bimetallic is really necessary, or if we take a monometallic congeners, those are effective or not. So what we do to convince, we made the monometallic congeners, and we saw that yes, this bimetallic actually outperforms all by monometallic congeners. Okay, and yeah, we did all this possible characterization as polymer chemist we do generally. This is a tetradetector GPC chromatogram, and you see that we varied all the monomer initiator ratio, we varied the time, and we saw that this is a really nice living polymerization. Okay, how the molecular weight can be nicely tuned. Even we got the very high molecular weight polymer. You will see that almost 3 lakhs Dalton. Okay, so that is really very nice. However, to make the polymer functional, we have to make the copolymers, as it is a living, so it actually offered to make the copolymers, and you will see that if you stepwise, if you do the polymers of different monomers, you this also able to do the give the copolymers. So that is really nice. And after that, we try to understand in more detail how this our catalyst is affected, how it is being operated. So we did a lot of control reactions. Here you will see that this is a this is the you see that where ruthenium 2 is becoming ruthenium 3 by taking this bromide, okay, and that by cleaving this bromide and becomes ruthenium 3, and then it becomes again there is the electron transfer between the ruthenium 3 and iron 2, and it becomes iron 3, and then again it takes the halogen cap from this one, and then again it becomes the iron 2 and ruthenium 2. Okay, so we have proved by DFT, by EPR, by mass spectrometry, and we propose this mechanism as I discussed in a very brief. In the last slide, I am not going in detail. We also try to understand what will happen if we change the ferrocene moiety. So for that we systematically, judiciously designed our catalyst in a such a way that this ferrocene moiety is varied, and we try to understand what is the redox, what is the electronic factor will be varied if I change the position. And you will see that we made all these kind of 3 type of bimetallic complexes, and we saw that this one, the HBC3, where your ferrocene moiety is directly attached with the terpidyl, this called the 4' position, and you will see that this is the most effective. So this is the, you see that this is the most effective one, HBC3. So we became very happy, and we tried to make with this HBC3 different type of polymers, copolymers, and the tuning of the tuning of the molecular weight is really nice. Okay, and we proved. So after that, we thought to how to make this polymerization is most sustainable, and whether it is possible in presence of air or in presence of oxygen. So with that, we incorporated not only the thermal stimuli, we also applied the photopolymerization. What I will not discuss in too much, as I wanted to show that this is also fantastic, this catalyst, if you do try to the oxygen tolerant ATRP, which is very fascinating and more applicable to make the polymers in a very ambient condition. So after that, that was the our main motto, that how this catalyst can be applied to more functional monomers. The acrylate and others, those are very easy. But if I want to induce the functionality in the polymer, I have to take a functional monomers, and often these kind of monomers are not compatible with this kind of metallocomplex catalysts. However, in our system we saw that all these kind of monomers which have a n-heterocyclic, that is the appended ligating sites, are really nice and give a well-defined polymers, one of the representative GPC you see here. And I am coming, why I am doing this one, okay? So what I'll try to show you, okay, that why we are interested to make, to develop this kind of catalysts for what kind of smart applications we are growing and what kind of polymers we need. So we actually, as I told that we are developing a catalyst which are compatible with more functional growth, especially with the polymers having the ligated coordination sites. So you will see that these polymers were made through this method, our catalyst, and you see that this kind of polymers, and this polymer, when I tried to do a self-fillable polymer, this was a partially self-fillable, but when I put the zinc, you see that this is really healed within 12 hours. On many polymers are also in less time. So this is really fascinating. So these same polymers have been made, similar polymers have been made with our methodology, and which is compatible with this kind of a N heterocyclic ligands, and you see that this polymer completely healed within a 6 hour in presence of Zinc 2+. I'm not going in detail about how the self-healing mechanism, why the choice of Zinc 2+, how does it happen. I just wanted to show that how indigenous catalyst in our lab can give a functional smart polymers. So this is amazing. This polymer as a room temperature self-healing, you will see that similar polymers have been synthesized by our catalyst, and I will give another very fascinating example. So similar, this polymer was synthesized by our catalyst, and you will see that this kind of polymers are amazingly give the safe memory properties. You will see heat it, come to the ambient temperature, and then again you see that you are getting the same safe. Okay, so in summary, what we did, we developed a excellent candidates of bimetallic catalyst which are compatible with many functional and more complex monomers in ATRP type polymerations. We also made the simple catalyst, bench stable iron 3 based catalyst, which can also give the photopolymerization, and we published this paper as a cover picture in last year. And the most of the work is done by Shoman Doloi, who just completed a PhD, and they are also following the similar kind of extension work. And this is my group, and thanks to the various funding agencies to carry out and to support our work. And thank you very much for the excellent performance.
Our next speaker, silver medal awardee, Dr. D.P. Hari. Dr. D.P. Hari is distinguished organic chemist and assistant professor in the Department of Organic Chemistry, Indian Institute of Science, Bangalore, recognized for his pioneering contribution to synthetic organic chemistry and sustainable catalysis, following doctor and postdoctoral research at the University of Regensburg, EPFL, and the University of Bristol as a Marie Curie Fellow. He has established an internationally admired research program at IISc, a recipient of the Dr. Rajgopalam Research Excellence Award, INSA Young Associate Award, Thyme Chemistry Journal Award, Infosys Young Investigator Award, and the IISc Award for Excellence in Teaching. He exemplifies excellence in research and education.
Yes, it came. Can I put this on?
Yes, sir. Okay.
15 minutes.
Yeah.
30.
15 minutes I'll finish. Yeah, I think so.
Next is
It is on.
One click is on. So this is my time. One second.
Yes. Okay. Shall we start? Can we start?
Okay. Can start? Hello, good morning everyone. And first of all, I would like to thank CRS and Saurashtra University for giving me this wonderful opportunity to present our research work. So before going to talk about this particular topic, I would like to give you a brief overview of the research themes that we are carrying out in our group. So we are particularly interested in utilizing the ring strain that present in the small molecule to access medicinally relevant compounds at ambient conditions. So we are also interested in either selective generation of a singlet carbene or a triplet carbene and controlling their subsequent reactivity for chemical synthesis. So the tools that we use to drive these transformations are mainly light and electricity, but when we need these compounds with high energy purity and stereoselectivity, we are also interested in developing metal catalyzed transformations. So today I am going to show you our recent contribution to the strain chemistry under photo and electrochemistry, and especially utilizing the radical polar crossover strategies. So that brings me to the first question: what is a radical polar crossover? So let's start with a compound which has a leaving group. So when you use an oxidation or a reduction, and you will get a radical intermediate. Now this radical intermediate can undergo for further oxidation to give you a carbocation, and this carbocation can be trapped with a nucleophile and you get this compound. If you look at the starting material and the product, both are neutral compounds, but during the mechanism it is going through a radical and a carbocation. You know, it is crossing a pathway. It is from the radical to the polar pathway, so that's why we call it as a radical polar crossover. So then the next question is that how do we get this radical polar crossover pathways? So you can use a photoredox catalysis. So let's start with a photocatalyst. So when you shine the light on the photocatalyst, it gets excited. In the excited state, it transfers a single electron to this carbon iodine bond and form a radical intermediate. So the photocatalyst now give an electron, right? So in order to close the catalytic cycle, it has to take the electron back. So when it takes the electron back, it becomes a radical to carbocation and you close the photocatalytic cycle. You can see that here you have a radical intermediate and which form to the carbocation, then you get this radical polar crossover. So this can be also achieved under electrochemistry, as we all know the cold-bay electrolysis, where you start from a carboxylic acid that undergo decarboxylation to give you a radical. Now this radical undergo further oxidation to give you a carbocation. So again you can access a radical and a carbocation. That's why we say radical polar crossover. So we use this strategy to develop fundamentally new transformations in chemical synthesis. Today I am going to show you 3 stories. In my first story I will show you how we use this strategy to access medium-sized carbocyclic compounds. In the second story I will show you switching from a photochemistry to electrochemistry. Instead of ring expansion, we are able to open the ring. And then I will finish my presentation by showing you how we combine the ring strain of a bicyclobutane with a radical polar crossover strategy to access oxa or aza bicycloheptane derivatives. So let me start with the first part, the why medium-sized carbocycles. So when you look into the literature, there are many compounds of medium-sized ring which has the beta hydroxy or gamma hydroxy ketone or the corresponding diols are very important structural motifs in organic chemistry because they present in wide range of complex natural products. It shows the broad spectrum of biological activities. So as a synthetic chemist, you are interested in synthesizing such a privileged compounds. So when you look into the textbook, and you see that there are so many methods developed for a 5-member ring or a 6-member ring because we have a Diels order reaction, so you can access. But when you look into the textbook, there are less methods developed for the larger size rings. The reason is that if you want to bring the 2 ends of the large compound, it's always challenging to bring because they have so many conformational effects. That's why there is a challenge in synthesizing a medium-sized carbocyclic compounds. As you can see here, this graph tells it's easy to synthesize a 5-member ring, but when the rings are going, the size increasing, it's quite challenging to access the medium-sized ring. So then how do we, address this problem? So one solution is that, let's say if you wanted to close
to access the 8-member ring in a end-to-end cyclization. This is in higher in activation energy. You can go in a 2-step process where you first close the 5-member ring, which is kinetically favorable, then you open to 8-member ring. So in this way, and this is like 1 step, 2 processes, but you can get access to the medium-sized ring. Such kind of a reaction is called a Dawat-Beckworth reaction. So what is this Dawat-Beckworth reaction? It starts with a beta halo compound, and under radical initiation, and you get the methyl radical. Now this methyl radical adds to the carbonyl, and you form a cyclopropyloxy radical, which is a highly ring strain. So this undergo ring expansion to give you see, you start with a 6-member ring and you end up with a 7-member ring here. So that takes the hydrogen atom. So this strategy used in the total synthesis of many natural products, and as you can see, some of them I drawn here. But when I started my independent career 4 years ago, so we thought, can we improve the chemical space of this reaction? Because often this reaction, the radical takes the hydrogen atom, and that is not a very good functional group. So then how do we functionalize that? So we wanted to utilize the nucleophiles to functionalize the radical, but as you all know, the nucleophiles cannot be used for functionalization of radicals. You need a carbocation. So that's where the radical polar crossover comes. We want to convert that radical to carbocation and followed by trapping with a nucleophile to access the desired compound. So with that, our initial aim was how to access this kind of a carbocation. So here is our reaction design. So we want to start with a photocatalyst, and it gets excited. In the excited state, it transfers a single electron to the carbon iodine bond, and you form this methyl radical. Now as I mentioned in a Dawat-Beckworth reaction, this methyl radical adds to the carbonyl followed by ring expansion, give you the tertiary radical. Now we have to close the photocatalytic cycle. In order to close the photocatalytic cycle, you need to donate an electron to the oxidized form of the photocatalyst. Now the radical donates 1 electron and close the photocatalytic cycle, and you form a carbocation that trapped with a nucleophile, and you get the desired product. So with this reaction design, we developed this, and I'm not going to talk about the optimization details, but it works with different ring sizes. You can go from a 6-member to 7, 7 to 8, 8 to 9, and you don't have to use only alcohol as a nucleophiles. You can use amines, or you can also use a carbon nucleophile. Okay, the next question. Can I insert more than 1 carbon at a time? Because so far we are going from a 6 to 7. Can I go a 3-carbon extension in a single step? So here is what we did. So we start from a 4-member ring, but outside we have a 3-member chain. Can we bring this 3 carbon inside the 4-member ring so that you will get directly a 7-member ring followed by functionalization? So with that, you can see that it also works very well with the different types of nucleophiles, and you can also use a fluoride as a nucleophile. So that brings me to the second story, where we use electrochemistry to deconstruct the cyclic compounds. And these deconstructive functionalizations are very important because often in the medicinal chemistry there is a concept called scaffold hopping. That means you take a known drug molecule and you try to deconstruct the central core of the molecule and to test it for the same activity. Often it shows the better activity, so we are interested in such kind of a deconstructive functionalization. And not only that, as a synthetic chemist, controlling the stereochemistry in a acyclic compounds is highly challenging, but controlling in the stereochemistry in a cyclic compounds, let's say Diels-Alder reaction, it's very easy. So what we are interested in that, can we first construct a cyclic compound and then deconstruct it into the acyclic compound and preserve the stereochemistry of it. So with that we started this. So our reaction design is that, just a minute ago I told you the Dawat-Beckworth reaction, how we convert this radical to carbocation and then trap with a nucleophile. Now we want to deconstruct the ring by interrupting this reaction. What I mean by interruption, because we wanted to stop this ring expansion here. So how do we stop? So start from a carboxylic acid here, you got a primary radical. Now this radical has 2 possibilities. One, it can add to the carbonyl group and follow the upper path, or if you can quickly oxidize this radical to carbocation, and you can get access to this kind of a primary carbocation. At this stage, the lone pair of the oxygen will push and you will see kind of a Grob type fragmentation, and you will form the acylium ion. So acylium ion is a very good electrophile. You can trap with a nucleophile
and you can get access to this kind of a acyclic compound. If you look at the overall transformation, you start with a cyclic compound and you completely opened up and you get an acyclic compound. So with that, so we did the scope of this reaction. As you can see here, you can use the 7-membered ring and you can open up to the acyclic compound. You can also use the large ketones. Still you can open up the the ketones to access the long alkyl chains. So here is my favorite example. You start with the naturally occurring ketones where the stereochemistry is already present, and you can open up and preserve the stereochemistry of the two centers. And again, you can start with this another natural product, that is a 2-zone, which you can again deconstruct it and access the cyclopropane with a 3 chiral center. Such kind of compounds are challenging to access using traditional methods. So that brings me to my final part, where I'm going to show you how we combine the ring strain of the bicyclic butane with the radical polar crossover to get the unified access to oxa or aza bicycloheptanes. Pyridine is very important in drug discovery, but the pyridine has a pi bonds. Under oxidative conditions, it undergoes decomposition. So therefore, we need a 3D bioesters of pyridine, such as a aza bicycloheptane. So which is a 3D bioester of benzene, and it improves the metabolic stability and also improves the drug-like properties. So here is one case study, a drug called ropatidine, which has a pyridine core here, and when you replace this pyridine core with a 3D bioester here, you can see that the half-life improved 10 times. So that's why now the medicinal chemists are interested in accessing such kind of a 3D bioesters. So we are also want to contribute to this area, starting from this photochemistry, exciting the photocatalyst here, and here we are using a bifunctional reagent which has a leaving group. So you reduce the bifunctional reagent, you form a radical and a leaving group as a Lg minus. Now this radical adds to this bicyclobutane the middle bond, which is highly strained. Now when this radical adds to the middle bond and you open the strained bond, you access the tertiary radical. It's the same radical polar crossover strategy now. Now this tertiary radical will give an electron to the oxidized form of the photocatalyst to close the photocatalytic cycle, and you form the carbocation. Now you have the carbocation, and you also have the intramolecularly nucleophile, which is a tethered nucleophile, and that will add to the carbocation. You cyclize the system to access such kind of a aza or oxa bicycloheptane, depends on whether your nucleophile is oxygen or the nitrogen. So with this strategy, starting from the beta amino acid derivatives, we are able to access aza bicycloheptanes. The scope of the reaction is remarkable. You can access variety of the systems using beta amino acids, and cyclopropanes, which are sensitive to radical chemistry, also tolerated this reaction. And you can access the bispyro or monospyro compounds, and most importantly, you can access the fused compounds. You all know that amino acids are chiral. When you start with a chiral enantiomer amino acids, you can get your compounds also in a chiral enantiomer form with 100% enantio selectivity. As I said, that depends on your nucleophile, you can access a different oxa bicycloheptanes. So when we start from a beta hydroxy derivatives, we are able to access the oxa bicycloheptanes. As you can see here, a large variety of oxa bicycloheptane derivatives is synthesized, and we are also able to access the spyro compound. And when we start with the chiral enantiomer alpha hydroxy acids, we are able to get the compounds with 100% enantio selectivity. So with that, so I want to summarize my presentation. So what I showed you in the last 13 minutes, that the radical polar crossover is a powerful strategy, and I demonstrated 3 examples. In the first example, I showed you how we are able to do the ring expansion by combining the photochemistry and radical polar crossover. In the second example, when we replace the photochemistry with an electrochemistry, we are able to deconstruct the ring. And in the final part, I showed you how we combine the ring strain of bicyclobutane with the radical polar crossover to access a unified strategy to either oxa or aza bicycloheptane derivatives. So with that, so I would like to thank my research group and of course IISc for funding and ANRF and Infosys. And again, once again, thanks to CRS and of course also Saurashtra University for arranging this talk. And with that, I would like to thank all of you. And if you have any questions, I would be happy to take. Thank you very much.
Wonderful. As expected.
Give him one more big round of applause. He is awardee. As you know, he has presented so well, and as we, CRS members, being probably we are the organic chemists, we understand his work, and we have seen the kind of work he has done. The whole CRS, members, kind of appreciated your work. So they immediately said yes. Okay. So referees' reports were very good, and you have done a phenomenal job. Continue to do it. In this aspect, CRS proposes or it honors you with its prestigious silver award. Yeah. Many congratulations. No, let him sit. Okay. No, his chair is there. Other side it is there.
You have come like a Madhumaka, Big round of applause, please. This is go to press. Go to smile. Very good. There is one more honor from the opposite side. Oh, this you are here only. Keep doing good work, okay?
Next speaker, Silver Medal awardee, Dr. Sridhara MB. Dr. Sridhara MB is an accomplished material scientist, was pioneering research in two-dimensional layer materials, inorganic nanotubes, fullerenes and solid-state materials, has significantly advanced modern material chemistry. After earning his PhD from the Jawaharlal Nehru Center of Advanced Scientific Research and completing postdoctoral research at the Weizmann Institute of Science, Israel, he has established himself as a promising researcher in nanomaterials and structural material science, a recipient of the Best Doctoral Award, an editorial board member of Inorganic Chemistry Communication, and a University of Gold medalist. He has made impactful contribution to advanced material research.
Thank you very much for the nice introduction. I personally thank CRS and Saurashtra University to giving me this wonderful opportunity to talk something what we are doing in Indian Institute of Science after having our lab. So before going that, I briefly tell you what we what is our research focus on. Okay, sorry. So we work on 2D materials. Okay, for some of you who don't know what is 2D material, you have usually your pencil lead, right? As a students, whenever you draw in pencil line, you continuously exporting a layer of graphite. So graphite is one of the best example for 2D material. So the beauty of graphite, it can roll into 1D nanotubes. So these are all class of material which are belongs to this 2D. Their layers are stacked vertically like this. The beauty of them is, other than 3D, you can really roll them into make into one-dimensional nanotube. And all of you know, when you make it 2D into 1D, there will be a dimensionality effect which comes in picture, and it drives the some other different properties. So we focus on this 2D and 1D infrastructure in our group. We also grow 1D topological nanomaterials, okay, using catalytic assisted CVD. And we try to see what happens to this reaction at nanoscales. Okay, we use electron microscopy to see how this reaction proceeds, how we can really have a very interesting compounds, and we try to look at their property driven by geometry. So in this particular talk, I would like to explain why really 2D materials form one-dimensional nanotubes. Okay, and I will explain some of the interesting compound, what are these misfit layered compounds and why they form nanotubes. And I will show some of the charge transfer properties and charge density waves in these materials. Okay, with this I explain really recently we come across some of the very interesting stuff. When you replace sulfur by selenium in this nanotube, they selectively goes in particular ordering. And I will explain this, and with summary I will go forward. So to tell you a simple story, the graphite discovered almost a century ago. 1916 graphite discovered, and 2004 it was really opened up a plethora of opportunities. See, this is a single layer graphene. You can see these, each one are carbon atoms. They are hexagonally packed. You can see this is the armchair edge of the graphene, and you can really see them atom by atom today in microscopy. And further on these, so there are two-dimensional materials which are like MOS2 and WS2, and they become very, very interesting, because when you have a two-dimensional material which are stacked many layers, this shows an indirect band gap. When you explore to monolayer, it shows a direct band gap. To give a direct example why it is very interesting, if you have a monolayer, it can act as a LED, right? It gives you photoluminescence, where indirect band gap does not give. So you can have a thinnest LED strip of a material, so when you have a monolayers. So this is very interesting compound. You can see when you come to monolayer, it becomes a very nice photoluminescence. When it's bilayer, it does not give you photoluminescence. So these are quantum size effects, leads to a very interesting properties. So when I was doing PhD, something I observed in similar fashion. When I start growing material, everybody starts seeing the product first, right? Like they think, okay, I have designed some reaction, let me see the product. So by seeing what's going on is most important according to me. So when I seeing like growing a small nanostructure, you see these edges are curves always. You see these are the 2D material, you see this edge is curving, this is carbon nanostructure, the edges are curving. This is a bulk structure, a gallium sulfide, you just exfoliate it on a like a flake, and you just give it some heat, it will curves. Why this happens? This is at nanoscale what we are talking. That means something is happening that like in the edges. So to understand that, we ask a question, why these 2D nanocrystal really scrolls and make a curvatures? Because this curvature brings you new properties. So to understand this question, I'm sorry, it's really going. Okay, so think about this simple material, MOS2 or graphene. When you have a very large structure, it is very stable as a 2-dimension. When you cut down into small nanostructure, 100 nanometer and by 100 nanometer, the surface atoms are unsaturated. For example, these tungsten atoms, the sulfur atom, they are not exactly 6-folded like this and 3-folded like this. They are 4-folded and 2-folded. When you are at a nano regime, they really want some friends to make a bonding. Okay, so when you are at 100 nanometer by 100 nanometer, they try to see who is next to me, let me bond, and they form a really nice, these tungsten try to bond with this sulfur and try to form a nanotube like this, very nice, beautiful structure. And these nanotube are very, well explored. You see, these are the tungsten disulfide nanotube, and these are the tungsten disulfide fullerenes. So when you make this 2-dimensional to 1-dimensional or 0-dimensional, the property completely changes. You know why? Because this has an inversion symmetry, this does not have an inversion symmetry. So you are breaking the symmetry of this material, so that gives you a dimensional driven properties. So this is very quite interesting. For example, you can take a nanotube, it shows you measure a current along this direction, nanotube direction, and opposite direction it's not the same, because you break the inversion symmetry. And for example, another thing, you can do a photovoltaic measurement. The nanotube shows a bulk photovoltaic effect. You take a laser, you shine from here, you see the current here, and when you go at the center, your current is more. But this is oppositely seen in other materials, right? So this is because of the break in the inversion symmetry. So these are what we are really excited and very interesting in why we work on nanotubes or a fullerenes, to see the dimensionality driven properties. So there are lot of interest in this material. For example, I told you a graphene and MOS2. Now we can stack them as a heterostructure and roll them. These will form a really 1-dimensional van der Waals heterostructure, and they show say like interface superconductivity and these kind of properties, and also interlayer excitons and intralayer excitons. Those are very, very interesting in optics. Okay, we choose some of the material which are very interesting for us. For example, 1-dimensional nanostructure which can be grown by CVD. Okay, and the major problem in this case, you have to take a carbon nanotube, you grow a MOS2 or boron nitride nanotube on that, and the yield is very, very, very low, maybe in hundreds of nanotube or less than hundreds of nanotube, and finding them very, very difficult. So we choose some of the compounds which are really interesting to grow them, something called misfit layered compounds, because they have a strain already between the two layers. So can you grow enough of them? So that was the idea, and they also show a metallic behavior that will be interesting. So we choose this material to grow a nanotube and a fullerenes. Okay, so I will show you only nanotube growth here. So to explain you what is misfit layered compound in simple way, you take a transient dimetal chalcogenides, you have a tantalum atoms here, you have a sulfur atoms here. This is in a trigonal prismatic lattice. You take another layer which is rock salt and put in between this. Okay, this is like your exactly battery chemistry. You are taking the MOS2, putting the lithium, but what we are doing much more interesting thing. We are putting a material in between. So we want to grow them exactly a layer by layer as a tracked heterostructure. So let's see what happens. So why we call them misfit? Because the B direction is matches, their A direction does not match at all. Okay, that's what why we call them misfit. These are the incommensurate structure, where MX is a distorted rock salt, where TX2 is a hexagonal structure. Okay, and can we roll them? And let's see, can we roll them and make it this structure? This can also be done 1:1 layer, 1:2 layers, like this. So, and there are plenty of compounds available to stack them. So you have plethora of opportunities to really make a metallic structure or a semiconducting structure. So these are all very interesting. So, okay, so let's go. We have really explain CVT protocol. We really get these materials, and these are the nanotube we really get. So I don't spend much time over here to understand all the crystallography, but let's see whether we have a stacked heterostructure like this. You see clearly, you have a tantalum disulfide, you have a samarium sulfide, tantalum disulfide, samarium sulfide. These are 1-dimensional heterostructure, grown very nicely. So to see further, you can really identify them atom by atom. We can see where there are defects, because these play a very important role when you are understanding their properties. So we cut them. We understand the structure. You can see clearly these are the samarium atoms. These are tantalum atom, samarium atom, tantalum atom. They finely arranged in a heterostructure way. Okay, we can do many of these materials. Like you can characterize them in detail. Let me not go details of them, because these materials are interesting in superconducting nature. So, for example, tantalum disulfide, niobium sulfide. We can see they are trigonal prismatic lattice here. There are hexagonal lattice here, something like that. So we characterize them by many other techniques, and we shown also the moment you put a samarium sulfide and tantalum disulfide, the superconductivity go from 0.8 Kelvin to 3.9 Kelvin. This is interesting. So you can now, just changing the charge transfer properties, you can really tune their not only structure, their properties. Okay. So with this last point, what happens when we replace sulfur by selenium? This is what the question we are asking. And you see, usually we expect the sulfur and selenium goes randomly distributed, right? But to our surprise, we see really selenium is one side and sulfur is other side. So selenium exclusively go to tantalum lattice, where sulfur go to lanthanum lattice. If you really starve the sulfur, it compromises the structure. It goes, say, instead of 1 by 1 layer, it goes to 1 by 2 layers. But this is easy to say, but how do you see this, right? So we do a lot of microscopy to see this. For example, this is at 20% selenium. You see really OT structure like this. When you have 80% selenium, you have a structure like this. But how do you prove there is sulfur here and selenium there? So to do that, we did another fantastic microscopy job here. You see there are 2 tantalum diselene layer, lanthanum layer, 2 tantalum diselene, lanthanum. This is 80% selenium. You see 2 tantalum and lanthanum, 2 tantalum. You see the sulfur and selenium now. Selenium layer, sulfur layer, selenium layer, sulfur layer. Very importantly, you see these are the 2 tantalum what I am showing here. And you see selenium peaks comes up. That means selenium is exclusively with tantalum. And whenever the lanthanum coming up, you have a sulfur signal coming up. So now what is the use of them? So that is a question you can ask. You can clearly see these have a really very anharmonic structures, and they have a break in inversion symmetry and nothing explored in a properties. Okay. So you can look at the superconductivity, you can look at the second harmonic generation, optical properties. These are quite interesting. So with this, I summarize. I told you why, at least I told you why 2D materials form a nanotube. Okay, that is a basic thing which we can understand why 2D materials. When you go to nanoregime, there are a lot of surface atoms, they form a nanotube, right? And I explained some of the heterostructure, how we grow them, right? And I also explained when we put sulfur and selenium, what happens to them. Okay, this forms a really asymmetric structure we can explore for the second harmonic generation. With this, I thank you very much, all the funding agency, IASC, SSCU, and also CRS and Saurashtra University for giving me this opportunity. Thank you very much. Please feel free to ask questions. Okay, okay, sorry.
Sir, thank you for a wonderful talk. Now it's our duty to honor you with CRS Silver Medal, which you richly deserve. Please be seated.
Big an applause to him, please. Look at that. Durga, you are you. Put your hand. Okay. Congratulations. One more honor. Sit down. One more honor from the audience.
Our next speaker, Dr. Y.S. Vidya. Dr. Y.S. Vidya is a distinguished physicist and associate professor in the Department of Physics, Government Science College, Chitradurga, recognized for her pioneering contribution to nanomaterials and energy-related functional materials. Her research on nanophosphorus, photoluminescence and supercapacitor has significantly advanced the development of luminescence material and high-performance energy storage device. A highly respected researcher with an impressive citation record, he has made valuable contribution through innovative research, scientist publication and her mentorship of young scholars.
Sorry, this is for the slides?
Yeah.
And for the light?
This is for next, this is for previous.
Okay, light will not come?
Yeah. Check it.
Yeah, it's come. Yeah. Good afternoon to one and all who are present here. First, I would like to thank organizer and the entire CRS team for giving this wonderful opportunity for me. I am Dr. Vidya, working as an associate professor in Government Science College, Chitradurga, which comes under the Davangere University. Today in this presentation, I want to highlight few of the glimpses of my research work. I have divided the entire presentation like this. First, I want to give the introduction about the functional materials, which will be applicable for the display applications, energy storage, and as well as for the electrochemical sensing platforms. All these applications are mainly depends upon one or the other way, they depends upon the method of the synthesis. These are the introduction. As we all know, the nanotechnology has emerged as a transformative field for developing the advanced materials, and the functional nanomaterials plays a very vital role in addressing the global challenges related to the energy, environment, healthcare and the advanced electronics. But in order to achieve all these things, the controlled synthesis and the engineering of the nanostructure, significantly they were going to improve the optical, electrical and the electrochemical and including the catalytic performance also. This functional, why we have chosen the functional nanomaterials means because they will possess the high surface to volume ratio and we can easily tune the electronic and the optical properties. They possess the highly enhanced catalytic activity. They have a more enhanced charge transport and the storage capability. These nanomaterials can be synthesized. I have highlighted only few from solid state method to the green synthesis method. All we have synthesized by using the different ways. Among all these things, nowadays we have stick on this one to the solution combustion synthesis method by using the green extracts, because crystallite size and the properties such as the crystallite size, phase purity, crystallinity, morphology, dislocation density, oxygen vacancies or the agglomeration, which plays a very important role in the application part, they will all depends upon the method of the synthesis. These conventional methods, because with respect to the green synthesis method, in almost all the methods we are going to use the chemicals, one or the other way we are going to use the chemical which is very harmful to the environment. So, but in the green synthesis method, we are going to reduce the chemicals and instead of using the chemicals, we are using the green extracts, because in the green approach, it is an eco-friendly in nature and we are using the renewable energy reducing agents. The mild reaction condition is enough in order to synthesize the nanomaterial. It is of low cost and the biocompatible, and we are using the natural capping agents, better sustainability. In order to achieve all these things, we are using the green approach. Here I took one example, which is the combination of both ZrO2 and as well as the TiO2, which is nothing but the ZrTi4 zirconium titanate, which is synthesized by using the two different approach. One is the chemical approach and another one is the green approach, where we have used the aloe vera gel extract as a reducing agent, and I am going to highlight how the application is going to vary. And in the first part, we have synthesized the sample by using the glycine as a fuel, which is nothing but it is a fuel But in the second flow chart, I have shown the aloe vera gel extract. It is not acting like a fuel, but it is the reducing agent. It helps to reduce the metal nitrates to metal oxide nanoparticles very easily. Usually, in order to achieve the orthorhombic phase of the ZrTiO4, we require the around 800 degrees Celsius to 900 degrees Celsius calcination temperature. But the use of the aloe vera gel has been reduced the calcination temperature to around 600 degrees Celsius. We have achieved the single phase ZrTiO4 at 600 degrees Celsius calcination. In order to standardize the aloe vera gel concentration, we have varied the concentration from 15, 20, 25 ml. But later it is stick on to the 20 ml because at the 20 ml, the intensity of the XRD pattern is also very good. As we observed in the XRD pattern, when we used the glycine sample, we are observing the mixture, that is the orthorhombic phase of the ZrTiO4 and as well as the monoclinic on the cubic phase of the ZrO2. But when we use the aloe vera gel extract, we got the few orthorhombic phase of the ZrTiO4. As we all know, when the mixed phase comes, it will and reduces the application part of the sample. And we are observing the morphology also. In the morphology, the chemical approach particle will consisting of an highly agglomerated nanoparticles. Whenever the nanoparticles are agglomerated in nature, it reduces the surface to volume ratio. But when it comes to the green approach, we are observing the nanorods. Because of the presence of the nanorods, the surface to volume ratio is a maximum and we can expect the maximum or the enhanced applications also. And from the green approach, we can able to easily tune the energy band gap also. We have done the UV observance and the talk plot also. As we observed, the energy band gap of the ZrO2 is around 5.8 electron volts and that of the TiO2 is around 3.8 electron volts. But the combination of those two has given the energy band gap has been reduced to 3.2 and the 2.7 electron volts. This is the photoluminescence emission spectra where we took the intensity with respect to the wavelength. As we observing, the intensity of the chemical approach is little bit high compared to that of the green approach. It doesn't mean it won't give the proper emission. That means even though the intensity of the PL is less, this is mainly due to the presence of the defect states. This clearly indicates defects are more in the case of the green approach. As and when the defects are more, they were going to create the energy levels in between the conduction band and the valence band. And as a result, instead of the radiative transition, non-radiative transitions we are going to observe. Because of that one, the intensity is little bit less. Here, the peaks are observing from 350 to 570 nanometer. That means both in the blue and as well as in the green region. And we can't able to distinguish which color we can able to see. That's why we have used the CIE software. That CIE software, from that one we can able to easily observe which color our eye can able to identify. Here the two samples were going to give the pattern in the two different colors. One ZTOG means it is a chemical part, A means it is the green synthesis part. The material which is synthesized by using the chemical approach gives the aqua. That means this material can be used as a nanophosphor material for the aqua LEDs. And the material which is synthesized by using the green approach can be used as a nanophosphor material in the blue LEDs. This paper is published in the Ceramic International. And this is for the CV plot what we have plotted in order to calculate the supercapacitance, that is in the higher energy storage purpose, and that is the Nyquist plot. As we all know, the area is directly proportional to the specific capacitance. This area is found to be maximum in the green approach. And here in the Nyquist plot also, that semicircle what we are observing is found to be less for the green approach. Whenever the RCT value is less, we can expect the more energy for the green approach rather compared to that of the chemical approach. We have used the same sample for the paracetamol and as well as for the ascorbic acid also. In the medical field, both will play a very important role because the dosage of the paracetamol and the ascorbic acid is required. In order to sense all those things, we need a sample. This material that means can be used as a nanophosphor material for the LED applications and for the supercapacitor and as well as for the as a sensing material for the paracetamol and for the ascorbic acid. And apart from that, we have by using the same sample, we have synthesized ZrO2 and the NiO, which composite, where the Mg is also doped for that one. for the H2O2 sensing material, and this is synthesized by using the Sepothedia, which is easily available in the park and all those things, and we took the green extract from that one and we have synthesized the sample. Again we have done the XRD, and the XRD pattern is also very good. We have synthesized ZrO2, NiO, and as well as the composite and as well as the dopant also. This paper is published in the Inorganic Chemistry of Communications, where we have done the morphology also. This material, this is the photoluminescence spectra. We are observing the pattern only in the blue region, so this material can also be used as a nanophosphor material in the LEDs. Yes, sir. Yeah. Yes, sir. Okay, sir. And this material is used for the H2O2 sensor also. And similarly, we have developed the other ternary composites also. That is BiO-Br doped with an Y, and also with an BiO-Br doped with La, and then G, that is graphitic carbon nano phosphide material for the other applications like in CDCl2 and the ibuprofen sensing, and also with respect to the Dolo 650 sensing. And these are some materials what I have highlighted. We have synthesized the sample in our laboratory ZNO by using the neem leaves, and also with an aloe vera gel and the gooseberry fruit extracts. And this is the another plant, Lucas aspera, and also by using, this is the Euphorbia thirucalli milk latex we have used. And lastly, finally we have developed that sample by LA doped MgFe2O4 by using the clove oil. And these are from laboratory to industry applications of the functional nanomaterials. This is used for the display, energy storage application, environmental industry, healthcare, and the pharmaceutical industries. So green manufacturing. So summary, we have the overall the green synthesis represent the promising strategy for developing the next generation multifunctional nanomaterials that supports the sustainable technological advancement. These are the future scope highlighted. I have highlighted only few. Development of the multifunctional heterostructure nanomaterials, scale up of green synthesis, and integration into flexible and wearable devices, exploration of the advanced energy application, and we can also use the artificial intelligence and the machine learning. These are some references, and I want to acknowledge the organizers of this program, President and Secretary of the CRS, and I would like to acknowledge the entire research team headed by Dr. Anant Raju KS, and also to my son Adyant and the Ayush KA. Thank you, one and all.
Man behind the woman. On behalf of the organizer, I give opportunity to honor. They are hero and heroine. That काम यही होता है. Thank you, madam. Madam, you wonderful talk. Keep doing good work in the college. Any help? What is?
Our next speaker, bronze medal awardee, Professor Umed C. Bhoya. Professor Umed C. Bhoya is professor and head of the Department of Chemistry, Saurashtra University, Rajkot. He obtained his MSc and PhD in the Chemistry Department, Saurashtra University, and has over 30 years of teaching experience and 27 years of research experience. His research interests included liquid crystal, analytical chemistry, and organic chemistry. He has published 78 research papers, completed 2 research projects, guided 14 PhD scholars, and currently supervising 8 research students. Professor Bhoya sir is an active member of Indian Liquid Crystal Society and Chirantan Rasayan Sanstha and has served on several academic and administrative committee at Saurashtra University.
Light one करजो. Good morning, everyone. I am going to present my work entitled Synthesis, Mesomorphic Behavior, Thermal Analysis, and DFT Study of Fluorinated Azo-base Homologous Series of Liquid Crystalline Compound. The objective of this research was to synthesize two new homologous series of fluorinated azo-ester and investigate how structural modification influence on their mesomorphic, thermal, photophysical, and optical electronic properties. Particularly emphasis was placed on understanding the role of fluorine substitution, molecular architecture, and alkoxy chain length in determining liquid crystalline behavior and photoresponsiveness. Liquid crystal represent a unique state of matter that combine the fluidity of liquid with the molecular order of crystalline solids. Among various liquid crystalline compounds, azo-base liquid crystal are particularly interested because the azo linkage can undergo reversible trans photoisomerization upon exposure to light. This photo-induced structural change alters molecular shape, polarity, and intermolar attraction, thereby the changes in mesophase length and optical property. The incorporation of fluorine atom is particularly attractive because fluorine enhances molecular polarity and intermolecular polarity and dipole moment, thereby improving intermolecular attraction and potentially stabilize liquid crystalline phases. Therefore, the present work focus on developing fluorinated azo-liquid crystal with improved thermal stability and efficiency, light responsive property for advanced photonic application. Then reaction scheme. First, 4-amino 2-fluoro-benzoic acid give ethyl 4-amino 2-fluorobenzoate by Fischer esterification method. Then diazotization of ethyl 4-amino 2-fluorobenzoate give diazonium salt, and then coupling with the phenol and substituted phenol give intermediate A and intermediate B. Then intermediate A give Williamson ether reaction to give final product means series A, and intermediate B react with alkoxybenzoic acid by ester stabilification method give compound B means series B. The synthesized compound were structurally confirmed using proton NMR spectroscopy. Here aromatic proton signals appear in the aromatic region 6.9 to 8.2. Ester methylene protons give 4.4 ppm. Alkoxy methylene group is appeared around 4 ppm. Here characteristic methylene differ from this group. Characteristic methylene proton appeared in 2.5 ppm, absent in series A, here 2.5 ppm, and here terminal group methyl proton give aliphatic region. This is POM analysis of series A and B. Series A synthesize 11 homolog. Compound C2 and C3 are non-mesomorphic in nature, while C4 to C16 are mesomorphic in nature and give a smectic A phase. Smectic A phase means smectic A, low temperature smectic A phase. Series B, series B synthesize total 10 compound. Here C3, C4 and C6 give first crystalline to crystalline transformation and then give mesomorphic phase, while other compound give direct crystalline to smectic phase and then isotropic temperature. Isotropic temperature are more, this series isotropic temperature are below 100, and series B isotropic temperature are greater than 100, means 140 degree Celsius. This is phase diagram of homologous series A and B. Here crystalline to isotropic and crystalline to smectic A phase are overall descending order. Smectic A to isotropic phase are normal manner. Here zigzag type of manner, and this is descending of manner in series B. Phase analysis of series A and B. This is crystalline texture of series A, then heating to give smectic A phase at 82.2 degrees Celsius, then heating to give isotropic temperature, and now cooling to show smectic A mesophase at 70.3 degrees Celsius, then cooling to give crystalline structure. In series B, this is crystalline texture of series B, then heated to give crystal to crystal transformation, and then heated to give smectic C phase, and then heating to give isotropic, and now cooling at 111.4 degrees Celsius to give smectic C phase. Now DSC study of series A and B. The thermal DSC study of series A, C10 and C4 homologous differed markedly. Series A, the series A C10 derivative display simple phase mesophase ranging. In contrast, series B C4 homologous exhibit greater thermal stability. Here, here 70.6 degrees Celsius in mesophase, so, and this is 94.5 degree R isotropic temperature. Here crystal to crystalline transformation, then start to mesomorphic, so in 100 degrees Celsius, and then smectic C to isotropic temperature in 145 degrees Celsius. Then comparative study of series A and B. Here are structural representation of series A and B. Linking group, terminal group, and lateral group are common. Q azo group, linking group fluoride, and Y are common but differ from X and L1. Here L1 is equal to disubstituted methyl group, and X are common, though smectic to isotropic temperature differ in X and L1 to give smectic A phase and give smectic C phase. Thermal stability of 88.3 degrees Celsius and 120.2 degrees Celsius in series B, though series B is greater than series One commencement of mesomic phase in series A is C4 and series B is C2. So C2 is greater than series 2 and mesomorphic length are 8.8 degree to 40.8 degrees Celsius. Here 12.6 to 47.9 degrees Celsius. So overall series B are greater than series A by changing in this group, this bulky group and this disubstituted methyl group. Here powder XRD was used to investigate molecular arrangement of series A and series B compound. Here at room temperature multiple low angle deflection are observed, show highly ordered layer structure, means crystalline phase. Then heating when sample is heated 60 degrees Celsius, the pattern is change noticeable. Only 2 peaks are observed and their intensity become much longer, suggesting the layer order is still present but has become more dynamic while loss of higher order reflection. The observation in powder XRD is suggesting presence of smectic C phase. This is series B. Okay, thermal stability. This is transit photoisomerization, kinetic study and conclusion. Okay, thank you.
Thank you for giving us good money. I should tell everybody that you give a good money for us. No, for the conference, not personal. Yeah, bhai.
Our next speaker, bronze medal awardee, Dr. Navya Rani. Dr. Navya Rani M is Distinguished Research Academic Leader and Associate Dean of Research and Development and Associate Professor at Nagarjuna College of Engineering and Technology, Bangalore. She is widely recognized for her contribution to biotechnology, nanotechnology, advanced functional materials, and sustainable energy technologies. Her innovative research in graphene and MXene-based nanomaterial has advanced application in energy storage, environmental sustainability, and next-generation materials. Please welcome, Madam.
myself Dr. Navya. So myself Dr. Navya, so I thank CRS for giving me this opportunity to share my research work. So today I'm going to share about my journey with graphene in the field of nanotechnology. So the contents of my presentation will be including the introduction of two-dimensional nanomaterial. I think the last speaker also explained you about the two-dimensional materials and the applications. So I have divided my applications into two sectors, that is biomedical as well as energy storage application. So to begin with, I think all of you know it is what is two-dimensional nanomaterials. So basically these are thin layer of atoms which are arranged in single layer. And so two-dimensional nanomaterials where the electrons movement are in the two direction, which is proving the quantum confinement. And because of this property, there are several properties like high tensile strength and high electrical conductivity and so on. So recently there are also evidence of using two-dimensional materials. So I started off my work with graphene, and recently a few materials which are just analogs to graphene like boron nitrate, metal oxide nanosheets and layer double hydroxide are also evidence. And very recent new addition is MXene, which you can see here. These are the large kingdom of the two-dimensional nanomaterials which are used for the applications. So the properties of two-dimensional materials are they are having intercalation, that is you can tune the properties, and high rich surface functional groups. So because of this addition of new functional groups, you are able to do the dispersion, and the electrical conductivity can also be tunable, and it is having high tensile and mechanical strength. And the synergetic performance, that is we could try to prepare some nanocomposites which had added the benefits like we can increase the electrical conductivity as also the electrochemical activity. So because of this, you can see applications in biomedical as well as the energy sector, that is energy storage applications in lithium-ion battery and supercapacitors. So this slide shows you the application of nanocomposites, that is using copper oxide and RGO nanocomposite. So we have used a medicinal plant. So the previous speaker, Dr. Vidya, also explained you about using the plant extract as a reducing agent. So the natural antioxidants which are present in the plants could act as the reducing agent for reducing the silver nitrate as well as the graphene oxide. So we have confirmed the same by XRD, that is exfoliation studies, and also we have done the characterization techniques of XRD and also the SEM and TEM. So you can see the shape of the nanocomposites that we have prepared. So graphene is basically the flake-like structure. So we try to observe the effect of this nanocomposites on several microorganisms. So basically we have used the gram-positive and gram-negative bacteria, this is pathogenic, and we try to observe the inhibition of those microorganisms using this nanocomposite that we could prepare. And this was a biomedical application. Further, we also extended our composite study on the sensing performance. So in this slide, you can see that we have used the natural fiber, that is silk cocoon, and we have done two comparative studies. So this one we have tried to combine the multi-walled carbon nanotubes along with the natural fiber, and this one we have done the carbonization of the silk fiber. So in both the cases, with and without the carbonization, we have tried to develop the prototypes. You can see these are the prototypes without and with carbonization. So this one was with multi-walled carbon nanotubes coupled with natural fiber, and we have checked the sensing performance. So you can see here this blue color one is bare silk fiber, and the red color one is showing the high electric performance after combining with multi-walled carbon nanotubes. So similarly, we have confirmed with characterization, that is XRD, and the morphological studies using SEM and TEM. And here you can see after carbonization, that is we try to use at 900 degrees centigrade in argon atmosphere. So we have developed the prototype, and we have also confirmed the high electric performance using this carbonized silk fiber. So using this our group, we try to do some pressure sensor applications. So we are trying to think where to place which acts just like a pressure sensor, so that is neck or wrist, so which will produce the electric current. So The next study was done using the kapok fiber, which is just similar to the silk fiber. That's my previous slide which I showed you. Here we have tried to carbonize the fiber, that is kapok fiber, which had just properties like silk fiber only. So here you can see. So here you can see after the carbonization, that is at 900 degree in argon atmosphere. So the first one shows you without grinding. So without grinding, this structure looked just like the fiber, that is kapok fiber, and B, C and D is showing you after mechanical grinding, where we have observed the nanosheets. And similarly we have checked this one for the battery and as well as supercapacitor application. So this one for lithium ion battery performance, and this is supercapacitance, where we could see the high electric performance. So this paper is also published from one of my co-author. And for the first time in India, we try to develop the super critical fluid synthesis. So this is a new way of synthesizing the nanostructures. The advantages, so all this conventional method is using a very huge amount of hydrofluoric acid, about 40%, whereas supercritical fluid we are reducing 10 times folder, that is only 4% to 10% to develop some nanocomposites. And the properties are this, you can see we are able to tunable and we have high reaction rate using this process. And another advantages, conventional methods, that is using hydrothermal or any other methods, is inclusive of corrosive acids like hydrogen fluoride. Whereas in this supercritical fluid synthesis that we try to develop, which is a novel method for the first time, we have reduced the percentage of hydrogen fluoride, that is just to 4%. So we have used water as a solvent for the dilution. So as I told you, using that supercritical fluid process, we have developed all this, that is MXene, which is just double layered structure, where the interconnection is very possible. That is what is very advantageous for the energy storage and battery performance. And we have also developed this nickel sulfide nanostructure and bismuth tungstate and RGO nanocomposite. So these two are nanocomposites. This one is MXene and nickel sulfide. So you can see here we could successfully produce the titanium carbide MXene and manganese and vanadium peroxide. Only the reaction time is different, that is 30 to maximum 45 minutes. We are able to produce a nanostructure, whereas the conventional method we were about to, we had to do it for the 7 days. So we have reduced it to the 1 hour by using the supercritical fluid synthesis. So we could successfully develop this, and we also got the granted patent in 2025, and we have published this paper in ACS journal. And similarly, we also try to synthesize the nickel sulfide using the supercritical fluid synthesis, and we have tried to control the phase structure and the morphology, which is also very suitable for energy storage application. And these two are the nanocomposites, that is bismuth tungstate with RGO and layered MXene, which is very suitable for battery application. So you can see here nickel bismuth as well as titanium carbide. Both of these are used for increasing the battery performance and the energy storage. So recently our group also tried to apply these nanocomposites for the battery and supercapacitor performance. So we were able to develop, you can see here. Yeah. So this one was using vanadium pentoxide. So we could get high energy and high current capacity performance, and this one was using manganese carbide. And similarly, we could also fabricate for the lithium-ion battery applications, and we could evidence very high energy and electricity performance. And we also tried to develop the prototype, that is just like the coin cell for the supercapacitor application, and we could also observe the high activity in the performance. So, and again, a new addition into our group is like we also tried using these nanocomposites for the green hydrogen generation, that is photocatalysis using sunlight, which is a very natural approach. And we could try to prepare two composites, that is, this one is defect titanium oxide molybdenum sulfide coupled with reduced graphene oxide, and this is molybdenum sulfide coupled with reduced graphene oxide. So in both the cases, we are able to use it as a good composite for the photocatalysis for the green hydrogen generation, a good water splitting. So yes. Okay. Yes. So this is a summary of my slide that we could synthesize and categorize the two-dimensional nanostructure and the new addition of the nano material or the nano composite, which is very suitable for both biomedical as well as energy storage. So which is a green approach, and we could develop a new method that is supercritical fluid synthesis, which I showed you, and we could develop several heterostructures and also composites which are very suitable for photocatalysis, supercapacitors and lithium-ion battery fabrication. Thank you.
You are also organizer, right? You are organizer, part of our, because of you we are here. ಎರಡನೇ ಸತಿ ಮ್ಯಾರೇಜ್ ಆಗ್ತಿದ್ದೀರಾ? ಎರಡನೇ ಸತಿ ಮ್ಯಾರೇಜ್ ಅಯ್ಯೋ ಬನ್ನಿ ಸರ್ ನೀವು ಬನ್ನಿ one more heroine director. Madam, wonderful talk. Thank you. Hi, good afternoon. We sincerely apologize because of many issues we could not come on time. There are so many cancellation of flights, delay of trains, many things happened, so we had to apologize sincerely. We have sincere apologies. Morning went off very well, but some disruption was there. So my sincere apologies to you. Then we can start now. And thank you. I can see Professor Attifeld is also there. Thank you. Thank you for joining. Yeah. Great.
Yeah. Thank you. So shall I share my screen? This is my screen?
Yeah, please wait for 1 minute.
Sure, just let me know.
Please start.
Can I start? Okay. Great, thank you. Yeah, so
You are quite
thank you.
audible and slides are visible. If you may, please start. Thank you.
Okay.
Your time begins now.
All right, thank you very much. So first of all, good afternoon, everyone. I hope you can hear and see me. It's a great pleasure to be there, not on site, unfortunately, because I'm attending a different conference in Singapore right now. But first of all, let me thank you for for the award. That's a great honor for me and a great appreciation of our work. Thank you very much for this wonderful award. Okay, so I'm diving right into my talk, and I'd like to start with a little drama slide. I guess we all know these pictures of extreme weather events, whether in Germany or elsewhere. I've just heard in India there also was a flooding, so I guess we're seeing these pictures more and more often. And of course, this is a consequence of global warming and climate change. And when we keep doing what we do, you can see this over here on the right, then by the end of the century, the temperature of the planet will have increased by more than 5 degrees. So it's a good idea to sort of decrease our dependency on fossil fuels, obviously. Now, the good news is that there's a solution to this problem, and the solution is the sun. We have more than enough. To put this a bit into perspective, if we cover an area around the size of Spain in the Sahara with photovoltaics running at around about 20% efficiency, which is quite realistic, then we can cover the entire energy requirements of the planet. So this is really good news, I think. The only problem or the only caveat that the sun brings about is the fact that it doesn't shine 24/7. Obviously, there's intermittency of solar irradiation, as you can see, for example, when you look at Germany's net electricity generation. So here we're looking at 2 weeks, one in the summer and one in the winter. And what you can clearly see is that there are 2 cycles that we need to take care of, 2 sort of fluctuations in solar energy availability. One is the day-night cycle, very obviously seen here. And the other one is the seasonal cycle. So essentially, in the summertime, the sun makes up for about 50% of Germany's electricity mix, but in the wintertime, only a few percent. So what we need is basically storage options that are long-term or short-term. So basically covering the day-night cycle and also the seasonal cycle. And there are storage solutions around that are adjusted to different system requirements and also to different durations. But when you look at these different storage options, then you'll notice that for all of them, there's a strict separation between solar energy conversion, say photovoltaics, and storage. And so we've been thinking about whether this is actually an inherent requirement or whether we can change this and sort of bridge the divide between solar energy conversion and storage. And to put this perhaps a bit more specific, the question is, can we store sunlight directly? For example, by making a solar battery, right? So the answer is yes, we can do this. But in order to do this, we need special materials. So basically, the answer is materials innovation, and we need materials that can both absorb light and store charge. So in other words, we need to bring together optoelectronics and solid-state ionics. And this brings me directly to the materials that I would like to talk about a bit more. And these materials are called carbon nitrides. Carbon nitrides belong to, well, I would say the oldest classes of artificial materials, at least artificial polymers. And already the godfathers of chemistry, you see them here, Friedrich Wöhler, Justus von Liebig, Berzelius, they all have been fascinated by this class of materials. They even made it into a Vanity Fair attraction, which you can see over here. So this is known as the Pharaoh's serpent. And this is basically the burning of mercury thiocyanate in air. And what comes out of this reaction, you see down here, this is a one-dimensional heptazine-based polymer that is called Liebig's melon. He called it melon for no obvious reason. And this is very often somewhat loosely called graphitic carbon nitride. So Liebig was also the first to recognize that these carbon nitrides have a lot in common with animal compounds, as he called it. And in fact, what he means is that we can synthesize carbon nitrides by thermal condensation reactions from very simple precursors, very cheap precursors like, for example, cyanamide or urea or melamine. Now, when we switch the synthesis from a thermal condensation reaction to isothermal synthesis, then we are also able to access basically two-dimensional carbon nitrides. And this is what I would like to talk a bit for the remainder of my talk. The 2D carbon nitride I'm referring to, which is down here on the right, is the so-called polyheptazine imide with cations, with potassium ions in the pores. So in a nutshell, this is kind of what we know about the structure of this material. It is a two-dimensional carbon nitride that is not a pure carbon nitride, so it has these hydrated potassium ions sitting in the pore. It is a nanocrystalline compound. The structure is fairly well defined, and the channels in which these cations reside, they run along the C direction. So we got interested in this material because it shows very interesting optical and photocatalytic properties. And in fact, although it has the same band gap as Liebig's melon that I was just mentioning, this 1D polymer, it shows a catalytic activity that is by an order of magnitude higher. And so we were curious about what is the reason for that. And so we took a look at the optoelectronic properties. And so in a nutshell, what we realize is that when we add an electron donor to the system and irradiate with above bandgap irradiation, this is what you see in the transient absorption spectrum here, then for PHI, a very long-lived component is coming up. And this long-lived component is actually a sign, a very clear signature of trapped electrons. We can even see these trapped electrons, we can see them with the bare eye even, and also in EPR spectroscopy. So these are very clear signatures of a process that we call photocharging. Now this is the optoelectronic side of the story. I just mentioned that there are also cations in the pores, and these cations, as you can see here, are actually mobile. So we see conductivities, especially if we increase relative humidity of 10 to the minus 5 Siemens per centimeter. So this is not, it's not super great, but it's a substantial conductivity and hence mobility of the cations in the pores. What we also see, and this is perhaps even more surprising, is that the conductivity correlates with the hydrogen evolution efficiency. So whether this is a correlation or causation, we're not entirely sure, but we can clearly see that the presence of the ion seems to modify the catalytic activity and also give rise basically to the opto-ionic properties of this material. And what I mean by that is shown here. So when we look at the, let's say, atomistic picture of this, opto-ionic behavior, then this is as follows. So basically we shine light on the material, electron-hole pairs are generated, the holes are quenched very rapidly by an electron donor. So essentially the valence band of this carbon nitride is very positive, so the material is very oxidative under irradiation, so the holes are removed and the electrons remain on the heptazine units and are screened by incoming alkali metal cations. And we believe that this is the reason why we can essentially separate the oxidative half reaction that I showed you from the reductive half reaction, because we collect electrons on the material and store them, and then we can retrieve them later on demand. And again, we believe this is an opto-ionic process simply because there is an indirect coupling between light and ions in the system, which is mediated by electronic charge carriers. So let me put this a bit into context. So such processes are not new, actually. They have been proposed, for example, by Helmut Tribuch in the 1980s already. Tribuch suggested a mechanism called photointercalation for p-type transition metal dihydrogenonides. And in a nutshell, what happens here is basically upon irradiation, the light-induced electrons in the quasi-Fermi level act as a driving force to pull cations from solution into the bulk of the material, whereas the majority charge carriers, the holes, are extracted into the electrode. And so, in essence, what's happening here is that the energy of the electrons in the quasi-Fermi level is lowered, but the overall energy of the system is increased, and so that effectively results in the storage of solar energy. So this process can be generalized also to N-type systems, like, for example, molybdenum trioxide, when we sort of switch from a photoelectrochemical to a photochemical scenario. So basically here we're extracting the minority charge carriers into the solution with an electron donor, and sodium is photointercalated into the system. And so we believe that this is precisely what is happening in this carbon nitride. When we shine light, electrons get sort of accumulated on the Heptazine units and charge compensated by cations from solution. And now, I would like to sort of show you what we can do with these types of, with this sort of photo charging behavior that we see here. Before I do this, let me just summarize what we've seen here so far in the materials that I just mentioned, including the carbon nitride. So basically, we see a detailed coupling between, or a detailed balance between, light-induced electronic and ionic charge carriers. And so that, we see this also in other types of materials, maybe most famously in MAPI, lead halide perovskites, where sort of the term optoionics has been coined by Joachim Meyer and colleagues. And so this is a quite general phenomenon that enables us to control ions with light. And I think that the mechanism of photointercalation is particularly intriguing because it gives us a possibility to kind of photocharge our materials. And that, of course, is reminiscent of the electrode materials in a battery. The only difference being that here we don't need sort of a voltage to charge the battery, but we actually produce a photovoltage to charge the battery, and that results in direct light storage. So on the last couple of slides, let me briefly show you what we can do to put this concept of light storage to work. I won't have time to go into all of these 4 applications, but let me just mention or pick out dark photocatalysis and direct solar batteries. And I think this will give you a flavor of what I'm referring to here. So first, dark photocatalysis. So here the idea is to separate the light from the dark reactions of photocatalysis. And this is pretty much inspired by natural photosynthesis, where we also have light-dependent reactions in photosystem 1 and 2, and light-independent reactions, which is CO2 fixation that happens in the Calvin cycle. Now, I should mention that in natural photosynthesis, the light-dependent and the light-independent reactions are decoupled spatially, but they are coupled functionally. So what that means is that when there's no sun, then also the dark reactions don't happen because they need NADPH and ATP that sort of is shuttled over from the light reactions. So in a way, we want to go a step beyond this, and we want to fully decouple the light and the dark reactions of photocatalysis. And this is possible with photocharging materials. So the principle is very simple. So here we have a suspension of our PHI. We sort of illuminate it in the presence of an electron donor. Then we turn off the light and we add platinum as a catalyst, a hydrogen evolution catalyst. And then the question is, does the system evolve hydrogen also in the dark? And here you clearly see that it does. So this is the phase where the light is on in yellow. And then when we turn off the light, you see that, even there are losses, quite substantial amounts of hydrogen are actually evolved even 10 hours or even longer after the light is off. So this really gives us a possibility to decouple solar irradiation from solar fuel production. And the question is, where could this be useful? Well, essentially, it could be useful everywhere where we need to supply solar energy also when the sun doesn't shine, which, for example, is during cloud overcast during the day, or also in the early evening hours, where there's actually a peak demand. This is known as the duck curve. So there's a peak energy demand in the early evening when the sun has just set. And so if we could shift the solar availability into this time in the early evening, this would be, this would certainly be an asset. So there are, and now I'm coming back to a previous slide, or what you've seen on a previous slide, there are a number of storage solutions, but most of them really are optimized for mid and long-term storage. And what we have here is essentially a buffer system, a solar buffer that generates persistent solar energy that can be used either to produce solar fuels or that can be harvested in the form of electricity. And that basically gives us direct solar batteries. And this is the second example that I would like to share. So basically, this photocharging behavior of carbon nitrides enables us to create a direct solar battery. And with direct, I mean that this material, as we've seen before, is able not just to produce a photocurrent like a solar cell, but also to store the charges at open circuit potential and so act also like a battery. So essentially, this makes for the photoanode of our solar battery. So KPHI absorbs light and stores charge, and then the holes are shuttled across an internal, let's say, hole transfer chain into the whole storage material PSS. So PHI is the sort of the heart of the solar battery, and it sort of, this is why we call it an opto-ionic solar battery, because it basically fulfills these two functions due to its very peculiar atomistic light harvesting and storage properties. Now, you might notice that in this design, we can photocharge without connecting the anode with the cathode. And so it's an extremely compact design, as you can see here. And this actually enables us, and you see this here in the GCD curves, this enables us to photocharge the solar battery while discharging it electrically. So we can basically do this at the same time. And this is seen here by the fact that when we illuminate also during discharge, the accessible capacity is much higher. So there are other design considerations that we have to think about, for example, in terms of energy input. So can we charge the solar battery purely with light, or do we have to supply an additional charging voltage? So in our case, we actually can charge the system purely with light, but still we realize that a sort of hybrid mode, so a combined photo and electric charging mode, actually leverages most of the capacity. So these are considerations, that are important to really design future solar batteries. And a very interesting and very challenging, in fact, other design consideration is optical design. So basically, we want to make sure that we manage the light, and that means basically we want to maximize light harvesting, we want to maximize absorption of our materials, but at the same time, we want to maximize the aerial capacity of our electrode materials, and that puts let's say, a limit to the film thickness we can use for our electrode materials. We also need to worry about charge carrier collection efficiencies, recombination, charge transfer across the interfaces. So all, I would say, interfacial challenges that we know very well from photovoltaics. And so these things, are keeping us busy at the moment. Now, finally, where could a solar battery actually be useful? So as you can imagine, this is a very young and emerging field of research. I don't think that at least, anywhere close in time, we will be able to be competitive with the separate system of, photovoltaics and battery that are connected in series, especially not for large scale or grid scale applications like peak shaving or backup power. But certainly this will keep this thing. Yeah, I'll be done in a minute. Yeah, I will be done very quickly. But so where this could be actually interesting is everywhere where, let's say, integration, miniaturization, and self-sufficiency is important. Like, for example, self-powered electronics in remote places, or perhaps, wearable electronics, things like that, electronic skin, for example. So where integration really is key. Okay, and with this, I'm actually already at the end. I'll skip a summary, but what I certainly don't want to skip is to thank my group, a fantastic group of people, all the funding agencies, and of course, thank you very much for your kind attention. Sorry again that I can't be on site, and thank you very, very much again for this award. Thank you.
Professor Bettina, it was wonderful
Yeah.
talk. I'm
Thank you.
sure all research students present who are working on these such areas are highly benefited. It's a very, very, very pleasant talk to
Thank you.
listen to you.
Appreciate it.
It has been phenomenal job you have done, and you are encouraging so many people like us. And in
Our speaker, sorry to say that. However, we'll accommodate him in the next session. Now we'll break for lunch. Have a nice lunch. Come back and sleep. Thank you. begin the next session, I would like to invite both the chairs. Sir, आप आइए. आइए. So these two are the chairs. Now they are going to conduct the event now. Sir, आपका हाथ में अभी दोनों के हाथ में.
सर टाइम स्ट्रिक्ट वो जो भी है 15 मिनट्स का जो है ना 13 मिनट 12 मिनट होने के बाद उसको अलर्ट करना है रिमाइंड करना सर स्ट्रिक्ट अबाउट द टाइमिंग्स તમારે ત્યાં ચાલે છે ના મુજુમદાર સર का फाइल में करेंगे स्पीकर માટે સર પ્રોફેસર મુજુમદાર फाइल में करेंगे હા એ કરે છે मैडम आप बैठ लिया हो 2 मिनट
Very good afternoon. I know it's difficult after lunch to speak and listen both. We have a good number of participants. So we have, I think, 5 in this session. Between 2 to 4 we have 5 presentation. Each presentation for about 15 minutes. 15 minutes. You are the first to break the ice after lunch. Okay. I don't know what menu was in the lunch.
Everything was very heavy, sir.
Okay. So, sir, accordingly, yeah. Okay. Fine. So the first professor, respected professor, who is going to break the ice for the afternoon session, Professor. आज છે ને हाँ वो मेरी तरफ देखे मैं बोलूँ तो कुछ हाँ आई एम टॉकिंग अबाउट यू सर fine. So respected Professor Baswaraj Padmashali. Professor Baswaraj Padmashali is a distinguished organic chemist, academic leader and administrator, renowned for his pioneering contribution to synthetic organic chemistry. I hope everybody is from the chemistry, so they know what exactly the synthetic chemistry is all about. Natural product chemistry, drug discovery and catalysis. His innovative research on biological active heterocyclic compounds has significantly advanced medical chemistry and pharmaceutical sciences. With an extensive record of high impact publications, numerous Indian and US patents, internationally recognized collaborations and funded research projects, he has made lasting contribution to chemical research and motivation. As an accomplished educator and university administrator, he has inspired excellence in teaching, research and academic governance. So, sir, stage is yours for 15 minutes. All participants are also yours. Thank you.
Good afternoon, everyone present here. In fact, there are 2 types of lunch we have. One is working lunch and another one is lunch that works. Hope you had the first one. At the outset, At the outset, I would like to thank CRS and Saurashtra University for giving me this opportunity to speak before you regarding the glance of my research work that we are carrying out. I thank immensely CRS because they have honored me with silver medal, and of course Saurashtra University for their nice hospitality. Go for the first slides. Yeah. So I would like to have a glance of how we developed indolizine chemistry and how we strategize the drug discovery process in our research category. So after completing my PhD in synthetic organic chemistry in Kuvempu University, that is in Karnataka, I took a fresh batch of PhD students, and we started working with those PhD students with these heterocycles. So there was earlier, because these are the early days of research, and I was in a confusion and I was in a dilemma so as to select which heterocycle. I saw some research papers on benzothiophene, and one student was assigned benzothiophene work, and I saw some research papers on benzothiazole. One student was assigned benzothiazole, and like that. So there was a confusion, and with that confusion only we started finding some, synthesizing some new heterocycles. So these are the some heterocycles that we concentrated in the beginning, and later on. So they were at that time we were very young and very haphazard also, because we had a confusion, greater confusion that to which heterocycle I should select for, and to which heterocyclic derivatives I have to go for the pharmacological investigation. These are some schemes that our earlier PhD students have done. We synthesized beautiful molecules, and in drug discovery what happens is, we synthesize in one scheme, we synthesize nearly 15 to 20 compounds, and out of 20 compounds only few, like 4 or 5 will be selected and will go for the biological activities. But the other thing, other molecules out of 15 or 20 will take only 2-3 molecules, and other will be they are useless. I am sorry to say they are not useless, but they are less used. So these are some heterocyclic molecules, that the novel heterocyclic molecules that we prepared with those fresh PhD candidates. But later on, when I moved to Rani Chennamma University, I was fixed to some extent. I should work for only one heterocycle, and I should develop chemistry with that heterocycle, and also investigate those heterocycles, those derivatives of those heterocyclic molecules for pharmacological investigation. So we selected indolizine. So this is actually indolizine molecule. It's very analogous to indole, and we know that indole constitutes very important scaffold for all drug molecules which are presently available in the market. Like this indole, this is indolizine, wherein nitrogen is in the bridged this one, and we selected this because of some reasons. When I selected this indolizine for the first time, that time Chinese people, Chinese scientists, they produced 200 to 300 papers, patents in a single year. So that made me some interesting fact about indolizine, selecting indolizine for my research field. So when I moved to Rani Chennamma University, I took another fresh batch of PhD students, wherein I allotted indologene framework for the synthesis and investigation of pharmacological activities. And of course, nature is the best guide for us, all of us, and it gives the base molecules for investigation of the various drug scaffolds. So this indologene moiety is present in the frogs, so like dendrobates, poisonous arrow frogs, then monomorium ants, then dendrobium orchids, tailofare. These are the plant products and animal products wherein you get indologene moiety. So this motivated us to go for the synthesis of indologene. There are several, of course, this was first synthesized by Scholz in the year 1912, and there are very many pathways wherein we can build this indologene molecule. So these indolegenes are, they are very good anti-diabetic, antimicrobial, anti-inflammatory, then gastric motility stimulatory indolegenes, central nervous system depressant indolegenes, antioxidant indolegenes, anti-cancer indolegenes, anti-tubercular indolegenes. So because of these pharmacological activities, we wanted to build some indologene derivatives so that we can test them for various biological activities, but we try to concentrate only on anti-tubercular activity and anti-cancer activity. So there are many methods available, but we chose, we were chosen this method wherein we have a pyridine nucleus and the phenacyl bromide, and we get, when we treat these two compounds in acetone and stir, we will get pyridinium salt, and this pyridinium salt, when we treat this with electron withdrawing alkynes, so you are going to get these indologene derivatives. Here I selected this method because of another reason. These are all room temperature stirring reactions, and you will get good crystals, highly crystalline compounds you are going to get. So that's why I chose this method. What variations we can do in this scheme is, we can vary the substituents on pyridine. Of course, phenacyl bromides, we have substituted phenacyl bromides wherein we can have different R groups here. One thing is, we will get pyridinium salt, and this pyridinium salt is treated with electron withdrawing alkyl groups. We try to concentrate these and we try to vary these groups also, and we got beautiful indologene molecules, and in this method, especially in this method, we got yields up to 74%. Then what we did is, of course, this is the mechanism wherein we can, we have confirmed it spectroscopically also. And what we tried to do is, I introduced one more electron withdrawing group for this alkyne. So fantastically, it was encouraging that, yields were up to, 90%. So earlier yields were 70%, but now because of two electron withdrawing groups, yields were increased up to 90%. Then what we did is, we tried to substitute this alkyne with electron donating group, and yields were decreased, only 50% we got. And then we tried to substitute that alkyne with electron donating methyl group, yields were just 40 to 45%. So from this we came to the conclusion that if we have electron withdrawing alkyne groups, then yields will be higher, and if we have electron donating groups, then yields will be decreased. We tried it with one more electron donating group, so we got only 30% yield, 30 to 40%. So that's why we have an established this one, that we have, when alkynes are substituted with electron withdrawing groups, you will be getting high yield. And what we did is, we tried to react that pyridinium salt with alkenes. So alkynes you get good yield, but we tried to go with alkenes also, but the yields are not encouraging. So we got initially we got unaromatized product. Finally, we aromatized it using chromium oxide, and the yields were just 30 to 40%. Then what we did is we tried to do some variations in pyridine. We put methyl group, electron donating group, in this pyridine molecule at para position. Then we tried to do the same reaction with electron withdrawing alkynes. Yields were up to 94%. Again, suppose if you go for electron withdrawing group, yields were reduced. Yields are reduced. So with the same molecule, yields are reduced. And then what we did is, we tried the same reaction with water. Earlier we were using only DMF and then potassium carbonate. Then we tried with water, and interestingly we got 60 to 70% yield, and we published it in tetrahedron letters. So this was the beginning of our indulgence in chemistry, and this motivated us to go for the synthesis of various other indulgence derivatives and the methods. Then what we did is, we tried to of course. So this is with for this nitrogen we have acetyl group at para position. So we got 60 to 68% yield. Suppose if it is at meta position, so we got two types of isomers, because that electron withdrawing alkyl group, it may undergo reaction here or here. So based on that we got two types of isomers. We separated them, and one was present up to 55% and another was just 6 to 10%. So this is one more attribute, and we tried to have this electron withdrawing group at 2 position, that is ortho position. Then we got excellent yields. So we varied this electron withdrawing group at para position, meta position, and then ortho position, and we came to the conclusion that ortho position, whenever we have substituent, whether it is electron donating or electron withdrawing, if it is at ortho position we get good yields. So then we try to extend that indulgence synthesis by using cyanides. We used cyanoethyl format for the first time, and we tried to look at whether we get the products. These are imidazopyridines. So whether we get the products or not, we try to get it. But very interestingly, with cyano group also the same chemistry worked out, and we got 2 isomers, because CN it can react in 2 ways to form one isomer like this and another isomer like this. So these are imidazopyridines, and using single crystal SRD we identified that this is the first isomer, and this we published in Asder Pharma at that stage. And now we are moving ahead. So we started making variations with pyridine also. We have introduced one more ring, that is quinoline. We tried with quinoline also. With quinoline we got interestingly high yields of pyrroloquinolines. Now you don't get indologine, but this is actually chemically it is pyrroloquinoline, but here we have this indole nucleus. So therefore we tried to introduce benzene ring, and then we tried to introduce 7-membered ring. There also we got indologines, and now we have developed so large chemistry of indologines has been developed so far now, and almost 50 papers we have published in various journals like JMS, Der Pharmachemica, Chem Select, etc., etc. Yeah, and by the research experience that we carried out during the synthesis of indologines and the pharmacological activities of indologines, we came to the conclusion that with imidazopyridines, based on our research experience, we came to the conclusion this is the drug prejudice which is responsible for anti-cancer and anti-cancer and anti-tubercular activity, because we have collaboration with the Durban Institute of Science and Technology for this anti-cancer and anti-tubercular activity, and we have collaboration with NITM also in Belagavi. This is the drug scaffold and drug prejudice, and this is actually bioactive pharmacore. When we introduce, first time when we synthesize imidazopyridines, we try to connect this oxazole moiety with this, and we interestingly we observed that this oxazole moiety, when it is connected to this imidazopyridine, was found to exhibit enormous anti-tubercular activity especially, and this we have published in recently in JMS, and we are trying to work out different substituents with this imidazopyridine. And another thing is this we also try to introduce this group with the imidazopyridines so that it will enhance the biological activity. We have given it to again Durban Institute of Science and Technology for biological activity. So what we do is usually we go for molecular modeling studies and then in silico studies for first we confirm the biological activity with those studies, and then we will give it to Durban Institute of Science and Technology, and they will go for the in vitro activity, in vivo activity, and finally we publish the paper. This is how we have developing indulgent chemistry, and especially imidazopyridines. So they have exhibited, these imidazopyridines, they have exhibited anti-tubercular activity 3 times more than the standard. So this we are going to cellular level. It has been already it has been sent to Durban Institute of Science and Technology for collaboration. We are moving with this imidazopyridine derivatives. Thank you very much.
Thank you very much. Next, Kapuria sir. Okay. So the next in line we have Dr. Naval P. Kapuria. Dr. Naval P. Kapuria is a distinguished medicinal chemist. Pooja madam, હું બોલું? Thank you. Dr. Naval P. Kapuria is a distinguished medicinal chemist and professor and head Department of Chemistry and Forensic Science, Bhakta Kavi Narsingh Mehta University, Junagadh. Recognized for his significant contributions to medicinal chemistry, synthetic organic chemistry, anti-cancer drug discovery, and multi-component synthesis. His research has advanced the design and development of novel bioactive molecules with therapeutic potential. With over 50 international research publications, 7 patents, 3 granted, 2 books, and the successful guidance of 6 PhD scholars, he has made notable contributions to chemical sciences. His scientific excellence is reflected through prestigious international research fellowships at Academia Sinica, Taiwan, the Ohio State University, USA, as well as his discovery of Su-novel rearrangement. So, sir, stage is yours for 15 minutes.
Thank you.
Yeah.
Thank you. Thank you for, I'm audible? Yes. Thank you, sir, and thank you, CRS, for giving this opportunity and especially bestowing the silver medal. I'm very thankful. Sir, I think there are two types of questions asked to the researcher. Number one, what to do, I mean, what you have done and how you have done. So I will answer the first question, what you have done, because how you have done take a lot of time. So here we have only 15-20 minutes, so I will just go through entire my works, what I have done so far. So basically my work is on multi-component reactions. We know the multi-component reactions are extremely useful for number of diversifying heterocycles, bioactive scaffolds, and so and so. And there are number of reactions are there. But there is a challenge is how to get new scaffold incorporated, how to get new substrate in there and make a diversified heterocycles, diversified drug candidate, API, and like and so forth. So my work is on the sustainable multi-component reactions. Why I'm interested here, because you all know that David Macmillan has got the Nobel Prize for the discovering his pioneer work on the organocatalysis especially. And organocatalysis plus multi-component, that a lethal combination for making a diversified natural products, diversified molecule in the scaffold. And that's why you can see the number of publications are increasing. So my second part is organic sensors. Now we know that organic chemosensors are nowadays very important because it not only provide the efficient sensing of the different analytes, but it is very easily we can prepare compared to the traditional pathways. Okay. So my laboratory, my students, we are working in these two phases. Number one is the construction of bioactive molecule. Basically I am interested in this enamine chemistry, which can diversify the number of heterocycles, which can diversify the different scaffold to get new compounds. And second, we are working on the different chromophoric moiety. So basically we are applying MCR, multi-component reaction, to prepare the chromophores, which can be utilized for the chemosensing applications. And I'm going to show you the highlight of 5 or 6 my recent publications and their results. Okay, so today I'm going to talk on these 5 research part that recently we have developed. Access to bioactive heterocycle from the MCR, and second one is access to organic chemosensor through multi-component reaction. Okay, so first one, chromines, we know that it's very important and its preparation always take a little bit difficulty, especially in the yield as well as the separation of isomers and so and so. So we have developed a organocatalyzed, or I can say bifunctional catalyzed reactions, which can easily produce at room temperature, which otherwise require a drastic condition heating as well as separation of water, which is forming through this reaction. But we have done it DMS or room temperature. So we have set a number of examples. It's very important, as I said, number of bioactivity is related to this molecule. We have tried number of reaction condition, and finally we came up that pyrrolidine plus a little bit of weak acid is sufficient to catalyze this reaction. And we try to incorporate the isoprene unit, which is specially for the vitamin E derivatives. So with number of derivatives we have prepared. We have also done the spirocyclizations, where spiro compound can also be prepared from these organocatalyzed transformations. And this is the mechanism. Basically it is a mix of aldol plus Manning type reaction, where alpha proton is abstracted and then cyclization go through Michael addition. This we published. Second, my work is to prepare the anti-diabetic molecules, especially we are focusing on alpha amylase, glucosidase, as well as dual inhibition of the alpha amylase as well as glucosidase. So recently we try to find out the new molecule in this heat compound. So we utilize the chromine moiety and utilize the diol amine, especially bis diol amine, and we constructed this moiety through multi-component reaction. So here again we tried to do the different several trial, and finally we found that the secondary amine is sufficient without solvent. Under solvent free condition we have synthesized these different molecules. We have evaluated for bioactivity studies, especially the anti-diabetic property. And we found that compound with para-chloro as well as 2-chloro. They are the lead compound from this series. We have tried to evaluate the mechanism, and we found that this compound is competitive inhibitor of the glucosidase, and it was a wonderful active as compared to the standard, which is acarabose. And also we have done with the in silico study, and this paper we published in the Journal of Molecular Structure with this competitive inhibitor. Next is my second work, where we are focusing on MCR to design the different chemosensing agent. This is very recently developed field in our laboratory. So we utilized a simple commercially available material to construct a 3-component condensation to get a phenazine molecule. Now this phenazine is very important because it is the highly conjugated system, and also it has a shuffling of electrons available due to the resonance. So after different catalytical applications, we find out that the heterogeneous catalyst PEG is sufficient to drive this reaction. We prepared a number of modification, number of different functional group, and to see whether which one is giving us better photon derivative we have done. And this is the very important fluorescence property of this molecule. You can see that every functional group has a different color, right? Can you see this color? Yes. So especially this is the fluorescence data, and we can see that this compound with 4-bromo was the highest fluorescence active. Of course, it shows the large stock shift, which is important for any chemosensor. Fine. So having this, we try to find out what is the application of this. So we found that this molecule can selectively detect the picric acid. The picric acid is an explosive material, and it has been also toxic to the cell. And we found that this material, picric acid, can be detected by our sensor very easily. You can see that the other acid, like different substituted acid or phenols, they were not detected. Only picric acid was able to off the fluorescence. So there is a fluorescence off on phenomena. So we found that this compound can wonderfully off the fluorescence, and the limit was up to 4.1 micromolar. Fine. So next, our target was to prepare again new fluorescence molecule. So we use the same easily commercially available starting material, but now we have tried to apply the pyrene moiety, because pyrene is also itself is a chromophoric group. So we use the multi-component reaction again to find out and make a highly conjugated system which has pyrene, pyrazole, as well as benzimidazole system. Now look at this, the property of this molecule. This molecule again, so wonderful solvatochromatic property. In different solvent, it gives different color, right? And also we find that if we can use the iodine when we try to check the application, especially the sensing, the iodine can easily off the fluorescence of this compound. And we also try to do the cell imaging study, whether it can imagine the cells. So especially MCF7 cell cancer cell line was utilized, and we found that yes, it can imagine the cancer cell as well. This manuscript is under preparation, and hopefully we'll submit. We'll get the under review. We'll get the result. Third part is on pyrazole base. I am skipping the synthesis due to time, but out of this. As you can see, that wonderful thing happening with this is this pyrazole, when aldehyde is there, there is no fluorescence. But once you put the another double bond with conjugation, immediately fluorescence turn on. And again, we treated with different anion, and we find that it can also detect the iodine at very micromolar concentration, and it can work as iodine chemosensor as well. This is the different properties of the photo-optical properties of this compound. Large stock shift, as I mentioned again, and concentration dependent fluorescence activity. You increase the concentration, fluorescence increasing. Similarly, the interference study we have done, whether this compound can work with the other anion in the presence of other anion or not. So indeed, it's also work in the other anion presence. Still, it can retain the detection capacity. And this is published in the results in chemistry. Another reactions, multi-component reactions we have applied to prepare another chemosensors, which is specially based on the quinaxolone moiety. We are interested in this quinaxolone moiety because once you attach with the thiosemic carbazide unit to this ketone, then we have a chromophoric unit plus we have a binding site for the different ions. Now these different ions can react with this, and you can see here the cation and anion. I can tell you that in the literature, most of the case study you will see either detection of 2 cation or 2 anion like that. Maximum 2 it can detect. But here this compound can detect 19 analytes, 19, including cation as well as anion, with distinguished color. You can see the visible color. This is a visible light. So you can see by naked eye the different color. That means when you want to detect the copper, you can just add our reagent and you can compare the color and you can understand whether copper is present or not, Fe is present or not, and so and so. Similarly, wonderfully with anion, you can see the carbonate detection. Carbonate is always difficult to detect because it's low acidity, but here this compound can easily give the blood red color with the carbonate, right? So we get the 19 analyte, just one compound can detect it. Now this is the different color change and also the shift of the lambda. A lot of shift you can see, and of course it going to the visible region. Now to enhance the utilization of this, we try to prepare the paper strip like pH strip, whether we can do this or not. So we have prepared the different anion cation solution, and we have prepared the strip, and deep into it you can see the wonderful different color with the different metal sensing capacity of this molecule. So finally we got the patent for this, granted patent for this molecule, as well as it is published in the JMS just recently, couple of months before. Apart from this, I was also interested to develop the new methods for the aza-indole because it is very important molecule for the number of bioactivity. Especially the 2 aryl function groups. 2 aryl function group is always difficult because most of the case indole has arylation on 3rd position, which is most active position. So here we have been able to do this by reverse Hamsterberg reaction. So here what we have done is we have done the cyclic azide, and we can activate this H on the alpha beta unsaturated carbon, and through nitrine we can insert the nitrine and we can cyclize this to aza-indole. So of course we have tried number of reaction conditions, and finally we found that there is a Doutham which is known as a eutactic solvent, which is a eutactic mixture of biphenyl as well as diphenyl ether, and when we heat them we can, without catalyst, without metal, we can insert the nitrogen, and we get a number of derivative from this. A number of functional groups has been tolerated, and we also been able to make the single crystal from this compound as well. This is, this is the mechanism which we are showing. I'm showing insertion of nitrine and then cyclization. This also we get the process pattern for this preparation of 2-aza aryl indoles, as well as it was published in the RSC recently. So summary, I want to say that we have sufficiently showcased the number of applications of MCR we can do with the bioactive molecule. We can prepare the sensors, chemosensors, and their applications. Finally, as I mentioned in my introduction, this is the one of the name reagent that is named for my professor Sanlong Su, with whom I work in Taiwan. And this is also in the app known as a reaction flash. You can just search the name, you will find this rearrangement. Finally, I want to thank all the students sitting here, because in every researcher's life there is a life cycle, life cycle where I can say you do the work in the lab and you speak, and then second stage your student do the work and still you speak, right? And third stage is there where nobody doing the work but still you speak, right? So I think I'm in the second stage, not in the third stage. And due to my students' entire effort, we have been able to do this work, and many more is coming, and hopefully will present in the future as well. And thank you, CRS, for giving this opportunity. Thank you very much.
On the behalf of Chemistry Department, Saurashtra University and RASAYAN-23, we are thankful to Professor Kapuria for his insightful talk. Thank you very much, sir. હવે કોણ છે? ગૌતમ ઘોષ. We have a third talk in this session by Dr. Gautam Ghosh. Dr. Gautam Ghosh is a scientist at Center for Nano and Soft Matter Sciences, CNS, Bangalore. He obtained his PhD from University of Calcutta and carried out postdoctoral research at Indian Association for the Cultivation of Science, ISC Kolkata, the University of Münster, Germany, and Jawaharlal Nehru Center for Advanced Scientific Research, Bangalore. His research focuses on supermolecular self-assembly, soft matter, liquid crystals, hydrogels, piezoelectric materials, something electric came. I am from the electronics, so some similarity. Piezoelectric materials, organic nanomaterials, luminance material, and supermolecule catalyst. He has published 44 research papers, has over 1200 citations with an H index of 18, and has filed 1 patent. His achievements include recognition of ChemCom Emerging Investigator 2026, appointment to the Early Career Researcher Editorial Board for Wiley's Polymer Portfolio 2025, recognition as the Rising Star 2024 by the Society of Polymer Science, Japan, ANRF Ramanujam Fellowship 2023, and the Institute of Scholars Young Researcher Award 2022, and finally the VD Good Young Scientist Award 2020. Sir, session is for you. 15 minutes.
Yeah, I'm audible, right? Yeah. First of all, I would like to thank CRS Secretary and Chairman for considering me for this bronze medal, and I would like to thank Saurashtra University for hosting this program. So today I will be talking about peptide-based piezoelectric material, nanostructural and chiroptical behavior, how it can modulate the piezoelectric response, that I will discuss. But here I will not explain the experiments and all these things. Simply I will tell what we do in our lab. Basically, we are supramolecular chemists. So supramolecular chemistry means it was termed as beyond the chemistry of the, beyond the molecular chemistry actually, by Jean-Marie Lehn, who mentioned it during his Nobel Prize on supramolecular chemistry. So basically, we are working on molecules that can assemble and make different nanostructures by their non-covalent interactions. Non-covalent interactions such as hydrogen bonding, pi-pi stacking, electrostatic interaction, different interactions, like it will make the different nanostructures, and then it will show different material properties. So but here we are particularly focusing on peptides. You know, peptide is a biomolecule, so that is relevant to biological system. And electronic things, so we can think of some bioelectronic in future. I will come to that slowly. So this is my title I am talking about first. But before I go to my main slides, I just would like to introduce my institute. I am from Center for Nano and Soft Matter Science, Bangalore. And this is our institute, very small institute, this institute, but we are having state-of-the-art, facilities. So I would like to invite all of you come and visit our institute. So now, as I mentioned, my main topic is on piezoelectricity. So now, first of all, I would like to say what is piezoelectric material. So piezoelectric material is a substance that converts mechanical stress into electricity. I mean, if I walk now, and if I have a piezoelectric material, then it can generate electricity. By this technique, recently, I don't know whether you might have seen that Japan, they made a road on piezoelectric material. And anyway, in the daytime, people has to walk on that. And during that walk, they are giving some mechanical stress on the road. And it is actually transforming the electricity. And you see, in the night time, then they don't need any electricity separately. So they can utilize that stored electricity and they can utilize as the electricity. So here actually you can say then how can be, it can be possible with the peptide. No, not at all. Peptide is not for the road. That can be useful for the biological system. But now what happened actually, all the molecules contain a random orientation of dipoles. So when you give some, it's okay? Yeah. So this random dipole orientation is there in the molecule. So when we stress, they give the voltage and all these things, then they will show different orientation. That orientation, and at the end, if it need dipole moment is there, then it will show the piezoelectricity. But now, what is the criteria for a molecule to or molecular structure to be piezoelectric? It should be lack of centrosymmetry, polarizable bond, aligned dipole, mechanical flexibility, anisotropic properties, and crystalline order. So these are the characteristics of a molecule to be piezoelectric. And application, you can see energy harvesting, sensors, actuators, renewable energy, and medical devices. So these are the common thing that piezoelectric materials and inorganic based piezoelectric materials are available in the market, and polymer based also it is available in the market. So now, in the first example, we'll show how peptide, one single molecule, we can make different nanostructures from the single molecule and how it behaves with the piezoelectricity. So in this case, if you see, we have synthesized this peptide in solid phase, and this chromophore actually we have included because of the pi-pi interaction, and a lot of amide bonds are there. They will actually interact by hydrogen bonding. So I will not go to details. So these are the various spectroscopic technique where we have showed that how it forms the self-assembled structure. And if you see that when microscopy, we found that molecules self-assemble into water, into short nanofiber in water. So this is the structure in the assembled state in water. And we are also curious about when we'll add some co-solvent, then how they change, because what I mentioned that our main goal is to change their nanostructures dimension. So here, when we have seen, we have started adding some co-solvent that can break the assembly, and slowly we used add a lot of co-solvent, and we found, if you see that the blue one, it is showing a CD signal. CD means it's a chiroptical, supramolecular chirality is showing the CD signal, means the molecules are packing in a helical fashion. So interestingly, when we added the co-solvent, you can see slowly it turns into opposite. So it's called chiroptical switching is happening. And interestingly, when we check their morphology in the microscope, under microscope, we found that short nanofibers become entangled nanofibers. So it's a change actually. So depending on that. So here chiroptical switching is also happening by adding the co-solvent. Now after adding little bit of co-solvent, then we heated the sample. When we added 20% of DMSO as a co-solvent, you see that short nanorod becomes small particle. And after heating and cooling back, we are getting this entangled nanofibers. So if you see, now we are getting different dimension, these and these. After heating, if we get different structure, we can consider that this system, this after heating, these nanofibers are thermodynamically controlled, because if we go back to our BSc chemistry, like chemical kinetics, that the product which forms fast is called kinetic state. So in this case, we can say it forms fast. That means it is a kinetic state. After heating, it transformed into the thermodynamic state as an entangled fiber. So the same molecule in two different states, two different condition, particle and the fibers. So in this case, then we have like we have shown our curiosity. If we check their material property, then we checked that piezoelectric behavior by piezo force microscopy, and we found that the particle, that kinetic state, it is piezo inactive. There is no such characteristic butterfly loop for the kinetic state. But when it is longer fibers, then it is showing this piezoelectricity. So here we have shown how nanostructure can tune the piezoelectric behavior of the peptide. So these are the overall work for this. This paper has been published in Chemical Science in 24. So now another system. Here what we have done, we have also synthesized another molecule, and we want to see how we can change in a different manner. If you see that previous section, I have mentioned that how nanostructures dimension can tune the piezoelectric behavior. And in this work, we have shown how chiroptical behavior can modulate the piezoelectric behavior. Chiroptical behavior means that how molecules are packing in a helical way. Depending on that, actually the piezoelectricity can be tuned. So, so in this, we have synthesized one molecule. Here also it is tetrapeptide, but if you see, here it contains the negative, like a carboxylic acid. It's called aspartic acid. It's an anionic peptide because all are anion here. So this molecule, when we self-assembled, it also form entangled fiber. But interestingly, when we check their chirality by circular dichromosome spectroscopy, we found that it is not there. Means, you see, this molecule itself, intrinsically it is chiral, but supramolecular chirality was 0. That means molecule didn't pack by helical fashion. And we have synthesized one more molecule exactly structurally similar, but it's a cationic. You see, exactly same. Instead of these two acid, we put some two amine, lysine motif. This is cationic. And interestingly, when we have checked their morphology, that also we found like short fibers, like one dimensional, but it's a short nanofibers. But when we checked their chiroptical behavior, we found that this molecule is showing strong chiroptical behavior. That means they are packing in a helical fashion in water. So very interesting thing that both are chiral molecule. In water, one is showing chiroptical supramolecular chirality, or you can say macroscopic chirality, but another is not showing the chirality. So this is very interesting fact. And then again we introduce co-solvent. Let's see what happened. Very interestingly, that whatever I mentioned, that anionic peptide was CD inactive in water, but as soon as we introduced little bit of DMSO, then you can see that the CD signal, strong CD signal came. That means that DMSO actually helped the molecular organization to reform in a different way so that they can pack in a helical fashion, and their morphology remains same, means entangled fiber. And the second one that I told, the cationic peptide was chiroptically active in water. As soon as we are adding DMSO, then it becomes CD inactive, keeping their morphology almost similar, like fibers. So what we found here, that all the conditions, this molecule self-assembled into nanofibers. So they are morphologically completely same. But what is the difference? Difference is the chiroptical behavior. Whenever one particular molecule is in water is showing chiroptical inactivity, but in presence of DMSO it is active. And the other way around. So now we have tried to check the piezoelectric response. Then interestingly we found the state what was CD inactive, that was piezo inactive. So if you remember that anionic was in water inactive, CD also
their piezo also inactive. But when we are adding DMSO, then it becomes CD active, and this is also piezoactive. And the same thing happened for the cationic peptide. The CD is completely related to, I mean, chiroptical behavior is completely related to this, piezoelectric behavior. So this is the thing. So they have a good deal with chiroptical behavior and the piezoelectricity. So thus another 1 minute I will take. Just the second one, the cationic peptide, that whatever I mentioned, that is also inherently showing piezoelectricity. But now our goal was to enhance the piezoelectricity, how we can enhance. So here what we have done, so already I have shown that it is forming short fibers and piezoelectric behavior. Then we introduced a metal organic cage. Actually, this is we got it from Professor Taposhkar Maji, JNC sir, Bengaluru. From him, his group we took this metal organic cage, cube. And it is actually at every corner 2 carboxylic acid, means anions are there. So these anions, because they already have shown that these anions can bind and then form different things. When we have introduced this peptide, that peptide can bind with all the acid, and they can completely change their orientation. And they enhance their piezoelectricity. Just see, previously it was 21.6, but after addition of this MOC, it forms 42.8. And very interestingly, I am telling you, whatever molecule I have shown now, that it is actually showing similar and even better result in terms of the commercially available piezoelectric materials called PVDF zinc oxide. So these are the things. This is actually one part of our work actually. So mostly recently we introduced and we established these things, and different ways are also coming. So in summary, the first one was that dimension of the nanostructure that can tune the piezoelectric behavior. Second, that chirality plays the role to tune the piezoelectric material. And the third one, that extended hydrogen bonding by the metal complex can also change the piezoelectric material. So my sincere thanks to all my collaborators, CRF, and definitely my students. I discussed about the papers of this lady and this guy actually who did this work. Yeah, thank you. Thank you very much. Thank you, sir.
Thank you very much, Dr. Ghosh. On the behalf of Chemistry Department, Saurashtra University.
I must mention, with the permission of chair, that this is one of the phenomenal work that has been recently done. Piezoelectricity from peptides is something amazing. I think in the days to come you do well. And I'm coming from the same institute. I'm a very senior colleague, he's a junior colleague. Junior colleague is doing better than a senior colleague. Thank you.
Thank you. Next 3 session introduced by Dr. Megha.
So, good afternoon, everyone. Next speaker in this session is Dr. Ashish Kumar Satpathy, Scientific Officer H, BARC, Mumbai. Dr. Ashish Kumar Satpathy is distinguished electrochemist and scientist, renowned for his pioneering contribution to electrochemistry, electroanalytical chemistry, energy storage, and hydrogen generation technologies. His innovative research on electrochemical interfaces, scanning electrochemical microscopy, supercapacitor materials, and photoelectrochemical water splitting has significantly advanced sustainable energy conservation and storage. He has also made notable contribution to the development of advanced electrode materials and the understanding of interfacial electron transfer processes. As Secretary of the Indian Society of Electroanalytical Chemistry and regional representative of the International Society of Electrochemistry, he has played a key role in promoting electrochemical research. I welcome Dr. Ashish Kumar. He is not here? Okay, I'm so sorry. The session is online, so we'll just start. I think he is with us, right? He has connected? Okay, okay. So please, let's wait for some time. Yes, it's on time. So we have some difficulty in connecting with the speaker, Dr. Ashish Kumar Satpathy. So meanwhile, we'll take opportunity and move to next talk. This once we'll have a connection, we'll arrange this talk. Okay. So next in this session, we have silver medal awardee and our very own Professor Ramesh K. Kothari from Department of Bioscience, Saurashtra University, Rajkot. Professor Kothari is distinguished microbiologist, academic leader, and professor and head of the Department of Bioscience and coordinator of the Institute of Biotechnology, Saurashtra University, Rajkot. Renowned for his pioneering contribution to environmental microbiology, probiotics, agricultural microbiology, and microbiome research, he has significantly advanced microbiome science through innovative research and academic leadership. With over 72 research publications, 4 books, multiple funded research projects, and 3 patent applications, he has mentored numerous doctoral and postdoctoral scholars. His outstanding and achievements have been recognized through the Bill and Melinda Gates Foundation Travel Award, DSTACRB International Travel Award, and Best Educationalist Award. We welcome Professor Kothari. The floor is yours, sir.
Good afternoon. 15 minutes, ne? Okay, no problem. Good afternoon. A difficult session after lunch, I know. Medicine, respected panel, member of panel and my invited guest and my dear students. I'm going to speak on microbes as medicine. And it is emerging trend in future direction of probiotic research. Now we know that the air we breathe, food we eat, water we drink, touch a place anywhere, microorganisms are everywhere. It has omnipresence. If we weigh the in and outside of our body, approximately 1.5 kilogram microbes are there. It was said that it was said in Gujarati or in Hindi, I would say, Jaisa ahar aisa vichar. It is scientifically proved now. So this is something on this probiotics. I'm going to discuss briefly on this. Let me start with global disease burden. If we see in therapeutic gap, more than 7 lakhs death per year are happening due to antimicrobial resistance. So microbes are developing resistance day by day. Approximately 10 million projected AMR death will be there by 2050. 19.3 million cancer cases which are already diagnosed in 2024, and 50% antibiotic resistance rise last decade. Now you see the magnitude of the resistance developed by microorganisms. If you see the rising AMR mortality trend, you can see the scenario, what will be at 2025. So why there is need of probiotics? Because rising failure of conventional antibiotics, one antibiotics treatment for a particular disease is not effective for other patients. Fine. So there are many chemical candidate in market, but their effectivity is decreasing day by day. Antibiotic side effect and microbiome disruption. Simply antibiotics is not killing the harmful microorganism, it is killing useful microorganism also. At the same time, it is disturbing microbiome diversity and dynamic, and that is affecting indirectly to individual health. Need for safe targeted alternatives. We know that anyhow the chemical molecules are long way, they have some detrimental effects. So if you take antibiotics, it is very safe. At the same time, growing consumer demand for natural therapeutics, you know that post-pandemic era, we all are now believe on naturopathy. So nutraceuticals are getting a lot of place in the market. And MDR pathogens, which invading all available drug classes. Whatever new drug you are developing, it is the antimicrobial resistance is already developed. So if you see the probiotics, we know that what are probiotics? We all know live microorganisms which when administered adequate amount confer a health benefit to the individuals. Now it depends. Many times, mostly in 99% probiotics, in our traditional way also, we are taking everywhere, wherever you are taking curd, buttermilk, it is a natural source of antibiotics, right? You will realize in India, a state, Punjab and Haryana, these are two states where the lifespan is very, very long. It is believed that they are taking plenty amount of this buttermilk and curd. So their gut microbiomes are more healthy compared to the other state. So if you see the historical milestone, so I'll not go much in detail, but if you see the key biotic genera, see key probiotic genera, mostly you will see, you might have heard about Yakult, which is already available in the market, right? So, and Yakult, at the same time, many times doctor prescribe medicine to small kids, even to adults also, when we are under treatment of antibiotics, to restore or to fulfill the harmful effect caused by the antibiotics. Fine. So lactobacillus species, it is most studied gut colonizer. Same time bifidobacterium, infant gut dominants. Bacillus species, it is spore former, heat stable microbes. Saccharomyces species, yeast probiotic, it is antidiarrheic. And Enterococcus faecium, which is safely classified as QS1. So these are already a successful candidate which we are using in our day-to-day treatment. Now, if you see the how to isolate and screen a systematic this type of probiotics, we adopt the, say for example, sample collection. From many different sources you can do sample collection, fermented food, dairy, soil, gastrointestinal tract, various type of fruit. Then you go for culture, then isolation based on using various microbiological media. Then you go for phenotyping screening, just like a gram staining, catalase and oxidase test, then morphological characteristic. Go for biochemical profiling. There are various biolog identification system. Are there more than at a time more than 45 to 55 biochemical tests based on fermentation we carry out, and tentatively we can assign genus and species up to genus and species identification. And probiotic validation. There are certain traits which a particular probiotic candidate should show to qualify as a probiotic cultures. So key probiotic selection criteria are: it should be acid tolerance, should be bile resistant, should have capacity to adhere in the stomach, it should have antimicrobial properties, should have antibiotic sensitivity, and at the same time it should be safe. Now as far as the safety aspect is concerned, it differs person to person, right? Now if you see the characterization from phenotypic to genome level, phenotypic, biochemical, molecular and functional. If you see the phenotypic, we can identify based on colony morphology, gram staining, then microscopy and various type of growth kinetics. Biochemical identification can be done based on carbohydrate fermentation and its enzyme profiling, as well as automatic biolog identification system. If you go for molecular identification, we all know it is 16S rRNA gene, and many other recent analytical techniques are available in the market. And for functional aspect, it is very, very important: hydrophobicity and the auto aggregation assay, biofilm analysis, and exopolysaccharide production. These are the characteristics that particular probiotic culture should show. Fine. So if we, as far as the hydrophobicity is concerned, higher the hydrophobicity, the higher colonization in the gut, so that it cannot wash out during the routine process. If you see the antimicrobial activity, again MD, multi-drug resistant pathogens, selected probiotics, there are certain isolates. These demonstrate the potent inhibitory activity against various type of pathogens. For example, inhibitory mechanism, if you see organic acid, lactic acid and acetic acid production, pH reduction, these are the actions that through which the probiotic show its activity. Bacteriocin production. Probiotic produce various type of antimicrobial proteins, and this antimicrobial protein serve the it carry out the function of particular antibiotics which carry out. H2O2 production, oxidative damage to the pathogens, competitive exclusion, niche and nutrient competition. In gut also, when we administer useful microorganisms, there is a environment of competition. So that characteristic is very important. And biosurfactant, membrane disruption and biofilm inhibition. The probiotic can compete, showing the effect of membrane disruption of any pathogenic microorganisms, right? So if you see this, I am showing this our original research. My students are there in this seminar. This work is dedicated to all my students. Three of my students are working on probiotic in the field of probiotics. These are certain original data that we have carried out. If you see the antibiotic susceptibility of clinically significant bacteria, we have isolated various type of bacteria, and we have tested the antibiotic assay. If you see the Staphylococcus aureus, Pseudomonas aeruginosa, Acinetobacter and Klebsiella, you can see the zone of inhibition shown by this particular. These are the antibiotics which were tested against this particular microorganisms, and you can see the size of zone of inhibition. So this particular antibiotics shows the sensitivity as well as resistance. Now what our result shows, that the antibiotics which were sensitive to that particular culture, our isolate, these are our probiotic isolate. Those antibiotics which are resistant to that pathogens, here they show sensitivity. So this qualify that this particular bacterial candidate is very much suitable for the probiotic as a probiotic. So surprisingly, we got very good results, and these are various our probiotic isolate, and they were tested again these particular pathogens. Antimicrobial activity, if you see these lactobacillus against multi-drug resistance, these are certain very encouraging results that we have found during our PhD research, and these are various isolate. One of my students have isolated various probiotic candidate using in various sources. These are the name of sources, and from where we have identified these many bacterial candidate, and these all are under scrutiny to qualify as a potential probiotics. We have also results that the probiotics are they have anti-cancer potential, and we have carried out in vitro assay. We have in vitro evidences that the probiotic microorganisms show anti-cancer activity. If you see the graphs based on, if you see the lactobacillus plantarum, if you see the we have tested, we have 3 human cell lines. We have conducted this experiment on we have conducted through MTT assay. We have selected HeLa cell line, HEP G2 cell line, and AGS cell line. You can see here, if you see the this point LD50. So at cell-free culture at 30 microliter concentration, it almost kill 50% population of this cancerous cell. So these results are again very much exciting. We have results for 48 and 72 hours, right? So this type of activity on different type of HeLa cell line indirectly indicate that they are potential anti-cancer candidates. We have analysis of flow cytometric analysis for anti-cancer potential in vitro evidences. If you see here, the we have 2 cell line we have tested. If you see in first graph, here it is control, both are control and these are tested. Yeah, okay. So this if you see in this particular test samples, the apoptosis is increasing like anything. Fine. So this probiotic candidate has potential anti-cancer properties. This was tested. These are results for 48 hours. The same it is for 72 hours. And these are the anti-cancer potential evidences on cell cycle. So if you see this particular in this HEP G2 cell line, it inhibits the synthesis phase, and here it is in G2 phase of the cell cycles. So these are again evidences. I'll shortcut this. So bioactive metabolite which are produced by these probiotics, these are bacteriocins, organic acid, exopolysaccharides, short chain fatty acid, biosurfactant, and enzymes and vitamins. These are the magic molecules which are produced by probiotics. Omic based probiotic research, if you see, the future is that genomic, metabolomics, transcriptomics, microbiomics, proteomics, and multiomics. These are the area through which we can work out, we can deeply study this. If you see beyond the gut, systematic health axis, if you see, nowadays the recent advancement says that gut-brain axis, and in addition to the gut, heart, and brain axis, these are the latest development. Even the fecal replacement therapy, it is also the latest development in this particular field. This gut immune axis, gut metabolic axis, and gut cancer axis, these are various latest piece of research, you can say. So clinically evidences, if you see efficacy and analytical insight, these are various conditions, and under this particular microorganisms have already been applied, and this is the outcome, successful outcome. Fine. So regulatory framework, if you see safety consideration, there are various safety aspect that, but safety assessment checklists you can see. So these are the conditions that if any candidate fulfill, then it is considered as a successful probiotics. And these are formulation, delivery, and industrialization. If you see the lyophilization, micro encapsulation, fermented food, functional beverages, pharmaceutical form, and symbiotics. These are various formulation aspect and delivery aspect that we can work on. And global probiotic market, if you see, by 2013 it will be around 160 USD billions dollars. Fine. So it is the future market for probiotic research. And next generation probiotic, if you see, these are various products which are already in its second or third human trial. Fine. And these are challenges, limitations, and research gap that particular in this particular field. And last, I would say future direction, if you see, precision probiotics, synthetic biology, immuno-oncology integration, clinical grade, then psycho biome research and industrial biotechnology. These are the latest area on which we can focus. So the key conclusion is that probiotica, I'll take 1 minute. Okay. So okay, so these are our publications, outcome of our research. We have published very good papers on this, and latest we got one research paper in 10.6 impact factor, and one paper is in gut microbiology with 15.3. So we have reached up to the pre-clinical trials, and we are finding opportunity to have the clinical trials. Thank you so much. Yes.
To keep our gut healthy, what we should eat?
We should eat curd every day. And should be part of our food planning. Thank you.
So our next speaker is Dr. Priyankar Paira from VIT Vellore. Dr. Priyankar Paira is Distinguished Chemist and Associate Professor in the Department of Chemistry, Vellore Institute of Technology, Vellore, renowned for his pioneering contribution to bio-inorganic chemistry, bio-organometallic chemistry, medicinal chemistry, and nanomaterials. His innovative research on ruthenium, iridium, and rhenium-based organometallic complexes has significantly advanced electrodynamic and photodynamic cancer therapy. With over 125 research publications, more than 3,200 citations, an H-index of 30, and several externally funded research projects, he has established an outstanding record of scientific excellence, a recipient of the DST SERB Young Scientist Award, and the ACMS Young Scientist Award, and a member of Editorial Advisory Board on Dalton Transactions. He has made impactful contribution to the chemical sciences. Please join me in welcoming Dr. Priyankar Paira.
Hello. Yeah. So, thank you very much for nice introductions, and I would like to thank to the CRS team and the Saurashtra University for honoring me here for the silver medal, CRS silver medal. So, I would like to talk about the stimuli responsive, the organometallics activation in the mitochondria, localizations in the mitochondria for the cancer therapy. So, yes, sure. Oh, okay. No issues. I'll stop now. Okay. No issues. and definitely organics and inorganic chemistry along with the analytical chemistry and also in the cancer biology. So we have developed our lab. Basically, we are involved in the interdisciplinary work with the help of various funding agencies. We have established the chemistry synthesis as well as the biological lab in VIT Vellore. So I would like to tell about these two our lead molecule. The first one is for chemodynamic therapy and second one is for photodynamic therapy. So I'm not going in details why cisplatins is not used nowadays, and there are a lot of drugs metallo drugs is already developed in the clinical trial. I'm not going on that. So I'm directly coming why we are involved, why we are using the organometallic complexes for cancer therapy, because the major advantages of organometallic compounds are this is having the lipophilic cationic group. Now, if you consider the cancer cell surface are mostly negatively charged, so most of the cancer cells. So, if we can design a molecule which is having the lipophilic cationic behavior, it will be attracted more towards the cancer cell compared to the normal cell. So, that is our main objective why we have designed the organometallic complexes. Okay. So, coming to that point, if we design the organometallic complexes, you can see here, two different metal is there. This is a heterobimetallic complex. It's very simple molecule is bipyrimidines. It's having two positive charge. So that means because of two different metal and the lipophilic group is present, you can see this is lipophilic group, this is also lipophilic group. So if it is lipophilic cation, the delivery will be much faster and it can cross the barrier, the cancer cell barrier, very efficiently. So as it is lipophilic cationic behavior of these particular molecules, due to endocytosis, it can cross this barrier and can enter to the cell, and then it can go to the either to the nucleus or can be mitochondria or any other body, but our target is on mitochondria. So now coming to another point. So why mitochondria? So mitochondrial surface, mitochondria is having the negative potential. So if you can design a molecule which is having the positive charge or maybe bipositive or more, then it will be the mitochondrial membrane potential, it will be localized to the mitochondria and mitochondrial membrane potential will be reduced and it will follow the mitochondrial pathway. So in our lab is involved in three different type of work. The first project is involved on chemodynamic therapy, second project is involved on photodynamic therapy, and then third one is the drug delivery. And these are all our associated publication in last few years, and these are the funding agencies which are involved, and they help, we got the funding from those funding agencies. Okay, so this is our group. So students are involved in different projects based on the molecules and also the different cell lines we have used, and then we have used different therapy like either in chemodynamic therapy or in photodynamic therapy. Okay, so now first I would like to show about what type of molecules we have developed for chemodynamic therapy. Okay, so first I would like to tell what is chemodynamic therapy. So chemodynamic therapy is a very simple thing. The molecule will generate the reactive oxygen species in absence of the light. And what is photodynamic therapy? It will also generate the reactive oxygen species but in presence of the light. So this is the difference, and we have developed the molecules or designed or synthesized the molecules for these two approaches. The first one is the chemodynamic therapy, and so this is our design approach. So this is the core moiety you can see here. So this is the lipophilic group, this is labyl chlorine, and these are the ligand. Ligand are mostly highly conjugated and planar, so it can intercalate the DNA. And this is the lipophilic part. So lipophilic means the molecule can target the cells and it can cross the barrier. And Cl, why the Cl is important? If you use the DNA base pair, so it can form the covalent binding with the metal and chlorine can be eliminated. So these are the 3 points what we involve in our project. Okay. So first what we did, we have screened several molecules we have synthesized, and then we screened in different cell line, and we found when you design or when you synthesize the molecule which is having highly conjugated ligand along with the ruthenium or iridium metal, it is showing highly cytotoxicity in the cell along with selectivity. So what is selectivity? So the molecules is targeting to the cell. So IC50 value is very low in cancer cell but very high in the normal cell. So most of the compound what I showed here, it is highly cytotoxic in the cancer cell and highly selective, and more than 30 to 40-fold selective in cancer cell. Okay, so that is the major advantages of this molecule. And then I would like to show here some of the molecule which is highly cytotoxic and highly selective. So the first molecule you can see highly conjugated ligand is there, IC50 in this cancer stem cell ACT116, it is 32 micromolar and selectivity factor is greater than 20, and it is localized to the mitochondria, and this paper is published in ACS Applied Biomaterials. Okay, so and most of the cases it is following the apoptotic pathway. We have done several biological study to prove that it is following the apoptotic pathway. Okay, and also it is how it is generating the reactive oxygen species. We have done the DCFDA study, so you can see the green fluorescence has increased after the drug treatment, so it means that it is generating the reactive oxygen species, and this is the approach. So for example, this is iridium molecule, so iridium is oxidized to form iridium 4 and it will release the electron. This electron is reacting with the H2O2 to form OH radical, or even it is reacting with the O2 to form the O2 dot, and that also been proved by EPR studies that O2 dot is forming or OH dot is forming in the cell. So that we have proved by the EPR study and also the DCFDA studies. And then coming to where it is localized in the mitochondria, and we observe that the mitochondrial membrane potential has been reduced. So it is depolarization in the mitochondria, and it is following the Bax pathway. So these two apoptotic protein, we know that. So Bax is upregulating, and whereas the BCL2 also upregulating, this is different behavior you observe this particular molecule, and that is why we confirm that it is not following the mitophagy pathway. So this is another molecule, very small molecule. You can see IC50 is 52, selectivity factor is 8, and whereas cisplatin is 50 micromolar, it is also localized into the mitochondria, and this paper is published in Journal of Medicinal Chemistry. Okay, so you can see, I would like to show you this result, how it is localized. You can see this particular case, you can see here this molecule is it is localized to the mitochondria, which has been tracked by MitoTracker. Pearson coefficient we observed 0.939, means 93% of this particular molecule is localized into mitochondria. So why? Because of that it is highly positive charge, and also this triazole unit. So this is interesting observations. If we incorporate the triazole moiety, the mitochondrial localization has been increased. Okay, and also it is following this pathway. You can see here NADH is oxidized to form NAD plus by the drug treatment, and it is releasing the electron. That electron is reacting with the H2O2 or oxygen to form the OH radical or O2 radical. So that can superoxide radical that are responsible for the cellular apoptosis. Okay, so we have also done the 3D spheroid assay. You can see here. So this is the diagram of 3D spheroid assay, where we can clearly observe the mammosphere formation has been reduced. So this is also very interesting result, and we observed that by we have also done the studies, and we observed clearly that the Bax is upregulated, whereas BCL2 is downregulated, and it is following the caspase pathway, and also can release the cytochrome C. We have done through the Western blot analysis. So that means it is following the apoptotic pathway. This is another interesting observation. So we know that in the cancer cell, GSH content is very high. So GSH has a role. So GSH can destroy the molecule. So what we observed there, by drug treatment, the GSH is oxidized to GSSG. So it has also been proved. We have done the mass spectrum. We have done the NMR spectrum. We clearly observe the GSSG peak is observed here, and also in mass spectrum we can also observe the GSSG peak. So that means the molecule is generating the reactive oxygen species, which can transfer the GSH or convert the GSH to GSSG. So this is also an interesting observation, and this is the mechanistic pathway. Similarly, we have also developed this molecule. I am not going details again and again. So this is another molecule. So it's showing the dual function. You can see here the ruthenium molecules and iridium both are there. We have synthesized. It is also following the caspase pathway, generating the reactive oxygen species, localized into the mitochondria. It is reducing the mitochondrial membrane potential, and also the antioxidant like ZN-SOD and CuSOD by the drug treatment, it has been reduced. So that means it is facilitating this particular pathway. Okay. So now coming to this interesting molecule, rhenium molecule, you can see. So all cases you can see these conjugations. Here one interesting group is there. This is carbon monoxide. So by the drug treatment, this molecule may integrate from here and can generate the reactive oxygen species from here. It is also lipophilic cation. It is showing the DNA intercalations. It is localized into the mitochondria. It is the redox behavior, IR3 and IR4 redox behavior is happening with this particular molecule, and similarly for rhenium also it is a selectivity factor is greater than 20, and this work is published in Dalton Transactions, and this recently we have done this work. It is communicated in JACS, and so this particular molecule you can see we have done the anti-metastatic behavior, because you know The vimentin is another protein. So due to anti-metastatic behavior, what is the role of the vimentin? So if you can downregulate the vimentin, the metastatic property of the cancer will be reduced. So by the drug treatment, we can see here, this is downregulating. So that means vimentin regulations has been reduced. So that means anti-metastatic behavior of this rhenium molecule we observe in this case. It is also localized into the mitochondria, and you observe the Pearson coefficient is 0.859. Now coming to this particular molecule, you can see here, so here also conjugation, but we have incorporated one halogen group here. So here also most of the cases of this type of molecule, we observe the dark toxicity 30 micromolar, and here also 20 micromolar in light, but we did not get very good result for that. So that is why for that we wanted to design some molecule which can show better light behavior or light toxicity. And so this work is published in JMET Chem in last year, and it is also following the mitophagy pathway. So I'm not going in details on that. And my third part of the project, I have already told why we need the drug delivery. Okay, so for that we have done only one work we have done in the last year. We use the carbon nanotube for the delivery of the drug, for the better delivery of the drug. So what we did here, you can see here, this is carbon nanotube is modified, carboxyl modified carbon nanotube is modified by biotin, because biotin is a receptor, so which is overexpressed in the cancer cell. If we can design in such a way, and then you incorporate the drug here, it will be more, the delivery will be much faster in the cancer cell compared to in the free drug. So that we did, and we observed that. So we observed that the accumulation is more in that case in the mitochondria. IC50 is much lower compared to the free drug, and this paper is published in the Chemical Communication. So far I have discussed about the monometallic complexes. Then we move to the bimetallic complexes. Look at here, different metal we have used here: ruthenium, iridium, ruthenium. So mixed metallic complexes we have used here. So very interesting observation we observe in this case. Yes, I'll finish. So very interesting result we observe in this case. When we move to monometallic to bimetallic complexes, the IC50 is much lower and selectivity is much higher because of the synergistic effect of this molecule. So this is also very interesting result, and we published this paper in the last few years. Okay, so I'm not going in details about that because all cases it is localized to the mitochondria. IC50 is low and selectivity factor is very high. We have also done the in vivo study with this particular molecule, and it is also showing very good result in the in vivo model, which is also been published in JMET Chem. Okay, so I'm not going about this. I'm directly going to my last part of the project. So we have last few years, we have also developed, these all are phototoxic drug, and most of the cases you can see highly conjugated and PI. So what is PI? So PI is phototoxicity index. The IC50 in presence of the light is much lower compared to in absence of the light, and we can see the PI level is very high. So if the PI level is very high, that means even if the molecule is delivered to the normal cell without light, it cannot work. So that means if PI level is high means thus it is much more selective compared to the CDT drug. Okay, so these are the molecules we have developed in the lab. Most of the cases you can see extended ring system is there, synergistic effect of two metal, lipophilic cation, attachment with the organic dye. Some cases organic dye we have also attached, and incorporation of the CO group. So these are the followed paper on PDT we have developed in the last couple of years. And this is the last part what we are currently doing. So this is very interesting molecule. We observed PI level has been increased to greater than 100, and you can see here this is bimetallic molecule with triazole. PI level has been increased to 500. This is very interesting result. And also you see this molecule, this also currently we are working here, also PI level is greater than 100. And this is the last part of my work. Here you can see this molecule, we have incorporated BODP. In this case, PI level has been increased to greater than 1000. This is very interesting result we observe. So this is the recent molecule, recent synthesized molecule in our lab. Okay. So last, I would like to acknowledge my PhD students. So these are the students who are working, and these all are my collaborator and the funding agencies, and these are my contribution in last 1 year. And last of all, I would like to tell about, I am the advisory board in Dalton Transactions, so I would expect more and more publications in bioinorganics and also in the inorganic chemistry. We are accepting the paper. And last one, we are also going to organize one bio-inorganic and inorganic chemistry conference in VIT Vellore. I am the organizer for that. So it will be in September 2027. I would like to invite all of you, and it will be circulated soon. Thank you very much.
meantime, we'll finish here. Okay, please. No. Felicitation means he has to give a talk under his chairmanship. Okay? Can you wait for a few minutes? He has gone to bring the laptop. Next year. Okay, we'll wait. Which department? Important. Mine. I'm 60. On. Minus 140. Minus 60. No, so, we'll take all photographs together. We'll honor her. I'm after doing this. You want to, you are there? You are there?
So, in this session, we have Dr. Sawan K. Majmudar. Dr. Majmudar is a distinguished physicist and professor at the Homi Bhabha National Institute, Rajaramana Center for Advanced Technology, that is known as RRCAT Indore. He is renowned for his pioneer contribution to the biophotonics, Raman spectroscopy, optical tweezers, nanophotonics, and phototherapy. His multidisciplinary research has advanced innovative optical techniques for rapid disease diagnosis, biomedical imaging, and light-based therapies for cancer and infectious diseases. Bridging fundamental science with the clinical applications, he, with his impactful research, high-quality publications, and leadership in translational healthcare technologies, he has made a significant contribution to biomedical optics and phonetics. With a large round of applause, I would like to invite Dr. Sawan K. Majmudar to deliver his talk. Welcome, sir.
Thank you for the introduction, though it was unnecessary. To begin with, let me thank CRS for honoring me with Silver Star Award, and also Saurashtra University for their nice hospitality and hosting this conference. So, I'll be talking today, I'll be now taking you through a different domain altogether, little bit our previous two speakers have already talked about. So, this is biophotonics. Now, before I start, let me tell you where from I have come. This is as I introduced that I am from Rajaramana Center for Advanced Technology. This is the Department of Atomic Energy Unit, and the motto of this our center is photons in the service of nation. And there are two mandates, you know, that particle accelerator and lasers. RRCAT is home to India's only synchrotron radiation sources. And that is called Indus 1 and Indus 2. And people, researchers from all over the country, they come here for their research in material science, bio, and other things. And this is a pioneering center, as you know, that lasers. It is a DA unit, and so we develop lasers and allied technologies. Now, there is a group called Laser Biomedical Application Division. So, you know, RRCAT is largely known as, you know, that Science, Physics and Technology Center, but this is a small group. That is my group. So, the mandate is R&D in the area of biophotonics. Now, what is biophotonics? It is a photonics for life science and health. You know that it is managed between photonics and biology. So, that photonics and biology, when they marry, then biophotonics emerges. And it is an emerging interdisciplinary frontier that deals with interaction between light and biological matter. Okay, that is the scope of biophotonics is very many. So, largely it is photonics technology for biomedical sciences either, or biomaterials for photonics technology. So, everything comes under these things: optical spectroscopy, imaging, photodynamic therapy, optical trapping, and so on and so forth. So, in laser biomedical application, the main mandate is R&D in the area of biophotonics. We do basic applied and translational research, and that lead to technology development. So there are two things: biomedical diagnosis and phototherapy. We do this is the mandate, you know. So R&D on the use of optical spectroscopy and imaging to advance diagnosis of cancer and other diseases like tuberculosis, malaria, etc. So we use different optical techniques like fluorescence, reflectance, Raman spectroscopy, imaging techniques like optical coherence tomography, then optical tweezers and micromanipulations I will touch upon, and phototherapy, that is photodynamic therapy of tumor, antimicrobial photodynamic therapy, and photobiomodulation. Now, before, you know that I am a physicist, so before we start biophotonics or we delve into biophotonics, the basic question one asks, how light propagates inside tissue. You know that in physics or in chemistry also, you are taught electromagnetic theory. So electromagnetic theory, that Maxwell's 4 equations, well-known 4 equations, any light propagation in a medium, you have to solve this Maxwell's 4 equations. But when you solve this equation, then you have an assumption that the medium has a unique refractive index. You know that this is known to everybody, refractive index. You know, so it is, but when you try to use Maxwell's equation or put Maxwell's equation in tissues, it is not possible because tissue is a turbid medium. Why? What is called turbid medium in physics? You know that when light is incident, light is a bunch of photons, you know that it is a, so most of the photons, they undergo multiple scattering. Only few fraction of the photons, they are called ballistic photons, they come straight without any scattering. And some photons, they undergo minimum scattering, that is called snake photons. But 90%, more than 90 to 95% photons, they are diffuse photons, they undergo multiple scattering. What is turbid? You know that, let me give an example. When you put a spoon in a glass of water, you can see that spoon. But if you start pouring milk in it, gradually you will not be able to see the spoon. Why it happens? You know that light, you imagine one photon which is incident on that glass of milk, milk with water, then they undergo multiple scattering before it comes out. So that poor photon forgets about its initial direction. So directionally totally lost. That's why you cannot see that spoon. So tissue is a turbid medium, that is an opaque medium. So that is when a medium is called turbid, that means photons undergo multiple scattering before coming out. So how we solve this problem, how light? So that is direct application of electromagnetic theory is not applicable, as I told. So we have to do it, that Professor Chandrasekhar's radiation transfer equation, for which he got a Nobel Prize, that came in to help, you know. And we solved that equation under many approximations, and then we found out absorption coefficient, scattering coefficient, elastic scattering, anisotropic factor. These are the 3 things. If you know these 3 things, then you can really know the optical properties of any medium. Okay. Now, simultaneously, you know that biomedical diagnosis using light, the hypothesis is that optical spectroscopy and imaging can improve diagnosis and therefore treatment of pathologic condition. So you will incident light on a biological medium, and the photons which are coming out, you just disperse it with a detector. That is the underlying mechanism. Now, why it is attractive or why it drew attention? Because real time, it can give you real time non-invasive detection of morphological and biochemical information. Okay. Now, you know that there could be 3 optical spectroscopic techniques, namely reflectance, fluorescence, and Raman scattering. Now, you know that reflectance is basically elastic scattering. When you shine blue light, you will see blue light without change in color. You shine red light, you see a red light. So that is the elastic scattering, and you use these things. This elastic scattering is very important. You know that by virtue of elastic scattering, we are being able to see each other. Light falling on you, reaching my eye, I am seeing you as you are, and vice versa. So this is being used in, unknowingly you are using this elastic scattering in everyday life. Even pathologists, they take help of elastic scattering to see the morphologic features of any cell. But by looking at you, I cannot make out what are the molecules which have made you up. So for that, I have to use inelastic scattering like fluorescence or Raman spectroscopy. So based on that thing, you have 3 different spectroscopic things. Diffuse reflectance, you will get this kind of spectrum. Fluorescence, you know that it is, if you incident light, different wavelength light on tissue, on same tissue sample, then this is the kind of fluorescence spectrum you will get. That is intrinsic molecules, intrinsic tissue fluorescence, the fluorophores or biomolecules which fluoresce, that intrinsically present in the tissue. So there are several biomolecules like amino acids, aromatic amino acids, structural proteins, collagen, elastin, coenzymes, porphyrins, they all fluoresce. So tissue fluorescence is a convolution of the fluorescence spectra of all these fluorophores. And Raman, you know that this is fluorescence, while fluorescence is a broad band, Raman is very unique, and it is a vibrational spectroscopic technique. It is unique to every molecule. As you know that when anybody walks, his walking style is different, and you can figure out from his back that this is the person walking. So every molecule has a distinct Raman signature. Okay, now for clinically applying all these things, the first requirement is, you know, that you have to have a portable diagnostic system. No matter what you do in the lab, how much excited you are, if you go to a doctor, they will not believe. They don't want to do research. They want a system which is user-friendly or doctor-friendly, you can say. So you have, this is the light source. You have to have a conduit which can guide this light to the biological matter or system, and then there should be a conduit which will take this light away, which is emitted from the biological system, dispersing element, the detector. Ultimately, you will get a optical signature in the form of either reflectance spectra, fluorescence spectra, or Raman spectra. Now, we developed several these systems, and this is the first system we developed, and that is a nitrogen laser-based system, fluorescence spectroscopy system, where the nitrogen laser, which emits a 337 nanometer, is the excitation light. And then that matured into a this is a very big system, trolley-based system. Then it matured into a second generation system, compact and portable version. Okay. Now, simultaneously, we also developed Raman system, portable Raman systems. So the Raman, you know that it is a very weak phenomena. 1 in 10 to the power 7 photons is Raman active. It is a very, very feeble light. So we have to have a little bit sophisticated system. Okay. Now, second requirement is that, okay, you have developed the system, you have recorded the spectra, then but you have to diagnose. How will you do that? In routine, regular life, you know that you go to a pathology lab and a pathologist is there. So he does the diagnosis. So you have to have a virtual pathologist in the form of a diagnostic algorithm. So you have to have a robust diagnostic algorithm which can give you near real-time accurate diagnosis. So it is the most important. So it is just like a virtual pathologist sitting in there. Okay? So you have the target tissue, you have optical signatures, you have a diagnostic algorithm which acts as a virtual pathologist, and that gives the diagnostic results. Okay? Now, we developed several diagnostic algorithms based on artificial intelligence and machine learning, but algorithm which we found to be most important, or you know that, or very useful, that is a probability-based multi-class diagnostic algorithm. You know that when you talk about a diagnosis, if you say that it is normal or cancerous or something like that, doctors believe it but accepts it but with a pinch of salt. He wants what is the confidence with which you are saying all these things. So that means there is a probability. So this gives you the probability of diagnosis. Okay, so we developed multi-class diagnostic algorithm. Multi-class diagnostic algorithm means, you know that normally if you are given multicolored balls, blue, green, yellow, and if I tell that please separate this out, so what you will do, blue versus non-blue, red versus non-red, like that in this stepwise fashion, but that is very much suboptimal. So the desired is, in one go you will say this is red, this is blue, this is green. So that kind of algorithm we developed. Okay, just it is okay. So so the major clinical applications is oncology, non-oncology, and diseases. So we concentrate on oral cancer. These are the pictures which are real pictures from Tata Memorial Hospital. You know that is the hospital with which you collaborate. This is the DAE unit. Most of you probably, I do not know whether you know or not, Tata Memorial Hospital, Bombay is Department of Atomic Energy unit. And so screening of oral cancer is the most important thing. And our previous work, when we started, we did from in vitro studies, that is ex vivo studies, it is called. The tissue samples obtained on resection at surgery or biopsy we took, and almost 500 patients we did. And this is still from National Geographic, I will tell you. this we are the pioneers in biophotonics activity in India. So this drew attention, the Lancet Oncology and all the other things. And National Geographic, they cast a story on hot science from India. This is one of the stories of, there are many a time in National Geographic telecast old these things, you may be able to see that. So we did clinical studies at Tata Memorial Hospital, and I will not go into detail. So this nitrogen laser-based system, which we installed at Tata Memorial Hospital, that was a very nice system, but unfortunately, the doctors there didn't like it. Why? Because it is a, the nitrogen laser is a very noisy laser in terms of electronic noise as well as physical noise. In the humid climate of Bombay, it, particularly in July, August, it used to sound like firecracker bursting, fart, 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 because it has electronic component. So they told that you are from advanced technology, so you have to have some answer. We did have answer, that is, that semiconductor thing, that is LEDs, but that only in 2014, 3 physicists got Nobel Prize, and they invented blue LEDs. And after that thing, if we recall, that market is flooded with LEDs. All lights are LEDs now. So high brightness LEDs. After the advent of those high brightness LEDs, we developed this onco-diagnoscope, we call it. We changed into this LED-based system, which is a standalone field usable system. And then that we validated in different hospitals, including Tata Memorial and other cancer hospitals pan India. We have undergone, or we are still doing clinical validation throughout the India. Okay, and it has been technology transferred to different companies. And that ECIL is also has adopted this technology, and they are also making it. And simultaneously, that we developed a FILD, fluorescence intergravity lesion detector. That is, that it is a kind of torch, fluorescence torch. And what happens here, that you have to isolate the lesion in the oral cavity. The patient comes in the doctor's clinic, and doctor uses these things to locate the lesion, and then he uses this onco-diagnoscope. So this field in combination with onco-diagnosis is ideal for screening of oral cancer, which is regularly happening now. Okay, so these are the results. And single cell research, as I told you, that we also do the cell research. For that, we need optical tweezer. So we developed optical tweezer. This is the gentleman, this is a scientist, Professor Arthur Askin, who got Nobel Prize in 2018 for this optical tweezer, though he developed this optical tweezer when he was in his 70s, okay, and he got Nobel Prize in his 90s, okay. So we developed these optical tweezers. I will not go into detail, but optical forces, that when I am shining this laser light has two forces. One is scattering force, it pushes the particles forward, whereas there is a gradient force which pulls the particles back into its focal spot. So there is a tug of war between these two. Normally the scattering force is higher than the gradient force. But when the gradient force becomes high, if you tightly focus the laser beam, then what happens, that optical trapping happens, and that's how the particle is trapped in its focal spot. And when you trap this focal spot, you can trap, that is why it is called optical tweezer. Without touching the cell, with the help of light, you can catch hold of it, and you do several kinds of micro manipulation. Once you catch hold of a cell, then you drill holes through with other lasers through its cell wall, and you can put in drug which otherwise the permeability of cell membrane doesn't allow. So all kinds of things. Is a very powerful tool, and we at RRCAD the first we developed in the country, showed this thing. And there are several publications or several things we did. And one of the things I will tell, that under this optical trap, these RBCs, that malaria diagnosis is a very tricky thing. And that's why normally when somebody is having malaria, then doctors say that you go to the lab when you have give the blood sample when you have high fever. Because malaria, these parasites, they hide in spleen and liver, this kind of thing, so they don't show up. in the blood sample. So normally, even if you have malaria, then your result is always negative. So here what we do, what we got, that malaria affected RBCs, though the malaria parasites are not residing in the RBC, they are under optical trap. Their rotation, they rotate like this. Normal RBCs rotate faster, whereas these malaria parasites, they rotate very slowly. So this can be used as a malaria diagnostic parameter, though we didn't pursue these things or after that, because there are several other things as well. But this thing basically drew the attention of even Arthur Askin. You know that in Arthur Askin, in his Nobel lecture, he mentioned about these things. He told that I was told by my colleagues that one Indian group has developed this, applied this optical tweezer for malaria diagnosis. And when I say Indian, it is not American Indian, but Indian. So if you hear this Nobel lecture in YouTube, we will find this thing. So like that, there are several applications of optical tweezers, and optical tweezers we have combined with Raman spectroscopy to record Raman spectra from a cell. You know that mammalian cell or any other cell, normally mammalian cell is of the order of 15 to 20 micron. Our hair is around 100 to 200 micron. Okay, so there are several applications of Raman optical tweezers. So similarly, we have done body fluids, and we recently developed nanotrap enhanced Raman spectroscopy. This is a very efficient technique for trace detection of bioanalytes. But you know that conventional, till now I have talked about conventional optical spectroscopy, but you know that conventional optical spectroscopy, normally if you shine light, and light has a penetration depth, in that penetration volume, whatever photons are generated, you record those photons. But you know that tissue is a multi-layered thing. You have dermis, epidermis, etc. So your disease or cancer can arise anywhere in these layers. So you have to have depth-sensitive optical spectroscopy. For that, what we did is the source detector separation. For example, you shine light here, and you know that these photons, they undergo forward scattering in tissue. And you know, if you see that if you are away from this point of incidence, the more you are away, the more you are looking at the photons which are coming from the depth. So this is called source detector separation. So this is how we do that. And based on that, we have developed, we have carried out several studies, and these are the studies. And we also developed this kind of depth-sensitive Raman probe, handheld Raman probe, and which are being regularly used. Okay, and optical imaging, as I told, there are fluorescence and Raman imaging we do, hyperspectral imaging we do, optical coherence tomography, you may be aware of in the context of ophthalmology. So we have developed tuberculoscope. It is a fluorescence imaging based TB diagnostic device. Normally TB diagnosis is very, very critical in the sense that, that Government of India has a slogan of TB Mukt Bharat by 2029. But this TB Mukt Bharat requires, that you have to diagnose TB, which is a very time consuming thing, because normally TB diagnosis, the WHO standard is, that you have to have sputum smear this cytology and fluorescence microscopy. So fluorescence microscopy, normally fluorescence microscopy is very expensive, and that's why TB diagnosis is mostly limited to the district towns. So just a few minutes. So we developed that thing. Then hyperspectral imaging, that when you take a snapshot, then at every, that image is a kind of, that intensity variation. But it is always desirable that if you have at every pixel, you have a spectral information, then you can get biochemical information. So we developed this hyperspectral imaging, which is the marrying between spectroscopy and imaging. Okay, so we developed this multimodal hyperspectral imaging. Then optical coherence tomography is a Michelson interferometer, and we have developed this optical coherence tomography, several versions of these, and we have done these things, and we have combined optical coherence tomography with Raman, fluorescence, etc. And in phototherapy, I will take 1 minute. Phototherapy, as you do, photobiomodulation, photodynamic therapy, up to you are already explained by my previous speaker. And so we do all these things, and photobiomodulation studies, TB treatment, then cell proliferation and tissue regeneration, alteration in gene expressions. So we do TB treatment with the help of nitrogen laser. Okay, so all these things are done clinically. Okay, so there are several such things, and photodynamic therapy just explained by these things, that when you know that it is a spin-off of this photodynamic therapy basically emerged for this anti-tumor therapy. But the spin-off of photodynamic therapy is antimicrobial photodynamic therapy, which has drawn attention because of the reason he told that what happens, antimicrobial photodynamic therapy, that this indiscriminate use of these antibiotics leads to antibiotic resistance. And antibiotic resistance is something which is very, very important, that we are ignoring it because of indiscriminate use of antibiotics. Maybe 5 years down the road, you may not find any antibiotic which can cure a simple infection in your finger. So that is the era we are leading to. So from that point of view, people are talking about antimicrobial photodynamic therapy and this chemodynamic thing, all these things that is basically emerging. And what is happening, that when you administer antibiotic, it is just like a terrorist group, and the government is basically forming a anti-terrorist squad. But once you apply that thing, then next time that thing doesn't apply, because they understand. Bacteria is also like that. So it is photodynamic therapy, antimicrobial photodynamic therapy is just like surgical strike. The terrorists do not know from where the strike is coming. So that is how it is important. So we did several things, and this I will not go. I will just finish by saying that we do also studies probiotics, okay, these light-mediated probiotics, okay. So we have developed this Nazolite and Aerolite for ear infection and nasal infection cure by antibiotic photodynamic, and these are all technology transferred, and this is available in Tata 1mg. Okay, so, and we have also developed during this COVID period the only ICMR approved this thing, UV radiation. Okay, this is something. And before I finish, I acknowledge all my students, colleagues, and clinical collaborators, Dr. Pankaj Chaturvedi, MGM Medical College, and then IIT Indore, Sharad Gupta, and other colleagues, and permanent director and present director. Thank you.
Thank you very much, Dr. Majmudar, for very nice presentation, and the applications of the light in the biomedical applications, starting from very fundamental applications to the most advanced applications. Thank you, sir.
Yeah. 4. Surya Prakash is not there. He has left.
No. They are in the board.
He is there. The chair only 4. Ah. Please join. Sit down. Ladies and gentlemen, good evening. Thank you for being with us very patiently. You heard all sorts of lectures. I hope, or I am sure that you will agree with me that we had wonderful presentations right from the morning till morning yesterday till evening today, and it will continue tomorrow. Well, I'm here before you for a noble cause. You must have heard about, yes, you have been hearing about CRS. What is CRS? It's a Chirantan Sanstha, which was instituted in the year 2016 by Professor Rajkot. This evolved because many of the papers, Indian papers, who can win, even in fact, who can go to science or nature paper, have been rejected continuously. There is sort of bias. I don't know what kind. I don't have time to talk about all that. But a group of scientists, you all, like me and him, why we should depend on somebody else? Why don't we start our own journal? There are several journals, but this particular organization, Chirantan Rasayan Sanstha, came up with the different ideas. Why not we, there are so many scientists, so many people who are doing a great job, but they have never been recognized by any societies or government of India or government whatsoever. That's how we started. We know our strategy, how we choose scientists, and we know, I think all of you agree with that, all the awardees have done a phenomenal job. Phenomenal job, actually. You give a big applause to all of them. Phenomenal job. So that is the strategy. We have a big team. We have council members. We do a good job, I think. We have been doing a good job. We have been able to even go to Nobel laureates. Please join us to, enhance the visibility of science and technology of government of our proud nation. Now coming to other aspect, as I said, there are so many interesting articles. There are so many interesting work. There are so many, kind of piece of work. They are of work publishing in Nature, worth even we're getting Nobel Prize. But many times, we have been ignored. I don't know the reasons. We'll not worry about it. But nevertheless, what we thought was we'll come up with our own journal through this society. That's how we have launched what is known as RASAYAN. Okay, in German it is called Invention. It's a RASAYAN. So we do have our own journal. It's quarterly published. Okay, so this particular journal is focusing on, is inviting all kinds of research articles, all kinds. It can be a review article, it can be your own research, it can be tutorial, it can be some kind of a material that would help students or any other researchers, or it can be some kind of a, work that, which you are not able to present elsewhere, which you are not able to, sort of not getting it through, we can do that. So that's how we have come up with the journal. And I'm here before you to tell you that this has been a wonderful conference. The kind of quality, the kind of, the awardees we have this year, this time, it is something phenomenal, really, truly phenomenal. I should thank Saurashtra University and Madam to, joining us in recognizing these people and making up a, big event. And I'm sure that you are seeing the biodata of everybody. They are wonderful, and you heard the lecture. Well, now let me introduce, in respect of RASAYAN, our bag, 3 people are sitting there. One is the chief editor, other 2 are associate editor. I am also associate editor. Paira, myself, my name is Mugar, and he is Rajkot Bag. And there is Soumya Day. Can you introduce Soumya Day? This is Soumya Day, Rajkot Bag, and Paira. So Paira and Day are the associate editor. I am also editor. Boss is Bag. So he is a chief editor. So we are requesting, Surya Prakash is also there, of course, NMR expert. So also, of course, we are slowly coming to you, sir, later on. Okay. So, we humbly request all of you to, submit your research articles. We will be definitely, if anything, I mean, not that every paper is in a, presentable form. We'll try to help you out, including students. We'll try to help you out how to, we'll try to edit it. That's why these stalwarts are sitting there. So, in this contest, first I would like to invite, in essence, what we are trying to do is, this particular event will be brought out in the form of articles. All speakers, we invite all the speakers to present their papers. We already invited them. This is something, this particular event was very much appreciated by Nobel laureate Venki Ramakrishnan. So he is very, very happy with all the speakers, everything. We had lots of messages. So in that context, it makes sense to us to bring out a special issue. I'm announcing coming up with a special issue. So for that, we are appointing 2 associate editors. I'm also editor and Surya Prakash is also editor. Now I would like to invite Soumya Day to say a few words.
Hello everyone. So big thanks to Professor Bag and Professor CV for giving me this opportunity. So when they told me about this, I was really excited about this because this is something that we should really do, because we are so much dependent on publication and everything on journals which none of those are published in the country, right? So it's I mean, if we think about Atmanirbhar Bharat, then we have to be self-dependent on this also. So anyway, I mean that this validation from outside has to stop. So we are good enough now. Our country is more than 70 years old, so we can actually judge our own papers and publish good quality papers. So what I would urge you to do is, even if it's a short paper, just try to maintain a good quality paper. It can be a perspective paper, it can be something that you have some interesting idea and you just want to put it out there, right? So it can be something like that. If you have some really interesting result, but it's a preliminary result and you think that you would like to publish it, you can use this platform for that. So it's up to you. As Professor CV said that there is a format, so I think in the email that format has been sent. You can use that format. If some editing help is needed, of course we are here to help you with that. So with that I will just conclude, and we'll be looking forward to your contributions. Thank you very much.
Now, may I request Dr. Paira to say something about the journal?
Yeah, sure. Thank you very much for giving me this wonderful opportunity. So I would like to say only few words. So anyway, so this is our own journal. So you better know that what type of work we can send there. It's not fixed in a particular topic. So n number of topic in chemistry you can select on that, and yeah, anything, and all branches of thing. Okay. So, and one more thing is, suppose you feel that the work is not suitable and all, so you can send it. We can give the idea how to improve the quality of the paper, and accordingly you can do the corrections, and then you can further submit it. So thank you.
I take this opportunity to thank profoundly organizers for giving us this platform to, tell about our RASAYAN. Thank you, madam. Thank you, everybody. Thank you. Madam, just with your permission, I think there are a couple of parallel talks were going on there. We could not honor some people who have arrived yesterday or today. We will honor them. If you can tell, we can honor. We can, honor you here with the, whatever medal you have. Anybody is here? We can really finish in 5 minutes. Anybody is here? Those who have not received the medals? Anyway, convey the message in the group, madam. It can be put in the group that would like to honor them, not today, if not possible. Tomorrow we can honor them. Yeah, thank you.
Now we have few company or professional over here, and they want to introduce their and give brief account of their company. So on behalf of organizers, I would like to first invite Mr. Sangram Gokhleji. He is from SCS International India Private Limited representing CAS. SCS International India Private Limited is a wholly owned subsidiary of SCS International, which is part of the American Chemical Society. The company represents CAS, the world's leading provider of scientific information and chemical databases. CAS curates, connects, and analyzes scientific literature, patents, chemical substances, and reactions, enabling researchers, academic institutions, industries, and government organizations to accelerate scientific discovery and innovation. SCSI India also support SCS publications and scientific information services across India. So now, Sangram Gokhale, it's your turn. You will have, sir, 15 minutes? Yeah.
I hope I'm audible. I speak louder, so generally keep the mic aside. That's fine. Very good afternoon to everyone. I know I have taken the tea time of everyone, and it has been great lecture series, and I would like to thank Saurashtra University for inviting us. Everyone has talked about research, all the research that they've done, they've showcased. The brilliant scientists have showcased their work. People have worked and done the research for almost 30 years now. But all research comes from some sort of a prior art, right? So CS is the one you choose when you are doing such sort of prior art. So when we talk about CS, we started in, I will just check the yes, yeah. So we started in 1907. There were a few scientists like you who came together, who started documenting the research that they were doing. Once they documented it, they started publishing it. And if you visit the older institutions like, say, IIT Bombay, IIT Madras, NCL, ICTs, they still have those abstracts. Those were called as chemical abstracts. So CS was called Chemical Abstract Services till pretty recently, till 2020. Now we just call it CS because now we have also moved into different domains, not just specific to chemistry, but in and around chemistry. Very simple definition what CS does is, whenever you see a chemical in your laboratory, there is a CAS number written on it. We provide the CAS number globally. Your name of the product can change depending upon your work, the brand that you are representing, but the CS number is as unique as your Aadhaar or a PAN number that we currently have. We were the first into domain to introduce a structure readable model where you can see the structure on the screen back in 1960s, and we have experts who speak more than 50 languages. So we don't just cover English literature, we also cover literature from other languages, because if we talk about data, the number of non-English literature published in past 10 to 15 years is more than the English language literature. How we do it? So we have registry services, that CS numbers, we have chemical structures, reactions, properties, bioactivity data, spectral data, references, citations, both from published literature as well as from patented literature as well. How much we cover, because when we talk about data, it is also the volume of the data that is important. So we cover more than 50,000 journal titles and documents. We have indexed more than 250 million substances. Substances translated from over 50 languages, and 109 patent offices are covered into it. How the data is organized, depending upon the research that you are doing, you will require the data in that particular format, in that particular way. So you can have data in the form of infrared spectras, biochemical isolations, targets, agrochemical formulations, so on and so forth. So you can pick and choose what you require through the products of CS. When we talk about CS, we have platform solutions like CS Newton, CS SciFinder, BioFinder as well as IP Finder. We have workflow integrations where we integrate with the system through API integrations, agent-to-agent interactions. We also provide consultations to data digitalization, AI model trainings, knowledge system design. But everything is always going to be in and around data. It can be your data or our data. With the technology that we have, we can collaborate on variety of levels. We are speaking about AI since past few years, but CS also integrated AI back in 2022 with variety of ways, and now we are able to predict the retrosynthesis of a compound which is not even reported anywhere. We are able to predict a target molecule. We are also able to predict the outcome of a reaction which has not happened yet. With the help of the data that we have built upon for almost, yeah, I will request, sorry. Thank you so much. So the data that we have for almost 150 years now, so all the models are trained on that particular data. So whenever we talk about AI, we have started using AI in your mobile phones, but those are generic AIs. The AI prepared by CS is trained and developed and understands specific chemical reactions. So when we talk about AI, I'm not going to show you what SciFinder does, many of you are aware of it, but we'll see what AI does for us now. So this is an AI that we have launched which is called Newton. It is our own AI, agentic AI, where you can ask questions the way we ask our teachers, the way we ask a system, or maybe the AI that we are asking. You can just ask a question and get an idea about it. What do? You can do agentic searches, cross-disciplinary research, large data searches, analytical insights, verifiable and sourced answers, and science smart capabilities. This is very important, verifiable and sourced answers, because if AI is giving me some answers, what is the background behind it? It is just a presumed thing, or does it have a reference behind it? So with CS Newton, you have the reference which talks about the results that are shown in front of us. How it does it? So I will just skip this one. So if we do a simple search which says, based on my search of CS content, I found recent research on EZH2 inhibitors intermediates, and here it is what I recovered. So you can see there is patent application, there is key synthesis from the papers. So even without opening a document, you have data that is available in front of us. See, I've done some search into Newton, and I've got this sorts of result. Moreover, it also asks you a follow-up question. In first, it has asked us focused on thiophene intermediate synthesis. So it asked me provide reactions for synthesis of thiophene intermediates and how it is done. So it will also lead you to a question. Once you ask something, it will prompt you that do you want to see extra around it, or it can also give you some reaction insights into it. Now, it is not possible for any organization or any institute to subscribe everything that is available under the sky. Plus, there are many people who are not even marketing their products in India. But through CS data, you have access to each and every document that gets published in different languages, whether it is Japanese, Chinese, French, German, so on and so forth. Moreover, if we ask about in detail insights, it will also give you the in detail insights, summary tables, as well as the conclusions for us. Moreover, if you give a structure to the compound, and if you say, please provide all types of reactions where enclosed structure is used as a catalyst. Now I am being very specific about my questions. Still, it will give me all the reaction types. Plus, it will say me it is used as a complex, as a catalyst in reduction reactions, and with the number of reactions that are associated with, as well as the number of references associated with it. Moreover, these are few initiatives that CS has taken. So it is first of its kind reaction discovery, intuitive natural language search. What is natural language? The way we talk. So give me the synthesis of X using Y and Z, having a specific catalyst or a solvent, it can give you direct answers. You don't have to go through number of papers or patents that might have similar options for you. You also have interactive retrosynthesis, customizable substance result display. Why interactive retrosynthesis? Because if I have a moiety, I want to modify it and see, I want to add a protecting group, I want a reaction to happen at a particular node, I can ask SciFinder or Newton to do it for me. Only reaction will happen at that particular location itself. So when we are talking about IP, filing patents of that sort, if I want to find a non-infringing route, so I have to block where the innovator has already done the work. I have to open the areas where they have not done the work or published it maybe. We also have something called as search sense. So through, oh sorry. Yeah. So what you can do is publication of Biswaswarup Pathak. You can just ask it, what is the restricted statement of thionyl chloride? Or you can just say, what is the 1H NMR spectra? You just have to ask it, you will get the answers around it with references, with the data from where it is getting extracted. Moreover, we also have done something called as IP connection. So who is doing the work? Not just the work getting done. Who is doing the work? Who is publishing the work? All the institutes, all the organizations, all the academies who are working around it, you can get all this through the IP connection. You can search for novelty through Markut searching, understand trends, gaps, focusing on data. So if I want to file a patent, these all things might be important for us. Similarly, you have a prior art discovery. So if you have a, say, abstract, which is very relevant to me, what you can do is you can just copy paste the abstract into it and ask it to search for similar documents into it. So it will give you similar documents having the abstracts associated with it. It will categorize it into the patented as well as non-patented documents. So you have abstracts which are relevant to me only the documents that are relevant to my specific research. Moreover, moving just ahead of science now, not science, chemistry, we have also entered into something called as BioFinder Discovery Platform. In BioFinder Discovery Platform, what you can do is you can search through ligands, scaffolds, proteins as well as diseases. You just have to enter it and get the data around it. It's a powerful research solution for pharma and biomedical scientists, enabling faster, smarter drug discovery. So whoever is working to drug discovery or medicinal chemistry, it can be helpful for them. Also people who are working into biosequencing peptides, they can also take help of this particular product. Even if you only have a disease or a target or a modality, you can find other two through it. Moreover, what it can give you sequences, organisms, diseases, toxicity, biological pathways, biomarkers, antibodies, so on and so forth, and everything is connected with each other only. So what scaffolds and molecules are associated with your disease of interest? What molecules are known or likely to be active against your target? How will your molecule interact with proteins? Which molecule will make you the best leads, as well as what biomarkers are relevant to your diseases? All these questions are getting answered by BioFinder. Moreover, you can see that comprehensive ligand modality is used in CS BioFinder, reported drug classes, indexed in CA data. So coordination compounds, classes of drug molecules, peptides, polymers, peptide drug conjugates, PROTACs, ADCs, everything gets covered. Plus you will always see a registry number at the top. So you know it is very specific to it. Plus you will have the structure associated with it. If structure is not there, you have a 3D structure of it like a protein structure, where you can see for what is the docking site, what is the locking site. You can also see that. We'll just take a case study. So using CS BioFinder's AI-driven predictive analytics, a compound was screened for in silico for micro-opioid receptors interactions. So now we are getting into very specific searches, but with the help of BioFinder, we were able to get exact answers. Plus you can see all the references associated with it. Anything you see, you will always see the reference that is associated with it. So it is going to make you take a decision faster, whether I want to open a document or not, whether the document is relevant to me or not. All these decisions are made before even opening a document, because the data is actually available with on your screen. If you want to have a trial access of BioFinder, you can just scan it. 3 minutes, yeah. So you can scan this QR code, or you can get in touch with me post this session. You can also have access to the trial of the product. It's a new product that we have launched, and why we have launched is because the bio data around bio sequences or bio is very much scattered. There is no uniform way or a uniform way to represent that data, whether it is for different PK values of it, anything, you have access to BioFinder. My name is Sangram, and you can contact me at sgokli@acs-i.org, or you can just drop an email to info@acs-.org. Thank you so much. If you have any queries, I think we have 1 minute. We don't have time. You can ask me after the session. Not a problem. Thank you so much. Yeah, sure. I think you want to scan it, right? Yes, yes. Yes, please scan it. If it is not getting scanned, you can just visit ch.org and request a demo. That's also fine.
But this is, you are going to charge us. Software.
No, whenever I show it is free. When I speak, I'm going to utilize it, obviously get charged.
Well, ladies and gentlemen, on behalf of CRS, along with the organizers, we profoundly thank you for the support. He who has, given us some kind of support in terms of, rupees.
Not in dollars. Keep supporting us, sir. Absolutely. And we will support you. Yeah.
INCRF, Indian Chromatography and Analytical Research Foundation, is a scientific organization dedicated to promoting analytical sciences, chromatography, spectroscopy, and laboratory technologies in India. The foundation works to bridge the gap between academia, research institutes, and industry by organizing conferences, workshops, training programs, and exhibitions. INCRF provides a platform for scientists, researchers, students, and instrument manufacturers to exchange knowledge, showcase technological advancements, and encourage innovation in analytical research. Yes, please, sir, Krishna sir. You have 15 minutes for your presentation.
Okay. Good evening. Good evening, everyone. Actually, I am from Incorp Instruments, Hyderabad. I am from Hyderabad. My name is B. Krishna. And we are representing Bruker Optics divisions, and we are displayed this instrument, this model called Alpha 2, displayed in our stall. At any time you can come and have a look here. And next one.
Yeah, it's there.
It's not coming. Okay, it's very slow. Okay. See, I will not go in depth about the chemistry and all these things. You know about the FTIR. This is the functional groups identification for the chemical analysis, and infrared spectroscopy is for the observations like emissions, reflections. Nowadays, reflection is more popular than the observation and emissions of the liquid gases, liquid solid material of any kind of these things. And Fourier transform is a mathematical calculations, and this is a conversion between the interference of the patterns into the spectrums. And first mathematical it was developed in 1948. And this FTR technology is there. It's a non-destructive technique, and we can use it samples again and again. There is no issues. And this is the electromagnetic spectrum, and we are discussing about this instrument for the MIR regions like 4,000 to 400 centimeter universals. And this central, there is a matter, why it is become slow.
Press this button for the next.
Correct.
Sir, you just need to towards this.
See, just now I told about this is the reflection is a more popular than about the observations and not coming. Otherwise, I'll just. And this is the infrastructure, spectroscopy is there. No, it is the vibrational technology, whether it is symmetric, anti-symmetric, or deformation, any type of vibration, it will take care of our instrument. And this is the best example for the water, and this is just for the example. And here we are talking about more about the ATR principle. ATR is nothing but alternated total reflections. This is the total IR light, just I shown here. This is the combined signal from the, it will penetrate into the sample and reflecting into the detector. Okay, and some of the spectroscopies. This is the fingerprinting technology, and each and every compound they having a spectrums. And for known samples, we have a threshold values. It will be 90% to 100%, and we can choose your in between the threshold value. For the here I have choose a 95%. More than 95%, it will be matching, means it will be okay, and below 95%, it will be it is into mark. And for unknown samples, we have a libraries. And for this model alpha 2 is it is very simple to analyze, and occupies very minimum space, is A4 size, and free maintenance, free operations, and work at any places. Even displayed in this one here, no need for the AC environment, no need for the humidity control and nothing. And even if it is 45-degree temperature also, it will works. And we can carry at the even field also. And we can, within 1 hour, we can train the users. This is very minute to 1 hour. And this low energy consumption, it is very 80 watts. And this white color indicates, that is a FTIR. And the blue color one, all are sampling modulus, like transmission, platinum ATR, zinc selenide ATR. Platinum means the transmission is, sample preparation is required here. And for making any sample, you have to make a pellet press and everything is required. But when you are using with ATR technique, there are two types of ATRs are there. Models, means it's a sampling modulus. One is diamond ATR. This is the universal one. You can use it any type of samples, whether it is too much acidic or too much alkaline also, it will withstand. Even hardness of the metal is more than stone also, it will works. But in eco ATR, there are some limitations with it. It should not be used too much acidic, too much alkaline, and hardness will be very, very soft. And this zinc selenide ATR, it will goes into the most into the recommending into the food samples and drug samples and all. And obviously gas analyzers is requires a different model, and reflection is those who are having some painting or in museum and is non-contact method. Those applications only we are going to promote this one, reflection. Multi-reflection ATR means here in ATR there is a one drop is required, but in multi-reflection it is a rectangular shape, and you have required some more samples, and it will be It's not a single reflection, it will be multi-reflections, and it will give the result. Like that drift also, there is some soil sensors applications, it will be useful. The main principle of the FTR is, the key component of the FTR is interferometer. The interferometer, just I put it in a block diagram here, and it's a combination of the spectrum, optics. One is they're calling beam splitters, and one is fixed mirror, another one moving mirror. Mirror means there is some coatings backside, and IR source is passing the beam into the beam splitter and splitting the beam into two, 50-50%, again reflected back and pass on to the windows, and the sample, it's the combined signal will pass on to the sample and go into the another window to detector. And detector, it will give the interferogram signal. The interferogram signal, it will mathematical calculation into the IR in the range of 4,000 to 400 centimeter universal. What Bruker is having a specialty for this interferometer means it is a permanently aligned interferometer. Why they are calling permanently aligned interferometer means, okay, instead of the flat mirrors, they have a cube corner mirrors, 3 mirrors, and beam will be same, and here parallel signal it will give. Because of this parallel signals, even we can, it's not required the like flat surface, and even if it is in frictions technique also it will be works, and pass onto the windows, and it will give the interferogram signal and mathematical calculation into the 4,000 to 400. And this is Bruker is going to give this interferometer 10 years warranty, and cube corner mirrors, and gold coated. Most of the people, they will use it for aluminum coated, but this is gold coated mirrors, and high humidity protection also it is available, that is zinc cylinder beam splitters and windows, that's optional. And solid state diode laser is also comes under 10 years warranty. And this will be looks like this, rock solid interferometer. And gold coated mirrors will be like this, it will be cube corner mirrors. It's compared to the aluminum mirrors, this will be aluminum oxide that takes place over the period of times, it will be going to be rest, but gold coated mirrors also it is better retro reflections. Usually we will recommend to in India, it is a zinc solenoid beam splitters on windows, and it will be insoluble in water, it is hydrophobic in nature compared to the KBR. Once if you opt for the zinc solenoid beam splitters, no need for the keep the instrument for 24 hours conditions. And key features of this alpha 2 is there a signal to noise ratio. This is more important factor to choose any FTIR, like the Bruker, this alpha 2 model is having more than 55,000:1. Even somebody is giving 60,000:1 also, it is still better. And another 4 parameters also, it's very important. One is the spectral resolution, spectral accuracy, spectral precisions. This is 4 parameters when you opt for the any FTIR. And diamond ATR, it will comes, obviously it will 10 years warranty from the Bruker. And as per the US pharmacopoeia, it is compliance issues, everything it is there. And wave number accuracy and all, everything it is in US chapter. Over, okay. And we have some package offers like Eco ATR, Platinum ATRs packages, and just now I have shown about this will be useful for the solid, liquid, and gel, every kind of these things with single ATR. And 3 variants of crystal plate is available. And this is the specifications related with the DTGS detector, DLTGS detector. With respect to temperature, nothing will happen. And IR source will be global, and the solid state diode lasers, and spectral range will be 350 to 8,000. This is the actually, just now I told about 4,000 to 400, this is MIR ranges, but This instrument, it will be have a capability of to range will be 350 to 8000. When you are using with KBR, suppose you are using with zinc solenoid, it will be 500 to 6000 centimeter universal. Resolution is 2 centimeter. Option also it is available 0.75. Approximately it will be 7 to 11 kgs. OPPO software is the very easy to operate, and 21 CFR for compliances, and it will be compliant with the US, European, and Japanese pharmacopoeias. These are all related sampling modulus pictures with the samples for every tax. Depends upon your application, this will be going to be changed. And we can use it for powder, granule, film shape, liquid, paste, everything in one machines. Identification of the material, they will use it for this one. And for known sample, unknown samples, everything it will be possible. And quantification also we can do it from here. And this particular instrument is having some this one, and we have a high performance instrument also. They are dedicated for the quantification instruments also we have. Usually, if any raw materials come, then we can immediately check it and we can pass the result. If it is not come, then we can return it back. This is for the how it will works within a minute. Your spectrum will be going to be generated. For unknown samples, we have a library also. We have an optional like 26,000 FTR, and we have different applications. We can use it like PVC, illegal drugs, and also we can use it to kidney stone analyze. Also we can make it, and contact lens also we can make it. These are all different applications we are doing, and this is related with the quantifications. And soil science purpose also we have some attachments also we have with same instrument. And for quantification also we can do it, and these are all related to the quantifications, and this is all related with the gas measurements. And this is for the mobile applications. We can carry out this instrument to any even field also. And also we can keep it in glow boxes. And other than these machines, we have like other equipment for high performance FTRLs and NR dedicated instrument, handheld Raman also we have, and Lumos microscope for the micro samples, and also we have a concave microscopes apart from this Alpha 2. Thank you.
Thank you, Mr. Krishna, for the nice presentation and making us acquainted with the models, the various models for the FTIR studies. So now the organizers wants to felicitate you. So please come forward and accept the felicitation.
At the end of the day, full of knowledge, let's celebrate the mesmerizing evening. As you all are on the land of India, here we celebrate all festivals in every region of every religion. That's why it is called as the Incredible India. Let's get started with the performances. We have talented groups and individuals showcasing their skills dressed in traditional attire reflecting the vibrant colors of culture. To start the event, I would like to hand over the stage to Janvi Bhatt. Please come forward and take this stage.
Namaste. First of all, I would like to bow down to the lotus feet of Pujya Gurudev. As we all know that today we have gathered here to witness cultural program which is a part of 3 days international symposium RASAYAN-23 which is held from 8th of July to 10th of July on the topic of science beyond boundary, invention, discovery, innovation and society. A jointly organized event by Department of Chemistry, Saurashtra University, Rajkot and Chirantan Rasayan Sanstha. Respected Honorable Vice Chancellor Sir of Saurashtra University, Dr. Utpal Joshi Sir, eminent scientist, academicians, Head of Department of Chemistry, Dr. Bhoya Sir, Dr. Ranjan Khoot Madam, officials of Saurashtra University who are present here from various departments, media personnel, students and dear participants. Jai Bharat, Jai Vignan and a very good evening to all of you. It is my immense pleasure to welcome you all for this event for a very special event on cultural program. Without taking much of your time, let us begin with our first performance. In our Indian tradition, we like to begin anything important or anything special by remembering Lord Ganesha or by performing Ganesh Stuti. As we all know that Lord Ganesha is the remover of all obstacles and a symbol of auspicious beginnings. In Gujarati culture, there is one extremely popular bhajan that is sung right before starting something special. I would like to present a few lines of the same bhajan. Prathama pehla samariye swami tamne sundhada devata riddhi siddhi nada tar devata मेर करुणे महाराज रे माता छे जेना पार्वती रे पिता छे शंकर देवता देवता गळामां मोतीडानी माळा देवता मेर करुणे महाराज रे. Even in Natya Shastra, the concept of Purva Rang Vidhi is extremely significant. Purva means before or prior and Rang Vidhi means stage performances or stage procedures. So when we invoke Lord Ganesha, we awaken the same qualities within us to start with a certain amount of clarity and confidence. So the Ganesha Stuti will be performed by the students of Ganga Girls Hostel. The names of the participants are Bhesdariya Yashvi and Gohel Khushi. I would request participants to please come forward and brace yourself for the performance. All the very best and good luck to you.
गुणेशानाय धीमहि गुणातीताय गुणाधीशाय गुणप्रविष्टाय धीमहि एकदन्ताय वक्रतुण्डाय गौरीतनयाय धीमहि गजेशानाय भालचन्द्राय श्रीगणेशाय धीमहि एकदन्ताय वक्रतुण्डाय गौरीतनयाय धीमहि गजेशानाय भालचन्द्राय श्रीगणेशाय धीमहि
Gananayakaya, leader of the people. Ganadaivataya, divine god of people. Ganadhyakshaya, representative of the people. Dhimahi, we bow down to you, we bow down to you. Ladies and gentlemen, such is our beautiful Indian culture of reverence and devotion. A thunderous round of applause for the performers. Many congratulations to Khushi and Yashvi both. For our next performance, it is based on Garba. So, Garba is a popular folk dance of Gujarat, held mainly at the time of Navratri. The word Garba refers to the Garbhadeep, an earthen pot which is lit with diya. Garba is an energetic, lively dance form accompanied with infectious and catchy beats of drum. Garba celebrates divine feminine energy and cyclical nature of life. Ras Garba is an integral part of Saurashtra, Kathiawad, Kutch and whole of Gujarat. It is also a part of UNESCO's intangible cultural heritage. Garba is mostly practiced barefoot because going barefoot it signifies the respect that we showcase for Mother Earth. Garba serves as a medium for communication, self-expression and storytelling, allowing humans to convey complex emotions and ideas that words often fail to capture. Without any further ado, let us welcome the students of Saraswati Girls Hostel to perform Garba. The names of the students, the participants are as follows: Kamani Keral, Nakum Vasanti, Chavda Hetal, Barad Rupali, Bar Sakhya Jaya, Thrangu Swati, Rathod Meena, Buchya Mital and Makwana Priyal. I request all the participants to please come forward and gear yourself up for the performances. All the very best and good luck to you.
जीना हाथ मारा मेजे मारा मन नी भूख
incredible, amazing. That was meticulously performed. The exuberant, vivacious and cheerful energy and rhythm were fantastic and on point. So kudos to you, all of the students, and many, many congratulations to participants. Let us clap one more time for the beautiful display of our beloved Gujarati heritage and Gujarati culture. I would like to take a moment and tell you all that through this international symposium, we are getting to learn a lot from eminent personalities like Dr. C.V. Yellamgar sir, Bhoya sir, V.C. sir, Brajgopal Bagh sir. We are learning not only domain expertise, but we are also learning soft skills. Through these 2 days, we have learned about the domain expertise that they possess, such as their intellectual brilliance, their rational thinking, critical thinking, scientific approach to problem solving, an insane amount of curiosity and seeking truth and knowledge. But at the same time, we are also learning some of the soft skills by observing them carefully, such as their communication skills, their down-to-earth nature, and their genuineness, and their positive growth mindset, and their willingness to share their discoveries with us, and in the simple language, in a language that we can understand. Because those students who are from non-science background, it is extremely difficult, it can be extremely difficult for them to understand some of the concepts, the terminologies they are very new to, some of the words that they are hearing for the very first time. So we must have a huge round of applause for the intellectual brilliance that we have here, for the excellence in science that we have here, and their determination to help humanity at the expense of many sleepless nights is also extremely inspiring for all of us. That sometimes we give up too easily, but if you want to get to a certain level, there are certain compromises and certain hard work that needs to be put in. So we are very thankful to all of you, sir. And as the students, on behalf of students, I would like to say that these virtues we will try our best to inculcate within ourselves, to assimilate, to learn as much as we can and make the most of these 3 days. And from our university authority, from our Vice Chancellor sir, we are learning so much from their visionary leadership and commitment to academic excellence and campus improvements, and then genuine concern for overall holistic development of students. So thank you for that, sir. After energetic, vivacious and vibrant performance of Ras Garba, I think we are getting more and more excited for what our next performance is going to look like. So our next performance is Ghumar. Moving on to Ghumar. So Ghumar, the performers will depict colorful, vibrant culture of Rajasthan. Ghumar is an iconic and graceful traditional folk dance from Rajasthan, derived from the Hindi Rajasthani word ghumna, which means to twirl, to spin in wide circles. Ghumar was originally performed to worship goddess Saraswati and local deities, Sthan Devta as we like to say in Gujarati language. Later, it was embraced by many royal households, eventually becoming a staple at palaces and at celebrations like Tej and Gangur across many regions of Rajasthan, and especially of Mewar, Marwar and Jaipur. Music of Ghumar comprises of beats from various instruments such as dhol, nagada and shahnai. In other words, we can say that Ghumar truly indeed is a celebration of regional pride and womanhood and divine feminine energy. So the Ghumar will be presented by the girls students of Narmada Hostel. The name of the participants are as follows: Rathod Rinkle, Doria Bhumika, Gohil Pinal, Kadavla Ekta, Solanki Darshana. So I request all the participants to please take your positions and gear up for the Ghumar. Madle. Excellent. Let's have a huge round of applause for the participants of Ghumar Ras. The key or the defining element of the Ghumar is accelerating spins and all of those twirls with heavy lehenga that require skill and balance, which was showcased very elegantly and effortlessly. So kudos and huge congratulations to all of the participants. I'd like to take a moment and thank the Department of Chemistry, respected Bhoya sir and Ranjan ma'am, and Chirantan Sanstha, respected Secretary of CRS, CV sir, for organizing such a wonderful symposium. Without all of your guys, without the immense efforts of our visionary leaders, this would not have been possible. So a huge round of applause for all of them. And I would like to thank the coordinator of this event, Dr. Rekhaba Jadeja, who is a rector of Girls Hostel of Saurashtra University. Thank you for your efforts and thank you for monitoring girl students and their performances. And thank you for sensitizing them regarding the importance of keeping our traditions and keeping our culture alive to the best of our possibility. In today's scientifically advanced age, we must learn that science is there to help us, to keep us more grounded and to keep us connected to our roots. So thank you for that. Our next performance is about Ras Leela. Ras Leela is the divine Ras of Lord Krishna, Radharani and the gopis of Vrindavan. It represents the pinnacle of bhakti or devotion, where individual souls detach from earthly bounds to achieve spiritual union with the Supreme God. Far from the worldly tale, the Ras Leela is the height of spiritual symbolism, a revelation of how soul can love the divine with complete self-forgetfulness and perfect surrender. Ras Leela is widely performed across North India and especially in Vrajdham, Vrindavan and Barsana. Ras Leela is not just a tradition or a performance, but it is a spiritual alignment of the mind, body and soul. As depicted in Bhagavad Puran, Ashtalakshmis, namely Lalita, Vishakha, Champaklata, Chitra, Tungvidya, Indulekha, Rangadevi and Sudevi, they played prominent role in Ras Leela. Ashtasakhis are also dearest associates of Radharani. So I would like to seek blessings. Let us all seek blessings from Radharani by chanting her 28 names. Radha Raseshwari Ramya Krishna Mantradhidevata Sarvadhya Sarvavandhya Vrindavana Viharini Vrindaradhya Rama अशेष गोपी मंडल पूजिता सत्या सत्य परा सत्य भामा श्री कृष्ण वल्लभा वृषभानुसुता गोपी मूल प्रकृति ईश्वरी गांधर्वा राधिका आरण्या रुक्मणी परमेश्वरी परातर परा पूर्णा पूर्णचंद्र विभानना मुक्ति मुक्ति प्रदा भव व्याधि विनाशिनी। बोलो श्री राधा रानी की, कृष्ण कन्हैया लाल की। So Ras Leela is prepared by students of Ganga Girls Hostel. Name of the participants are as follows: Chashia Astha, Odich Sanjana, Rana Rajviba, Bambhaniya Vilas, Barar Nikita, and Chauhan Nandini. I request all the participants to please come forward and perform Ras Leela.
श्यामल सावरे मैं करूं बावरे मोहन मोह के खिले ना रंग रे धन पे डारना धन की छावरे प्रेम लगन लगी मोहे छो
प्रेम का पंछी पंख पसारे काहे न जाए हाय
कान्हा काहे तुम मेरे सखाए कान्हा काहे तुम मेरे सखाए जबर जोड़ी करे पकड़ भैया घरे टूट गई अंगी की डोरी रसिया कान्हा काहे मोहे लाज आए कान्हा काहे तुम मेरे सखाए
चंचल रूप सहद के जैसा काहे न भंवरा आए गोरी रूप कलश ये तेरा छलक छलक जाए
नैना तूने फेरी मैंने खाए मर गई कोई सांस न आए
हो खोल हर के द्वार जरा से मृदुबने मन माने ना
छोड़ना कमर मोरे
तुम्हें मेरी
कान्हा काहे तुम मेरे सखाए कान्हा काहे तुम मेरे सखाए जबर जोड़ी करे पकड़ भैया घरे टूट गई अंगी की डोरी रसिया कान्हा काहे मोहे लाज आए कान्हा काहे तुम मेरे सखाए नीली हो गई मोरे कलाई काहे मरूरी तूने
बिहारी न होगी रसते हैं सोने
उंगली से अपनी पीठ पे मारी लिख लिख कर कामना तेरी
एक है आधा चांद गगन के एक पूरा मोरे सामने बेबद होता है साधना है आजा गई बोल के बोले
तुम मेरे सखाए कान्हा काहे तुम मेरे सखाए जबर जोड़ी करे पकड़ भैया घरे टूट गई अंगी की डोरी रसिया कान्हा काहे मोहे लाज आए कान्हा काहे तुम मेरे सखाए सच शाम से जया मैं न जाऊंगी मैं न जाऊंगी मेरे जान से तो मैं शाम शाम की शाम सुने थोड़ी जाने की रसद अब थोड़ी आगे जो से मैं सुना तो मुझे लगी लगी जाने से से लगी जाने
A thunderous round of applause for all the participants. The energy on the stage was very infectious and all of the students have put your heart into the performance. I would request all of the students that we will play this song in the respect of our Matru Sanstha and Saurashtra University, and I request all of the respected audience members and esteemed guests to please humbly stand up at your own place. Thank you.
सौराष्ट्र विद्यापीठ सदाए पावनकारी नाम दनिया जे भी घूघवे अहिया जग विद्या तमाम जय हो जय हो जय जयकार जय हो जय हो जय जयकार सर्वधर्म संभाव हृदय में नरसैयानी भक्ति छे सावज गण कुमार गिर में एवी युवान शक्ति छे गिरनार जे स्थिर जीवन हो ध्यान मंत्र गुराम जय हो जय हो जय जयकार जय हो जय जयकार ले प्रेम झलहरे राखे गारनो तेज सोमनाथ ने द्वारिका नो महिमा एलो एज बागीश्वरी नी वीणा बागी झंकृत गामेगा जय हो जय हो जय जयकार जय हो जय हो जय जयकार महावीर गांधी नो पथरायो छे अजवास निर्बल ने बलवान संग में खेले दांडिया रास वल्लभ विद्या याद राख तू जीव तू विद्या धाम जय हो जय जयकार जय हो जय जयकार
वंदे भारत माता की
Sir, I would like to request Secretary of CRS, CV Elamgad sir, President CRS, Brij Gopal Bag sir, Bhoya sir, Head Department of Chemistry, Majmudar sir, please come forward. To felicitate our performers, I would like to call the girls. Rathod Wrinkle, Doria Bhumika, Gohil Pinal, Kadavala Ekta, Solanki Darshna. Kamani Keral, Nakum Vasanti, Chawda Hetal, Barad Rupali, Barsakhya Jaya, Dhrangu Swati, Rathod Naina, Buchia Mittal, Makwana Priyal. Followed by Rana Rajviba, Chhasya Astha, Odit Sanjana, Chauhan Nandini, Bambhania Vilas, Barad Nikita. Pesdadia Yashvi, Gohel Khushi, and sweet anchor of the evening, Jhanviba Rana. I would like to call upon stage Dr. Rekhaba Jadeja, coordinator of this cultural program, to please come forward. Thank you all the dignitaries. May please take your seats off the dais. I would like to call Dr. C.V. Yelamgat sir to share his view.
કેમ છો મજામાં કેમ છો કેમ છો honorable highly respected vice chancellor of the Saurashtra University, my friend Utpal Joshi ji, my colleague, my boss, CRS President, Professor Bag, Professor Boya, Professor Kun, Dr. Pooja, fellow my colleagues, distinguished scientists, speakers and awardees, and most importantly, Kem Cho students. Kem Cho, that is what I wanted to hear. Well, at the outset, I would like to express my deep sense of gratitude to all the performers who have performed so well. I started thinking of my Radhe. She is also a scientist, very famous scientist. My wife is also a scientist. I am Krishna because of her, kindness and Radheness, perhaps. I was thinking to go slowly, but now having, seen Krishna and Radhe Jodi, I had to go back. I have to go back. You are reminding of my wife, all of you are. Well, ladies and gentlemen, you have seen the splendid performance by the children. It is so nice. It is so nice to see all of them performing so soulfully. It was so wonderful to see. It was really a festival for us, for all of us, really. Can you give a big round of applause to all of them? Big round of applause to all of them. Generally, I speak from my heart, generally. I'm a very straightforward person. That's why I can reach to each and every one of you, especially my friend. Just one night call, everything is done. I want to be very honest with you. We have conducted about 22 Rasayanas. Okay? Rasayana is a meaning. It is very close to Krishna and Radhe. We have been able to, conduct these events all over India in very big places. Let me be very honest with you and very straightforward. This is one of the best memorable event we ever had from our CRS. Best moment. You go everywhere, you take food, it is sweet. People are sweet, they talk sweet, act sweet. हमको चेक करना पड़ेगा कि हमारा शुगर लेवल क्या है अभी जाके. मेंटली फिजिकली मेंटल तो जो स्वीटनेस है ना मेंटल वो कुछ नहीं होता, फिजिकली देखना है. This is one of the best conference this event we ever had. I'm very honest to say that. Sincerely, I'm saying. See, generally, what happens when you go to other organizations, they go by professionalism, but here that personal touch was there. Personal touch. That is, I think, should give big applause to these guys, especially volunteers. The way they, conducted the program, I feel like coming again and again, sir. You'll kick me off. Well, it is so good to see. I just finished my WhatsApp, message, reply comes. Just even night 4 a.m. Pooja replied me, 4 a.m. Right? So that is the kind of commitment people have shown, and Kund madam and Boya sir, immediate replies. Any volunteer, anything, Pooja, great. Today you go and sleep at least, I'll take care of it. You never had a complaint from your husband? No? No. Okay, fine, that's fine. Well, that is, a kind of people I met. See, this is something, creating some kind of a, goodness in me and goodwill, some kind of a feeling that Gujarati people, especially the Saurashtra university people are really great. Really great, sweet people, very sweet people, very, very sweet people. Well, I had previous experience. I am a faculty in MS Baroda University, visiting fellow. I have been teaching there for many years, and I have taught something there. It's not first time I am coming to Gujarat. Kemcho is, I am known. Kemcho word is known to me. Well, see the differences. Region-wise, there are some differences. I find it to be a very, 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 very pleasant place. For what reasons, I don't know. Maybe I met several Krishnas today, I don't know. Some blessings are there. One thing I want to say that these people, Saurashtra University people, including our Honorable Vice Chancellor, they have put in a lot of efforts. For that effort, I don't know what reply I have, except to say that thank you, thank you, thank you. Big thank you to all of you. I don't have any other words. And it reminded me of Dandiya. Right? 9 days. Actually, I step out to go to some Gujarat. There are some Gujarat zones in Bangalore. Most of the, Chickpet and market area is full of Gujaratis. Wherever I go, Kemcho is a common word to me. Majama is common word to me. The thing is, when you go to that place, I make it a point to go at least one day to participate. I don't dance, but at least I watch that. I feel that actually Krishna Radha are dancing. That kind of feeling we get. Now, I had some kind of a, I would say, Bangalore, I don't know, Gujarati must have converted into Kannadigas by now, but here I see originality. Wonderful dance, wonderful. Thank you very much, thank you. What a moment that each and every, the bend, a twist of your leg or whatever it is, and especially the head movement, if I try to do it, I'll break my head perhaps. I will not do that. Should I, yeah? Yeah, please, if it is possible, especially that Krishna dance, it's possible. If VC has a time, I know that he is not well, I know that, but still, I should appreciate. Ladies and gentlemen, it's my honest opinion, all of us CRS members, awardees, everybody has enjoyed every moment of the conference, I would say that. I'm representing do you all agree with me? Yes, right. See, this is how a conference should be. This is how it should be. This is what I call it as a conference. And the way this anchor, where is she? The way she reciprocated what they learned, that is something amazing. Something that speaks about the kind of people you are, the quality of you students you have, the really good quality. That reciprocation always, when you learn something, you should reciprocate. You should tell, okay, I have learned it. Okay, that's something extraordinary I found. As I said, we have attended so many conferences, but this is not the way. This is not the, people say so many things, but the way you said, you touch my heart. Truly touch my heart. Yes. Yes. Yeah. With that note, I think I should not come in the between of your dinner and your sleep. Well, I must say that we would like to come back. And I wish you all the best. Thank you very much. Thank you.
Thank you so much, sir, for your appreciation. As we are concluding a beautiful cultural evening, I would like to extend our heartfelt thanks to our dignitaries, Honorable Vice Chancellor Sir, Professor Dr. Utpal Joshi Sir, Secretary of the CRS, Brij Gopal Bagh Sir, Secretary of the CRS, CV Yelamgad Sir, President of the CRS, Brij Gopal Bagh Sir, Head and Convener of this event, Bhoya Sir, Coordinator of this event, Ranjan Khut Madam, Coordinator of this cultural program, Rekha Jadeja, and all the participants, those who have come across the nation and globe. We would like to express our heartfelt thanks to you. Thank you everyone for being part of this cultural celebration. Last but not the least, you all are requested to moving further on the way to enjoy the delicious Gujarati food. As Sir rightly mentioned that it is a little bit sweet because the people are sweet. Thank you again everyone. I wish you all are enjoying the rest of the sessions. Good night.